Hello, I think we're live. Oh, hold on. You're muted. You're back. Hello, Margaret.
Hello, Henri.
How's it going? And hello back to everyone in the chat. How's it going? We are
All
back
right.
to hour 34 of the live stream.
This is actually going to be hour 35 of the
35.
live stream.
Awesome.
And are we getting a new host for hour 35?
I think so.
All right. Well, let's thank Henri for doing such an excellent job of hosting. We're going to switch over to Marie McGraw.
All right. Thanks, everyone. It's been a blast. I'll see you all tomorrow night late, I think. All right.
Thanks,
bye.
Henri. And welcome, Marie.
Woo! Hey, everybody. Great to be here with you again. It's 9 p.m. where I am in Colorado, 11 p.m. on the East Coast. I did just see someone ask if there's anything special you need to do to get your questions seen. Not really. I think if you can always repeat them and paste them more than once. We're trying to monitor the chat the best we can to grab those questions, but obviously sometimes we do miss them because it's moving fast. So paste it again, and if you paste it again close to the end of the talk, it's a little bit more likely that we'll see it. So yeah. Okay, so we are rolling into hour 35. So we've got 65 hours to go. And thanks again to our awesome organizing team. You guys have done an amazing job. So in the next hour, we're going to have two more awesome science talks. First, we'll hear from Albany Blackburn about orographic precipitation. So that is precipitation that falls in mountains and complex topography. And then we're going to have a talk from Professor Mariya Rugenstein about modeling surface temperature and global radiation with neural networks. So before we dive into our next talk, we want to remind everyone of why we are here. High quality weather and climate forecasts and data are essential to all of us. They affect us personally, our gardens, our vacations, where we buy a house, and huge parts of our economy. In the US, we have a really strong tradition of global leadership in weather and climate forecasting. We've been hearing examples of this all week, so here's another one. US meteorologists have been pioneers since the 1970s at using tools like Doppler radar to develop cutting-edge tools to improve tornado forecasts. US meteorologists are amazing at tornado forecasts in general. So yeah, over the years, US scientists have improved our weather and climate predictions through public investment in weather satellites, radar, on-the-ground observations, things like balloons. We just heard a lot about balloons and radiosondes. We've been hearing about planes and ships and unmanned vehicles that measure our weather and climate. So these strides have been incredible, and they've been supported by the American public through our public science institutes like NOAA, NASA, the National Science Foundation, the EPA, USGS, the Forest Service, and so on. But in recent months, as we know, the scientific enterprise has been put at great risk due to funding cuts. For example, the NWS cuts have resulted in a shortage of radar technicians and operators, meaning that if anything happens to a radar, they might not be able to fix them. And that's really scary considering we're in spring and summer severe weather season. So if you're worried about this or any other cuts to our science and research, please use the link on your screen to contact your representatives and tell them to save our forecasts and keep the lights on for weather and climate science. And talk about all this to your friends and your family too. It really does go a long way. So we hope that you keep learning new and fun things about weather, climate, our oceans, clouds, etc. And keep posting questions in the chat. We'll do our best to catch them. And finally, a reminder that all speakers, hosts, and volunteers are appearing in a personal capacity and are expressing their own views, not the views of any institution or other group. Okay, so I'd love to welcome Albany Blackburn to talk to us about orographic precipitation.
Hi, thanks so much. Hi, I'm Albany. I'm a PhD student at UC Berkeley. I'm very early on in my career. I've only been doing climate science for under a year at this point, but I'm really excited to talk to everyone about orographic precipitation. Like Marie said, this is just complex, fancy jargon for rain that is caused by mountains. So I'm hoping to talk about orographic precipitation in general, as well as just rain in general, and a little bit about the research that I'm doing on it. So let's talk about precipitation. But first, even let's take a step back. I think in order to understand precipitation, you first have to understand how clouds form. And I think, like, even me, not too long ago, I was like, oh, of course I know how clouds form. That's just the water cycle. We have evaporation, and then condensation, and then precipitation. And this is the story. And there's nothing wrong with this picture of the water cycle. This is what happens. But it's really lacking in details. I realized as I was thinking about, do I know how rain works? Do I know how clouds form? If I asked questions that were deeper than just this picture, I kind of came up empty. I didn't really know, I know now, what's happening in between these steps of evaporation, condensation, and precipitation. So my goal for this first part of the talk is really to teach you how rain works, how clouds actually form. And I'm hoping that you could actually take this away and like talk to your friends and loved ones. One, because I think it's very important to look at the world we have with wonder. And I think that understanding how it works really makes you look at it in a really new way. And my much more boring reason is that understanding precipitation in general will make understanding orographic precipitation much more easy. So let's talk about it. Again, first, I want to talk about clouds before I talk about precipitation. And I think I want to clear up, like, what exactly are clouds? Again, not very long ago, I was wrong about what clouds were. So first of all, I want to stress that clouds are made out of liquid water, of water vapor that has condensed out of the atmosphere. I certainly had the preconceived notion that clouds were water vapor that I could somehow see, but no, they are made out of liquid water. So we know that they're liquid. We need to ask ourselves, well, what makes water vapor condense? How do we get liquid out of air? As a generalization, we can do this by cooling the air. If we make the air colder, the water will condense. And I think this is intuitive to a lot of people. For example, think about having a nice, cool ice water on a hot summer day. Eventually, warm, moist air is going to hit your glass, and it's going to cool down, and it's going to condense on the outside of your glass. So that's all well and good. This is a very concrete example with the glass of cooling air on my actual glass of ice water. But how does water vapor cool in the atmosphere? Like I said, I'm based in Berkeley, so I want to give this example of the Bay Area fog that's ever so prevalent. Fog, which is very similar to clouds, it's really the same except it's at the ground. The fog in the Bay Area happens in a very similar way as to this condensation on your glass. What happens in the Bay is that we have warm air from the Pacific Ocean. It's blowing in west to east, coming into California. The coastal waters of California are very, very cold. So this warm, moist air goes over this very cold patch of ocean. This cold patch of ocean cools the air down. And because this air is getting cooled, water vapor will start condensing out of it and form this fog, which then blows into the Bay Area. So that's fog. I said it's very similar to clouds, but clouds are in a very different part of the atmosphere than fog. So for clouds, primarily how they form is when we have air that moves upwards in the atmosphere. The reason for this, again, I think is intuitive. First is that pressure decreases as you move up in altitude. There's less air sitting on top of you as you go up in the atmosphere. So that's less pressure from the air that's on top of you pushing down. Because the pressure decreases, the volume of the air itself will increase. Again, because there's less air sitting on top of it to be crushing it into a more compact form. And then because it is expanding, it is losing energy. And because it is losing energy, it is cooling down in temperature. And again, this is intuitive. I think it makes sense. If you've gone up into the mountains, you know it's colder the higher up in altitude you go. The snow is only at the top part of the mountain. But let's look at this picture in a little bit more detail. So let's go through step by step and figure out, how do clouds form and how do we get rain out of them? So first, like I said, we need upward motion of the air itself. So air is going to move up in the atmosphere until it reaches an altitude where it is allowed to condense out of the air. We call this the condensation level, which I've labeled here. Once that air hits the condensation level, it's going to start condensing, and we're going to get water droplets forming. These are teeny, teeny, tiny. But we still have this upward draft of air, and it's still bringing new air that has water in it up to the condensation level. So we're going to get more and more droplets. These droplets are also going to find each other and stick to each other and form bigger and bigger droplets. And this process repeats and it repeats until we get water droplets that are big enough to fall to the ground. By big enough, there's two things that they need to overcome. The first is that we have this upward wind that's pushing the water droplets up. They need to be heavy enough to counteract that. And also, once the water gets below the condensation level, it can start evaporating. So the water droplets need to be big enough that they don't just evaporate before they ever reach the ground. So in case I lost you somewhere in that explanation, here are the key points that you need to form rain clouds. The first is that you need to have water vapor in the air already. Like I said, clouds are made out of water. That water has to come from somewhere. We can't just magically create it. So it already has to be in the air to begin with. The second is that we need vertical motion of the air. Again, this lifting of the air causes it to cool down. This cooling makes the water vapor condense to form the clouds and also to make the droplets until they're big enough to reach the ground as precipitation. So I've been talking about a lot of this mechanism of needing air, needing to be risen. Something needs to make it rise in the atmosphere. One option to do that is with orographic lifting. This is a presentation on orographic precipitation. So how this works is if you have a mountain and you have wind blowing at the mountain, the air that's hitting the mountain isn't going to just like be destroyed and just disappear once it hits the mountain. Again, it has to go somewhere. And the mountain's going to force the air to go up the slope of the mountain. Again, as we've just established, if I have air rising and going up in the atmosphere, it's going to cool and condense, causing rain. So you can see that on the left side of this diagram here, that where the wind is coming from on that windward side of the mountain, we're going to get a lot of rain because the mountain is lifting up the air. But on the converse, on the leeward side of the mountain, on the side that the wind is not hitting, all of the air is going over the mountain and it's going to go back down. The reverse thing happens if it decreases, if it goes down in the atmosphere, it's going to heat up. So we're not getting any condensation from that. And in fact, we kind of rain out most of the water vapor that's in the air to begin with. Most of it is coming out in this precipitation. And we call this really dry side of the mountain a rain shadow because there is no rain there and it's very, very dry. And this is an effect that we can really, really see from pictures. So on the left here is a satellite picture of the Sierra Nevada mountain range in California. I should point out that it's been said in previous talks that across the US, generally we have a west to eastward flow of wind. So the wind is hitting the mountains from the west side. And you can see this, that the west side of the Sierra Nevadas are very, very green. They look very, very lush and lived in. But on the east side of the mountains, it's very, very dry. It's very sandy looking, very brown, and very dead looking. And this is, again, because of the orographic effect, that we are raining out everything on the windward side of the mountain, and then the air is descending on the other side, and we're not forming rain clouds on that side. And these are pictures on the right side here of just these opposite west and east sides of the Sierra Nevadas. Again, where this upper picture is like this nice green forest, and this other one is a desert. Death Valley, which is one of the driest places on Earth, is on the east side of the Sierra Nevadas. So the mountains have a big effect. That was just a zoomed in version of California. We can look at this on just the scale of the continental US. So the two plots I have here, the one on the left is a plot of the annual average precipitation taken from 1991 to 2020. And the plot on the right is a topographic map. It just shows the surface height across the US, with reds and browns being very tall, and the greens and the very pale greens being very, very low and close to sea level. And if you just take a first glance at this, you can see, oh yeah, the rain is kind of tracing the mountains. And I want to help guide your eye for that. I think there's a lot of interesting things you can see here. So let me point out, let's go west to east. In California and along the Pacific Northwest, all along the coast, we have the Coast Mountains, aptly named. We also have the Cascades up in Oregon and Washington, and the Sierra Nevadas that I pointed out earlier. So we have these like two strips of mountain ranges. If we go look at what they're doing to the precipitation, again, let me stress that winds are going generally west to east. We can see this first band along the coast. That is rain occurring because the coast mountains are there. And then just right next to them, we have this big band that's happening from the Cascades and the Sierras. If we move a little bit further east, we can look at the Rockies, which are going through Colorado, Wyoming, that area. And again, we can see that where we have a lot of peaks of this mountain, the rain is really tracing the shape of the orography of the mountains themselves. And not only are they showing us where the steep parts of the mountains are, we can also see that where we have valleys, lower parts within that Rocky Mountain area, we're seeing less rain there also. So there's kind of this like U-shape valley up in Idaho, and you can see the same sort of U-shape lack of precipitation on the precipitation plot, and similar things throughout the Rocky Mountains there. Then we can go to the East Coast. Here are the Appalachians. They go from the tip of Georgia up through Maine. The winds here can be a little bit different, so some other things are affecting the precipitation here. Hurricanes typically are coming in through the Gulf of Mexico. They're heading north, and they tend to kind of like hook east off of the United States. And this is kind of affecting where the wind is happening. But you can still see that the precipitation is tracking the mountains. For example, you can see the very southern part of the Appalachians has this very heavy rainfall. And then you can even see that a little bit further north in West Virginia. And you can even see the orography being traced out. For example, there's this very vertical south-north kind of section of mountains that is going through like Vermont, New Hampshire area. And you can see the same vertical line showing up in these plots of precipitation. This is all really to say that orographic precipitation is very important and is also very tangible. It's very easy to see exactly how important it is throughout the United States. To switch gears a little bit, I want to talk a little bit about my own research. So for my research, I study extreme orographic precipitation. By extremes, I mean the rainiest of the rainiest days. Typically for me, I'm looking at the top 1% of rainy days. And I'm also just looking at extreme weather events, specifically hurricanes. And I'll talk about that a little more in just a second. I also approach things from a dynamics perspective. What this means is that I'm trying to understand the physical mechanisms that cause things. I really want to understand the physics behind what's going on, what forces are causing this precipitation to happen. Are they what we expect or something different? And I want to talk a little bit about the motivations why I like these two different approaches for my own research. For one, I think that by understanding the actual physical mechanisms and developing theories and models for these things, I think we can better predict how our weather will respond to changes such as global warming. For example, one thing we do as climate scientists is we run simulations and models, and we run them decades out. But those models are based on the physics that we're feeding it. So we need to be able to get things correct. We can make good guesses based on historical data. But I think if we have like something rooted in very fundamental science, I think that'll lead us to better predictions when things are not looking the same as they do now. And for extremes, I think that generally people might be more worried about extreme weather rather than, say, the average weather. For example, maybe your average person would not notice if you got an extra centimeter of rain a year. But I think your average person would care a lot if their flood risk went from once in a lifetime to once every couple of years. So these are my motivations for this kind of approach that I've taken to my research so far. I want to talk about one specific project that I'm working on. It's tropical cyclones going over mountains. Specifically, I'm looking at the Appalachian Mountains. I showed earlier that hurricanes are coming in from the Gulf and hitting the Appalachian Mountains. When they do, they cause orographic precipitation, which you could see. One pertinent example of why this might be important is Hurricane Helene, which hit last year. And it was catastrophic, really terrible hurricane that led to over 250 deaths and $78 billion in damages. And a lot is unknown about how tropical cyclones interact with mountains. When you start learning how to do research and doing your own projects, you do a literature review and you try to ask yourself, what have other people done on this subject before? What I have found is that people say, oh, it's really complicated when tropical cyclones go over mountains, and they don't really elaborate. They just say there's a lot of different effects that might be competing. So for example, we don't really know what type of rain is occurring and what is dominating necessarily. And we don't know what mechanisms are at play that influence the storm as it goes over the mountain. Or we're not sure about them. We have guesses. And lastly, I want to just show one little tidbit of something I'm working on in this project. So these are looking at the tropical storm called Faye, which hit the US in 2008 and went over the Appalachian Mountains. This plot on the left shows contours of the precipitation, the actual real observed precipitation. And on the right, I'm trying to just use a very simple model. So some very simple explanation, very similar to what I've talked about here, where the air goes up because the mountain is forcing it up and we get rain from that. Basically taking that, saying nothing more complicated is going on and seeing what rain I get from that. And you'll see that these plots don't match up like at all. That when I do just a very simple model, it's very, very badly under predicting the rain that we see and also getting the distribution not quite right. So something more complicated is probably at play. I have some guesses as to what that might be, but I look forward to probing it and figuring it out to try and better understand the hows and the whys of what is going on with this type of precipitation. And that's all I have for you. Thank you all so much. And I will take questions.
Amazing. Thanks so much, Albany. That was a great talk. And it's really good to hear from early career scientists like you. You know, we were all in that place at one point, learning, like starting from scratch, learning about weather and climate. I certainly didn't study it until grad school, and I think that's true of many other people. And in my opinion, early career scientists often give the best talks because they really put in the effort and they don't assume that you've been thinking about this stuff for 30 years. So that was awesome. We have a few questions in the chat. So we have a question about your precipitation map. And if you're looking at all kinds of precipitation or just specifically orographic precipitation, our listener, Dr. Kieprish, was thinking that the Great Lakes might have more precipitation just due to lakes. And were you looking at just rain? Did you include snow? Can you just talk a bit more about that?
Were they referring to these maps? Do you know?
I think so. I believe so. Yeah.
I will be very honest. I did not make this map. I stole it off the internet because I thought it illustrated this point well of tracing it out. So I would have to go back and track that down. I'm really not sure.
I'll also just add that so snow, for example. So I was a Great Lakes person who grew up in the Great Lakes. We get a lot of lake effect snow. 10 inches of snow is often like only 1 or 2 inches of precipitation. So it doesn't, it might not scale the way that you think it does. So that could be maybe contributing to part of the confusion. So we have another quick question from Kit the Kite. Is orographic precipitation and rain shadows why there are often deserts on one side of a mountain range?
Yes, like I showed with the Sierra Nevadas, that is really the driving factor of why that is the case. This is the case even on smaller scales. Like I said, I'm from Berkeley. We have just hills. Like campus is built on a hill. If you cross over those hills into, say, the Walnut Creek area, it's really dry there. Not quite a desert, but like you can see that it's like yellow grasses instead of like very green like Berkeley is.
Yeah, even the East Bay and the peninsula are kind of different, and I think that's maybe a little part of it. Okay, right before we transition to our next speaker, we do have a quick question from Kelsey Ward about, is there anything citizen scientists can do while they're out in the mountains to gather data to help with this?
Ooh. I'm not really sure. I am very early career. I haven't really delved so much into the like actual observational part of it, other than just using the data. I believe that I have heard talks from other grad students who do field campaigns, and like I'm sure there are rain gauges in the mountains. I'm not sure what getting involved with that might look like. Perhaps. I hope. Yeah, I don't have much more to say to that, other than it might be a possibility.
So I will say, if you live in the mountains, one thing you can do is join a group like CocoRoss, a community rain, hail, and snow network. I'll drop the link in the chat in a sec. You can set up a rain gauge and a hail gauge at your house, and then you report. So you help us by taking good measurements at your house. So you don't have to live in the mountains to do this, but if you are especially interested in this and you live in the mountains, that's one thing you can do. And like I said, I'll drop that link in the chat in a second. Well, thanks again, Albany. That was fantastic. And good luck with continuing on with your PhD work. I'm sure you're going to do a great job. We care about quality weather and climate forecasts and weather and climate data like the Argo floats, which have been transformative for oceanography. And the U.S. has this really strong tradition of leading the world in weather and climate science that has gone back nearly a century. But unfortunately, that leadership is at risk due to the proposed funding cuts. So another thing that is on the chopping block potentially is the NOAA facilities that monitor toxic algae blooms in the Great Lakes. So if this is concerning to you or other cuts are worrying to you, please use the link at the bottom of the screen to contact your representatives. Call them if you can. Tell them to save our forecasts and support weather and climate science. And again, talk to your friends, talk to your family, and talk to your communities. It really, really helps. All right. So again, we hope you're learning. We hope you're enjoying this live stream. Keep posting your questions and your comments and your enthusiasm. And before I hand things over to Jeremy Rugenstein to talk about paleoclimate, I'm just going to remind everyone that all speakers, hosts, and volunteers are appearing in a personal capacity and representing their own views. So on that note, Jeremy, take it away and give us some education on paleoclimate. Wow, I love what we're starting off with. So
yeah, thank you, Marie. Is my audio okay?
Yep, you're
Wonderful.
coming in loud and clear.
Well, thank you, everyone, and thank you for the organizers, and thank you for everyone who's tuned in. I want to talk now about why it's important to understand past climates. This is a picture from the Colorado Plateau. This is the goosenecks of the San Juan. And what's shown here are the sediments that are about 300 million years old from the last time the Earth experienced a major ice age. So today we live in an ice house climate. That is to say, we have ice, permanent ice at both poles. And the last time this happened on Earth was around 300 million years ago during an event called the Late Paleozoic Ice Age. So first I'll talk a little bit about myself, my own motivation for research in my group. I'm a paleoclimatologist. I'm also a geochemist. By that, I mean, I don't study future climate. I don't study current climate. I really study how the Earth's climate changed in the past. And this is useful because it places anthropogenic climate change in context. It's also a way of testing climate models. It's also just cool. The Earth has gone through a lot. And if we want to understand what it's gone through, why are there the species that exist today? Why did some species go extinct? How did life survive on Earth for 3.5 billion years? It's worth looking at past climate and understanding what drives changes in climate. So the specific questions I like to ask are kind of what was the hydrological cycle like when CO2 was higher in the past? And also, why even does atmospheric CO2 vary over the history of the Earth? So we know CO2 has been higher in the past, and it has come down to current levels or pre-industrial levels prior to widespread burning of fossil fuels. And I should point out, 90% of my group's funding comes from the NSF. This research really wouldn't be possible without federal support. I've shown pictures of my 4 students, Taylor, Rachel, Gabby, and Adam. All of them are at least partially or fully supported by federal support. And they wouldn't be receiving the training that they're receiving today without continued support from NSF to study past climates and to train future scientists. So let's talk about why we want to study past climate. Well, we know atmospheric CO2 is rising. This is a graph of measured atmospheric CO2 from 1960 to around 2020 at the Mauna Loa Observatory in Hawaii. Not only is it going up, but we think it's going to keep going up. So these are projections based on different ideas of how economies will evolve in the next 100 years. And essentially, very high emissions pushes us above 1,000 parts per million. Even really drastic attempts to lower emissions still see a rise to almost 500 parts per million. And that's projected to increase temperature, right? So we have lots of climate models. This is what most of this live stream much of this live stream has been about, that project widespread increases in temperature and global temperature up to maybe 5 degrees Celsius by the end of the century in sort of the worst case scenario. And how do we know that the Earth is going to warm? Well, there's physical theory. We can measure the warming today. We have models of the climate. All 3 of these things are topics that people in this live stream have talked extensively about. But we have another reason as well, and that is to say we can look at Earth's past when CO2 was higher, and we can see that the Earth was warmer during these periods. So let me show you a graph that summarizes a lot of our knowledge of how the Earth's climate has changed over the last 100 million years. There's a lot going on in this graph, so let me walk you through it. On the x-axis here is the last 100 million years of Earth history. And then shown here is projections of CO2 change for the next 200 years. In this gray bar is what we roughly think atmospheric CO2 has done over that last 100 million years. It turns out to be very hard to measure CO2 in the past. Probably many of you have heard of ice cores. Unfortunately, the ice cores only go back about 1 million years, so they get us to about here. The rest of this is all deduced from measurements of leaves and of isotopes in marine organisms and other fairly sophisticated but also somewhat uncertain methods. In the colored line is an estimate of global temperature over this time. Just to orient yourself on this plot, the dinosaurs went extinct here. That's 66 million years ago. So the last 66 million years have been the age of mammals, the so-called Cenozoic. We've had an Antarctic ice sheet for the past 34 million years. And we've had ice in the Northern Hemisphere, primarily in Greenland, but also during ice ages in Canada and in Scandinavia, only for really the last 3 million years. And what I want to point out here are some really remarkable things. Just 50 million years ago, when CO2 we think was around 1,000 parts per million, we think the Earth reached temperatures of about 27 degrees Celsius on average. That's about 12 to 13 degrees Celsius warmer than today. If you go back even further to really the peak of the dinosaur era, this would be about 95 million years ago, the so-called Middle Cretaceous, we think temperatures on Earth might have reached as high as 35 degrees Celsius. So that's 20 degrees Celsius warmer globally than it is today. And that took only a CO2 that we think was maybe a little over 1,000 parts per million. So maybe to put in context our own emissions, even if we really start to curtail fossil fuel burning and stop to slow emissions and therefore the rise in CO2, this is considered a sort of intermediate scenario for economies. We are looking at returning to a time period in terms of CO2 that hasn't existed in the last about 25 million years. Returning to a time period when we think Earth's temperature might have reached 20 or 22 degrees Celsius on average, so 5 to 7 degrees warmer than today. If we think about the worst case scenario, we just keep burning all the fossil fuels that we know exist in sort of achievable reservoirs. We potentially push our climate to a level of CO2 that has really actually not been observed in the last 100 million years. So, we are really pushing the envelope here of what we know the Earth's climate has been sensitive to in the last 100 million years. So for the rest of my talk, I want to focus a little bit more on specifically my research. What I just presented might sound like a lot of doom and gloom. And I want to say that paleoclimate is a good way of testing a lot of models and seeing if sometimes the projections are accurate or not. So I'm going to look at a time period about 15 million years ago. This is called the Middle Miocene. We know that temperatures during this time period peaked about 7 degrees Celsius warmer than today. We think CO2 was anywhere from 300 up to about 500 or 600 parts per million. So it was a warmer climate than today. There was an Antarctic ice sheet, but there was no Greenland ice sheet. And I'm going to focus on one specific area, that is to say the US Southwest, where there's a lot of debate about what's going to happen to climate and particularly precipitation as the world warms, right? This is an area that experiences a lot of water scarcity. And so even small changes in precipitation can have a major impact on ecosystems and societies in the US Southwest. So this is largely the area I'll be talking about today, sort of New Mexico, Arizona, southern Utah, southern New Mexico. Today, this region receives much of its moisture from the Pacific in the winter. And in the summer, most of the moisture comes from the North American monsoon, sort of averaged over the whole region. About half comes in the winter, half comes the summer. And there's a lot of concern about how both of these circulation systems, both the Pacific wintertime moisture and the monsoon, are going to respond to warming. There's been a lot of work using climate models to try and understand what's going to happen. This is from a really, I would say, almost classic paper now, projecting changes in precipitation into the future as the world warms. And let me just walk you through this plot. So we have time between 1900 and 2100 on the x-axis. On the upper panel, we have the wintertime precipitation, and in the bottom panel, we have the summertime precipitation. The blue line is precipitation projected beyond about the year 2010. The green line is projected change in evaporation, and the red then is changes in runoff, so just precipitation minus evaporation. And what I really want to point you to in this graph is that as the world warms, starting from 2000 onward, precipitation in this blue line is projected to decrease. It's pretty noisy, but it's projected to decrease in both the winter and the summer. Now, this is just from a handful of models about 15 years ago. More recent model simulations show a similar picture. There's thought to be potentially widespread drying in the Southwest due to increasing temperature and rising CO2. But we can use the geologic past to see if precipitation really does decline at higher CO2 and higher temperatures. So what I'm going to do is bring you back to the Middle Miocene, 15 million years ago. And we're going to try and determine if precipitation really was lower. And in particular, was it lower in the winter or was it lower in the summer 15 million years ago when CO2 was quite a bit higher? So how do we do this? This is kind of an image that summarizes a lot of our field work. So here we have a map zoomed in on northern New Mexico. Here's Albuquerque. Santa Fe is right here. This is the southern extent of the Rockies, the Sangre de Cristo range. And this red dot is our field area outside Espanola, New Mexico. This is an image of what the outcrops look like. It's a lot of, to me as a geologist, really beautiful sedimentary rocks. These are all so-called past soils. So each one of these layers was a soil exposed in the surface, and then maybe a big flood came along, deposited new material, and that soil kind of moved up in the sedimentary column. These white dots that you can see here, those are made of calcium carbonate, and that's carbonate that formed in the soil. So if any of you are from sort of arid parts of arid or semi-arid parts of the United States or anywhere in the world, if you garden at all, you have to deal with this. There's a lot of carbonate in the soil, and this forms from these really dry climates. This picture here is a zoom in on what those carbonates look like. We call them pedogenic carbonates. Carbonate is made from calcium, carbon, and oxygen. And so we can actually measure those oxygen isotopes. We measure the ratio of 18O to 16O. And that measure, which we denote as delta 18O, tells you something about paleoprecipitation. So that oxygen that's locked into that carbonate comes from the water that fell during rainfall or snowfall. We can measure this using mass spectrometers. This is a picture of one of my close colleagues at the University of Leipzig, Katharina Merner, introducing one of our samples into a mass spectrometer where we can measure these two isotopes. Now, why are these isotopes a useful tracer in the Southwest of what's going to happen to precipitation? Well, it turns out isotopes in the Southwest, and this is true actually in many places on the globe, are really sensitive to seasonal changes in precipitation. So what I'm showing you here is a plot of months of the year against the delta 18O of water that we've collected outside Santa Fe, New Mexico. The blue is precipitation delta 18O. So every month we collect a sample of precipitation outside Santa Fe and we measure that for the delta 18O. And you can see the delta 18O in the winter, say January or December or February or March, is pretty low, -15, -20 per mil. And in the summer, it's very, very high. And this is reflective of those two major moisture sources I told you about earlier. So these low values are reflective of wintertime moisture from the Pacific, and these high values are reflective of moisture from the monsoon. So if these values then get locked up into carbonates, we can actually use the carbonates to infer were the carbonates recording precipitation in the winter or in the summer? And how did that seasonal balance in precipitation vary as CO2 was much higher in the past? So let me show you the data, and I'll walk you through the data. So what we have on the x-axis here is the delta 18O inferred of past precipitation, okay? What's shown here on the y-axis is age. So this is 17 million years ago. This is 11 million years ago. The peak of that middle Miocene warming is about 15 million years ago. The blue dots are all of the samples we've collected and measured for delta 18O, okay? And we have attempted to convert those to the sort of precipitation value that would have fallen. So let me walk you through this. If these carbonates were reflective of summertime precipitation, so that is to say there was a lot of summertime precipitation 15 million years ago, we would expect them to have values around this dashed line, okay? So that is to say, if there was a really vigorous monsoon 15 million years ago when CO2 was higher, this is roughly the value we should be seeing in these carbonates. And as you can see, none of these carbonates overlap with that value. If instead these carbonates sort of reflect mean annual precipitation, so there's no real seasonality in precipitation. Some of it falls in the summer, some in the winter, some in the spring, some in the fall. This would be the value we expect in this dashed line. And if these carbonates reflect a lot of wintertime precipitation, then this is the value we expect in this dashed dotted line, okay? And as you can see, most of these carbonates reflect the value we would expect for wintertime precipitation. Just to show you, we can actually dig modern soil pits and look at the carbonate that forms today. Other researchers have done this as well. And this is what we expect. This is the value we get for delta 18O in modern soils. It's shifted to much higher values. It's much more reflective of a sort of an equal balance between summertime precipitation and wintertime precipitation. And ultimately, what I take away from this data is that most of our data from 15 million years ago are really skewed towards wintertime precipitation. That is to say, when the world is warmer, we don't see a lot of summertime precipitation. So it does seem that the North American monsoon really was quite a bit weaker 15 million years ago when CO2 was higher. But instead of just a weaker wintertime, weaker summertime monsoon, we also have much more wintertime precipitation. So when CO2 rises, at least in the past, it seems like you shut off the monsoon, but you actually induce a lot more wintertime precipitation. And I can say that because one, these values align much more closely with what we observe today for wintertime precipitation, and they're much lower than the delta 18O observed in modern soils. So just to summarize all of this research, warmer climates in the past in New Mexico appear to be associated with more wintertime precipitation, but less summertime precipitation. So the kind of dual season drying that models project, that is to say both declining wintertime precipitation and declining summertime precipitation, perhaps that's just a transient signal. This is just I'm not going to say artifact, but a fact that these models are only run for 100 years, and perhaps eventually sometime in the future, the Southwest might become wetter. It could also be that there's an issue even in the models, and that these data suggest that actually, as CO2 rises, really the Southwest should be getting more wintertime moisture and less summertime moisture. So I want to close by stressing that I think paleoclimate can really help us understand what we are doing as a society to the Earth system. One, it permits us to put current warming in perspective, right? We can compare our projections of future CO2 and say, well, when the world hits 1,000 parts per million, what does the geologic record tell us that the temperature will be? And, that temperature is largely 10 to 15, even 20 degrees warmer than today. It's certainly a way of saying, if we reach 1,000 parts per million, we're going back to a time when there was no northern hemisphere ice and there was no Antarctic ice. You've melted all the ice sheets at this point. It also allows us to test climate model projections of future change, right? So, models, and I go back to the example in the Southwest, models project that the Southwest will get drier. And there's a lot of good reasons to think that this could be the case, but we can go back to the geologic record and look in the Southwest, where we have sediments, where we have paleoclimate data, and say, well, was the Southwest really actually drier when CO2 was higher? And if it was drier or if it was wetter, what were the reasons behind that change? And at least from our work in New Mexico, it seems like the Southwest, maybe the monsoon gets weaker, but the wintertime westerlies and moisture delivered in the winter actually increases relative to today. And I'll finally close that, paleoclimate in general just leads to a better understanding of our only planet. The Earth has really gone through a huge amount. And I think this graph shows that really well. During the peak of the time period when dinosaurs were alive, the average temperature on us was 35 degrees Celsius. There was no permanent ice on the planet. And it allows us to understand, how did life survive this interval? How did life adapt to really warm temperatures? Why did the Earth cool? What is it about the past 100 million years that has led to a long-term cooling that we are now reversing? So I'll leave it at that, and hopefully there's some time for questions. And again, thank you to the organizers, and thank you to everyone who stuck around late into the night to listen to the science my group likes to do.
Awesome. Thank you so much, Jeremy. That was great. And before you got on, we had several questions about paleoclimate. So I hope all of those people were able to stick around for your talk. So we have a couple of questions about carbonates and where they are formed. So maybe I'll give you a couple and you can answer them like rapid fire. So the first one, how quickly does it take for calcium carbonate to form?
Oh, that's a great question. In general, those nodules that I showed you are I would say, about 1,000 to 10,000 years. They really integrate a lot of time.
but also fast for geologic standards.
Yeah, fast for the timescales I think about.
Yeah. Okay, so we've got two that are related to carbonates and kind of related to each other. So we've got a question about why are the seasonal swings and distributions apparent in some regions or biomes and not others?
Yeah, so the swings in oxygen isotopes that we see in precipitation largely are driven by temperature changes combined with topography over which moisture has to travel. So you see these large changes in delta H&O in regions largely in the mid latitudes where there's large scale temperature changes between the winter and the summer. You don't see this in the tropics. And that's because the temperature, to first order, the temperatures just don't change as much in the tropics. And so the controls on precipitation delta H&O are somewhat different. Now, unfortunately, those exact seasonal swings don't get precisely recorded into carbonates. They're just too fast relative to carbonate formation. Instead, carbonates are kind of recording the long-term average of the precipitation that falls. So if you shift more towards the winter, you'll get a lower delta H&O. If you shift more towards the summer, in the mid-latitudes, that is, you'll get a higher delta H&O. And that's how we use these carbonates to try and understand past precipitation.
All right. And then on a related note, why is your field site sort of in the desert Southwest? Do the carbonates preserve better out there?
Yeah, that's a great question. It turns out New Mexico has one of the largest rift valleys on the planet. This is the Rio Grande Rift. It stretches from roughly Leadville in Colorado down into northern Mexico. The Rio Grande follows much of that rift valley. Because it's a rift valley, it's opening up, and as a consequence, there's a lot of space to store sediment in this, and so there's a really high amount of sedimentation in this valley. And that preserves a really high resolution record of climate because all of that was at one point, the land surface, and there were plants growing on it, animals living on that land surface, and then more sediment gets deposited, and another, a little bit later, and again, plants and animals thrive on that surface. So it provides a really great paleoclimate record in a set of basins that are pretty well dated. That is to say, there's been a lot of work by the New Mexico Bureau of Geology and other scientists to understand the timing of all of this sedimentation.
Amazing. And you're giving me ideas for my next road trip. I love it. I had no clue we were so close to a huge rift valley.
It's spectacular. If any of you are familiar with George O'Keeffe's painting, she painted a lot of these outcrops because they're just so spectacular.
That's what she was going for. All right. Okay. So next we have a couple questions about estimating the precipitation changes. So someone asked for a bit of a clarification on how the quantity of past precipitation is estimated. So I wonder if you can elaborate on that a little.
Yeah, that's a great question. And I unfortunately didn't have time to talk all about that. The way we can only really infer quantity of precipitation versus seasonality. And the way I like to infer the quantity of precipitation is by looking at the other isotope that we can measure from calcium carbonate. So, calcium carbonate is made of calcium, carbon, and oxygen. And I talked a lot about the oxygen isotopes. But when you measure this on a mass spectrometer, you actually get two isotope systems for the price of one. You get oxygen and carbon. It turns out the carbon isotopes in these carbonates are directly related to the amount of plant productivity on the surface. So if you have a lot of plants growing on the surface, it's a very productive environment. You'll get a low carbon isotope value. And if you have a really arid environment, you'll get a high isotope value. If we look at these carbonates from New Mexico, they tend to actually have a very low carbon isotope value. And what that implies to me is that you had a lot of plant productivity 15 million years ago. And of course, to first order, if you're going to have a lot of plants, you have to have a fair amount of precipitation. In fact, more than today. So we can show actually that through carbon isotopes that not just that the seasonality of precipitation shift towards the winter, but you must have had more wintertime precipitation to drive a really productive ecosystem. And this actually ties in one of the reasons why scientists first started studying this area is it has one of the most amazing and well-preserved fossil records anywhere in North America. So it's been the site of fossil work for more than 150 years. And it turns out the fossils in these sediments are really reflective of a pretty productive ecosystem. So you have a really diverse fauna. You have a lot of organisms that must have lived close to water. So they require, like salamanders, that require sort of easy access to water. So all of these things point towards greater quantity of precipitation, not just the shift towards more wintertime precipitation.
All right. Awesome. We also had a couple questions about sort of like the process of collecting this data. And, does it take a really long time to collect? How do you know the age of the sample before you measure the isotope decay? And then we also had a question about if there's a way for citizen scientists to help with data collection.
Absolutely. Yeah, let me talk quickly about the dating. So there's lots of ways to date sediments. One of the ways at this field site we can date sediments is one of the nice things about North America as a geologist is there have been lots of volcanoes going off in North America for more than 80 million years. And those volcanoes shoot ash into the sky that gets deposited on the ground. And we can date the minerals in those volcanic ash deposits because from basically when they formed. And so this field site is actually full of these ash deposits. And a lot of my colleagues and students have worked to date these ash deposits. We can also date these sediments using the paleomagnetic record. So the Earth's magnetic pole shifts every 800 to 10 million years from the northern pole to the southern pole. And that induces a different magnetic signature in the sediments. And you can actually use that to date the sediments. So this is actually one of the really well-dated sediments on Earth. As to citizen science, absolutely. We actually regularly have volunteers help us in the field to collect these samples. We spend typically a week to 2 weeks for any given field season in the field collecting. The way I think about it is we can collect about 50 meters of sediment a day. That is, we can measure 50 meters up in an outcrop per day. And so if we need to do 500 meters, it takes us about 10 days. All of that precipitation isotope data I showed you, that's all been collected by volunteers that I actually recruited through another program run out of the Colorado State University called COCO-ROS, which is a network of people that measure their precipitation on a daily basis. And so I've asked a lot of these volunteers to just throw another precipitation sampler in their backyard and send me the sample so I can measure it for isotopes every month.
Wow. It's like we coordinated this. I was just mentioning COCO-ROS like an hour ago. So we put the link in the chat again.
Wonderful.
Check it out.
Great
Anyone
program.
can sign up and help us measure rain, snow, hail, etc. Okay, so it's the top of the hour. So thanks again, Jeremy. That was awesome. We got so many questions. If you have time, it's kind of late here, but if you have time, you can pop back in the chat and see if there's any more you want to answer. We did,
Cool.
I think we touched on most of them at least. Okay,
Cool.
So
on
that, yeah, and yeah, lots of great questions on that. So we're wrapping up our 36th hour and heading into hour 37. So I'm going to sign off for the night, and Ryan North is going to take over from me. So have a good night, and again, keep up the energy and enthusiasm, especially all of you early career scientists in all fields, not just weather and climate.
All right, thank you for that transition, and hi everyone. As she said, my name is Ryan North, and I will be your host for the next 2 hours. I'm a PhD student at Texas A&M University. If you tuned in last night, actually at this time, you may have heard my talk about Chicago O'Hare International Airport, and if you were there, welcome back. I'm thrilled to be here once again. And if you're in the Central Time like I am, thank you for starting off your Friday with us. With those introductions out of the way, I'd like to say thank you for joining us in our 37th hour of the Weather and Climate live stream. We have 63 more hours to go, and it's great to see you all here. We've got another great hour of science ahead. So as we transition here to the next speaker, I have some things to say. And the first thing is I saw a question pop up in chat asking if I create dinosaur comics. That is not me. I cannot take credit for that. So sorry to disappoint if you thought that you met that Ryan North. He is much more famous and much more artistic than I ever will be. But how I can't speak to that. But I do have a few comments of my own to say regarding why we're here on your screens this evening or morning, depending on where you are. So the Weather and Climate live stream and the community behind it has set out to host this 100 hours of continuous science talks to help save our weather forecast here in the United States. So we are currently halfway through our 37th continuous hour, and we'll be continuing to showcase our work for another 62.5 hours. So there's lots of great science to come. For anyone who has joined us recently, hello and welcome. So just a quick intro to me again. So again, my name is Ryan North. I am a PhD student at Texas A&M University, and I will continue to be your host for the next hour and a half. I'm not sure how many of you are familiar or SpongeBob or SpongeBob fans out there, but sort of as I was thinking about what I was going to say during these interludes, I was thinking of the scene where Mr. Krabs comes out and rings the cowbell after the Krusty Krab starts doing their 24-hour never closing days, and it was just. It doesn't really have anything relevant to this, but just sort of what I envision myself here, sort of out here with a cowbell saying we're at the 37th hour. So, well, completely random thoughts that I have on my way while sitting here. But yes, I see in the comments there, let's give it up for day 15. I could hear him talking in my head. But anyway, sort of to back on topic, we've had a lot of great talks so far throughout this entire stream. And if you're able, I was able to catch some of them earlier, and they've all been extremely interesting. And our next speaker is going to be no exception to that. But again, just a brief reminder that our speakers are appearing in their personal capacities, and they're expressing their own views, which may not be those of other participants or their funding agencies or their affiliations. However, we're all here with a unified purpose, and that's that Americans deserve good, accurate weather forecasts. U.S. scientists have led the world in weather and climate predictions, and we're here tonight advocating for this to continue. The U.S. was the first developed computerized The U.S. was the first to develop computerized weather forecasts, and we were the first to use computer models to see how climate impacts, or sort of how the climate is impacted by carbon dioxide in the air. We have unparalleled observation networks, and these consist of many different instruments, from surface observation stations at airports and the ASOSs, or the automated surface observing systems, up to satellites continuously monitoring the Earth from space. So this excellence is because of the investment from all of you guys, the American people. And U.S. federal funding for science is essential. And we are today here asking you to reach out to representatives and advocate for science. So once again, the link to reach out to representatives is floating across the bottom of your screen, and we really do appreciate you reaching out and advocating for us and other sciences if you have a passion for those. And with that, I am pleased to announce our next speaker, which is going to be Kay McMonigal. And I stuttered on your name earlier today, but I hope I got it right this time. And with that, I'll give you the floor.
You did. Awesome. Thanks, Ryan. I hadn't thought about SpongeBob in like a very long time. So
I don't know. It just seems like an appropriate time for that.
all right, let me share my screen. All right. Sorry, everybody. Just taking me a second here to get my screen shared. And it seems like I have to give Chrome some permissions.
Yes, and then you'll have to pick the window you would like to share.
Okay, sorry, I did not get to the Chrome permissions before this. Okay, I think we're going. All right. Just a second here. You'd think everybody would be great at this after all of the COVID times being on Zoom and things, but
we all ran into our little snafus along the way. I was having audio issues last night, so you never know. Even the most prepared you can be, and you end up having issues.
Well, thank you. for making me feel like I'm not the only one then.
Of course
Okay.
not. There will always be tech issues.
All right, let me try that again now. I don't want to upload a file. I just want to share my screen.
So sort of as he's working through that, I do have the title of your talk here, so I could read that out to you. So Kay will be presenting his talk called "What Ocean Processes Lead to Predictability." So I have a few. I have a few guesses, but I won't ruin the surprise for everybody. But we can come back and see how accurate my guesses were.
It's claiming I need to restart Chrome now. Is that something I need to do, Ryan? Because then I'm going to be off this link. Let me see if I can just upload some slides quickly here.
If you want to try uploading it, I can fill in the time a little bit and do some talking a little bit here.
Yeah, it says it's uploading, so I don't know, you can tell me more about SpongeBob or something.
That's about all I know. For some reason, as I was sort of typing up some speaker notes for tonight, that was the thought I had in my head. That's what I was thinking about. Day 15, day 30, whatever it is. It's late at night for many of us, and some of us are probably coming here after a long day. So I saw someone ask you about fun facts for myself. So if you were here for my talk last night, I told you all that I love to travel. And I love talking about airplanes. I love talking about trains. You can sort of see one on the back wall here. That is a wooden cutout of a Chicago elevated rail car. So if you've ever ridden the L in Chicago, I actually have one of those posted on my wall. And on the wall next to me here, the is a map of the Chicago elevated rail system. So I absolutely do love trains as well as weather. Oh, yes, I did actually write it into my notes, but. Okay, so I will hand the floor over to you.
Awesome. Thank you. All right. Sorry for the technical problems, everybody. So as Ryan just said, I'm going to talk some about sea surface temperature anomaly persistence and what we can learn about this in a model hierarchy. And I want to also just note, you can see this is a paper that we wrote up last year, and there's quite a few people on this. So this was really a big team effort with people from many different institutions. I'm located in Fairbanks, Alaska, so it's 9:30 p.m. here and still light out. But there's people kind of from all over the US that were involved in this. And this was funded by the National Science Foundation, and we used some of the high performance computing resources that we have through NCAR. All right, so let me give a little bit of a background. Okay, so we really want to be able to understand sources of climate variability. And the reason for that is that improves our ability to predict future weather conditions. So kind of the classic example of this, which I'm sure many people have heard of, is El Nino. And right now we're not in an El Nino or a La Nina. We're in what's called neutral conditions. But we kind of expect that to continue to be the case. But let's hypothetically say that we thought an El Nino was going to develop into the fall. So maybe we thought that we saw some signature in the ocean, and that was a sign that we're going to have an El Nino coming. Then we could look at something like the figure on the right here, which comes from climate.gov, and this is what happens in a typical El Nino winter. So if we knew today that we were going to have an El Nino in the winter, then I could tell you something about what your conditions coming up in the next few months might look like. So for me in Fairbanks, it would probably be a warmer winter than typical. If you're in Southern California, it would be wetter than typical. And if you're in Illinois, it would be drier than usual. And so that's really great information to have, especially if we can do it longer out than a typical weather forecast. So if we can say that kind of months ahead of time, that could be really useful for lots of different things. So I listed some types of industries that would be interested in this, but there's many more. So things like fisheries might have some interest, maybe where you catch fish or what fish you catch are going to depend on our weather patterns. And then also things like agriculture, what types of plants you should plant, when you should plant them, and disaster planning and insurance. So, maybe if we have a wetter winter than usual, if you're in a drought in Southern California, that's great, but maybe it also means that there's an increased chance of something like landslides. So again, just really useful to be able to predict all of these things, at least particularly at longer lead times, so you can kind of prepare for them. And when we think about what gives us this type of predictability, potentially, especially months ahead of time, we expect that some of this could come from ocean processes. And that's because ocean temperature anomalies, so the ocean being warmer or colder than it typically is, tend to last for a pretty long time. And so I'm going to call that persistence. All we're thinking about is if some area of the ocean is warmer than usual, how long is it going to stay warmer than usual? And so I gave an example here on the right-hand side. This was the Pacific blob, as it's called. I love that name because it's a very unscientific name, but just this blob of warm water in the Pacific. And there was one in 2014, and then kind of a new blob. Sometimes people call it like the blob 2.0 in 2019. And these stuck around for a pretty long time. And as you can imagine, this had a lot of impacts on things like ecosystems and weather patterns. And so what we would like to be able to understand is what is causing features like the blob, or really any sort of warm or cold period in sea surface temperatures that then maybe is going to give us some hints of how we can better predict weather on kind of monthly to longer timescales. I told you that a lot of this is coming from the ocean. I'm going to tell you a little bit about why we think that a lot of this comes from the ocean. And the key thing is that the ocean has higher heat capacity than the atmosphere, so it can store a lot of heat. So when I say heat capacity, what I mean is the heat required to raise the temperature of 1 gram of some substance. So I'm thinking seawater here, but could be anything else, by 1 degree Celsius. So if your coffee is kind of, lukewarm, you can microwave it, you can get it warmer. What you're thinking about is how much heat do you have to add to raise the temperature of your coffee by 1 degree C. And it turns out you can do the calculation and find out that the upper 10 meters of the ocean, that's about the upper 30 feet, contain as much heat as the lowest 10 kilometers, or about 30,000 feet, of the atmosphere. So really all that means is that the ocean has a lot of heat in it. And because of that, it heats up and cools down slowly, much more slowly than the atmosphere. So if you have like a really warm day, the ocean isn't just instantly going to become warm because the air was warm. It'll take a lot longer for the ocean to heat up. And this causes quite a few kind of features in weather. And one that I'm showing here is what's called a sea breeze. So if you've been near the ocean or like a large lake, you might notice that there's a wind that changes direction over the course of the day. And what's happening is during the day, when there's sunlight, the land will tend to warm up pretty fast. And the ocean doesn't warm up as fast. So the land is going to be warm. Where we have warm land, we have rising air. The ocean, relatively speaking, is going to be kind of cold. And so there's falling air. And then we get this circulation cell where the winds are blowing from the ocean towards the land. And then at night, you get the opposite. So at night, the sun goes down, the land cools off pretty quickly. When the sun goes down, I guess it depends a little bit how humid it is, but in many places, when the sun goes down, pretty quickly it'll cool off if you're over land. But the water is going to stay pretty warm because it got all that sunlight over the course of the day. It absorbed that heat, and it's going to hold on to that heat due to its high heat capacity. So now we get the opposite situation. Air is falling over land and rising over the ocean, and we get a wind that's blowing offshore. So we know that we think that ocean is going to give us some of this predictability, but we can also get some predictability from processes in the atmosphere. And so some of the atmospheric processes that can lead to enhanced persistence or just longer periods of warm or cold temperatures come from clouds. One of them is what's called the low cloud SST feedback. SST here is sea surface temperature. So you can just think about that like it's the temperature of the ocean. And what's going on here is when we have clouds that look like this, they're really thick and they can reflect a lot of sunlight. So if you're outside on a day like this, you know, it's not going to be the warmest day ever. It's going to be cloudy. You're going to be probably relatively cool. And so when we have these clouds, it'll lead to cooler temperatures in the ocean. And then that makes the atmosphere more stable. And that actually leads to more of these clouds forming. And then it gets even cooler. So that's a positive feedback. So you can imagine if we have an anomalously cool time, then we're going to get more clouds and then it'll stay cool. And so that's another feature that can lead to longer persistence of these cold or warm periods. But instead of coming from the ocean, now it's coming from clouds. So what I've said so far is we expect ocean processes are going to enhance our sea surface temperature persistence. I told you that that's due to the high heat capacity of the ocean. There's a couple other features in the ocean that we think will elongate our timescales. So one of these is we can have subsurface anomalies in the ocean that kind of pop back up to the surface the next year. And then in the ocean, we have things like waves that take a long time to cross an ocean basin. And so similarly, we think that then we might be able to predict with how long that wave takes to cross the ocean when different conditions might appear. And then there are some processes in the ocean that are going to lead to persistence. One of these is the Bjerknes feedback, which is what forms El Nino. Another are cloud feedbacks. And really what we want to be able to do is to determine the relative importance of each of these different processes in different regions, because then we'll be able to say, hey, we think we can actually look into this more and maybe gain some predictability on these kind of monthly and longer timescales to tell you what the weather is going to look like into the future. I have a bunch of citations here. That's not at all because I expect anybody to go read these, but really the point is just that this is a huge body of work. So this is something people have been looking into for a very long time. They've done great work, but I think there's still more to look at. And I have a little bit of a schematic here on the right, which is just kind of illustrating these different processes that occur between the atmosphere and the ocean. So the atmosphere and the ocean exchange heat fluxes so that the atmosphere can warm the ocean or the ocean can warm the atmosphere. We have some winds. So wind stress from the atmosphere will force the ocean circulation, giving us things like ocean currents. And what's illustrated here as well is what's called the mixed layer depth. So that's kind of the upper layer of the ocean, and that's the part that gets directly heated by the atmosphere. So I'll come back to that in just a minute. Okay, so the way we thought about this is we want to divide out the role of different kinds of processes impacting sea surface temperature. And I'm going to categorize it into 3 groups. So one I'm going to call local ocean processes. These are things that are happening in kind of one particular part of the ocean. It doesn't really have to talk to places to the north and south of it. So you can think of it also maybe as kind of vertical ocean processes. So these are things like mixing, entrainment, which is where deeper, usually cooler waters would get moved up in the ocean, and then changes in the mixed layer depth. So changes in how deep that surface part of the ocean is. Then we have ocean dynamical processes. So these would be things where the ocean currents change or waves change or the winds drive some ocean circulation, and that leads to moving heat into a specific area or out of it. And then our third category we call thermodynamically coupled air-sea processes. So this is the Bjerknes feedback, which again is what gives us El Nino. And then another feedback that's called the wind evaporation sea surface temperature feedback. And so really what we want to do is divide out what is the role of each of these on the time scales of our anomalously warm and cold periods. And so kind of a classic way to do this is to compare 2 climate models. And you want a climate model that has all these processes and then a model where you get rid of some of them. So kind of the typical setup is we would have what's called a fully coupled model, and that's our most realistic model. It has all the processes I just talked about. And then we would compare it to what's called a slab ocean model. And in that slab ocean model, we take the ocean model that's realistic. We call that POP2. I don't know exactly why we have to use acronyms for all these things, but we call it POP2. And we just replace it with basically like it is a slab. It's kind of like a slab of concrete. All it does is warm up and cool down. It doesn't have ocean currents. It's not really very realistic. But then we can compare the two and see when we have this more realistic ocean, how do things change? So that tells us something about the role of the ocean circulation in our climate variability. But what's difficult when people do that is the slab ocean model doesn't really have an ocean. It just has kind of like a block that warms up and cools down. And so it doesn't have any of these local ocean processes, and it doesn't have any of these ocean dynamical processes either. So that means it's really hard to tell when the difference between the two models comes out, like, is that due to mixing or is that due to the large scale ocean circulation? I really can't tell you because it's all kind of mixed up. We just threw all the ocean out. So what we did is we decided to put something in the middle of these two. So from left to right, we're thinking from the simplest model to the most complex. So the one on the right side is our model that looks a lot like the real world and has a real ocean. What I'm illustrating here is the orange bar is our atmosphere model and the blue bar is our ocean model. And these communicate with each other. So these Q buoy here are heat fluxes that go between the ocean and the atmosphere. And then these taus are the wind stress. So the way that the atmosphere drives the ocean currents with a wind stress. So in our fully coupled model, we have the most realistic version of those, what we think is going on in the real world. What we do in what we call our mechanically decoupled model is we have a time mean wind stress, but we get rid of any variability. So we get rid of like storms or just like the fact that the winds maybe are stronger one year than another. So we kind of have a time mean ocean circulation, but we don't have this variability. And then again, the slab ocean model, there really isn't an ocean. It just warms up if the atmosphere warms it. It cools down when the atmosphere cools it. So what we want to do now is compare how sea surface temperatures change in these models and how long sea surface temperature warm and cold periods persist so that we can determine the role of different ocean processes on that sea surface temperature persistence. So I'm going to show you, I guess before I go to that, I want to say that we did this in the Community Earth System Model version 2. So this is one of the US climate models. And I'm going to show some comparisons. And so when I compare the mechanically decoupled model to the fully coupled model, that's going to give us the role of the wind stress driven dynamic ocean. When I compare the slab ocean model to the mechanically decoupled model, that's going to give us the role of local ocean processes. And then when I compare the slab ocean model to the fully coupled model, it's going to give us the sum of those two. Okay, so the first thing I want to show you is the mixed layer depth. We can think about this as just how deep that top layer of the ocean is. And in general, we think it's going to be the deepest in the winter. And so that's what we see. This is in our fully coupled model that's very realistic. In December, January, February, we have really deep mixed layers in the northern hemisphere where it's winter. In June, July, August, we have really deep mixed layers in the southern hemisphere where then it is winter in the southern hemisphere. What I'm showing now, don't let me skip ahead, is the difference between the fully coupled model and the mechanically decoupled. And this is now showing blues are shallower than the fully coupled model, reds are deeper. So mostly what I want you to notice here is these aren't like huge differences for the most part. And that's good. That means our experimental design is going pretty well. It doesn't work so well in the Southern Ocean because it turns out that storms are really important to the mean state in the Southern Ocean. But in general, we see that this is a little bit blue. So the mechanically decoupled model has slightly shallower mixed layer depths. Now let me show you the slab ocean model. So I told you the slab model, all it can do is warm up, cool down, warm up, cool down. That mixed layer depth doesn't change at all, even seasonally. And so you can see that these have huge differences from the fully coupled model. This is like 300% difference. So it's much less realistic, and that's part of why it's kind of hard to compare those two models to each other. Okay, now let's look at sea surface temperature, since that's what we're actually interested in. I'm just showing the mean first. And on the left, this is a data product. And then across the top, we have each of our models. So we have a fully coupled model, a mechanically decoupled, and then our slab model. And then I'm showing the differences below. So first, if we look at the fully coupled model compared to the mechanically decoupled, this is mostly blue. So the mechanically decoupled model is a little bit warmer, and that's because the mixed layer depth is shallower. And then I want to skip over to this one. That's the fully coupled minus the slab. This one, there's kind of a complicated pattern, and it's really hard to figure out exactly why. So we can't really learn a lot there, but they're not too different, which is useful for comparing them. Okay, now let's look at variance. So this is just how much the sea surface temperatures change from one time period to another. Again, we have a data product on the left, and then each of the three models. And I think the biggest thing you can notice, the mechanically decoupled model, our variance is really small in the tropical Pacific, and that's because when we do this, we remove El Nino Southern Oscillation. So that's the source of most of this variance in the real world and in the fully coupled model. Then when we look in the slab model, we get these kind of weird bullseyes. And this is something that I think I would say those don't look physical. This model's just unrealistic, but it actually looks a little bit like some things that we see in the data product. And so we think that these are created by that low cloud SST feedback. And this is something that we now have an active NOAA grant to investigate further to try to see if this is real. And if so, what can we learn about the real world to understand cloud feedbacks better? We can now look at the variance ratios. Anywhere this is red, the fully coupled model has more variance. So this is telling us that ocean dynamical processes enhance the variance. If I skip to the next one, notice this one's mostly blue. What this is telling us is that local ocean processes damp variance. They reduce the variance. And if I throw on the last one, now I'm comparing the fully coupled model and the slab, and it's blue in some places and red in others. So what that's saying is that in total, there's a tug of war between these local ocean processes and the ocean dynamical processes. And at any given location, one of them wins out. So then we can do the same thing, but now I'm showing
going to jump in here. So I want to make sure we have a little bit of time for questions. Since we started a little bit late. So one of the questions that I have for you is, so models are not the real climate. So how can we trust that your climate models tell us something about the real world?
That is a really good question. Actually, let me go back. I was going to skip to my conclusions, but I think something that can kind of give us some trust in these climate models is seeing if they look anything like data. So for instance, here, the plot on the left is coming from real data of the sea surface temperature. And this one's coming from our realistic climate model. And they're not perfectly in agreement. You know, you could find some places that these disagree, but I think it's doing really a pretty good job. Most of the patterns are here. And then I think the other thing to keep in mind is these climate models have been developed a lot. So there are many different versions of these climate models. There are lots of work digging into comparisons to the real world. And so this is something, you know, there's many teams working on this, and it takes a lot of teams to do it.
Yeah, yeah, modeling work's always challenging.
Yeah.
So I just wanted to put a shout out of my own in here. You mentioned the land sea breeze circulation earlier on. That's most of my research is in that. So I always love to hear a good land sea breeze discussion. So let's see, we still have a few minutes here. So let's see. Let's see if we have a question from the audience. So the Bjerknes feedback was mentioned in a few previous talks, but could you just briefly summarize what that is for everybody so they have an idea of what you're talking about?
Yeah, so the Bjerknes feedback is this feedback that kicks off El Nino. So what you get is when you have an anomalous wind in the tropical Pacific, then that alters the ocean circulation. So this is kind of a coupled atmosphere-ocean phenomena where you need to have, say, a weakening of the winds in the tropical Pacific, and then that's going to alter that mixed layer depth, and then that will give you anomalous sea surface temperatures, and it kicks off this whole process then that we know how it develops into an El Nino.
Thank you for that. You know, I had a very similar question because I've never really heard people describe it actually that way. So thank you. And let's give Kay a round of applause for his fantastic conversation. And of course, we'll do it virtually here, but thanks again. And
Thanks, everybody.
And then we'll just give a big thank you again to Jane and Kay for sharing their insights here in this stream. So as we've been hearing throughout this whole stream, the science behind weather and climate is extremely powerful. It's extremely thought-provoking. And with that, though, it's also vulnerable right now. The forecasting systems that we rely on are the result of decades of public investment. But right now, that investment is threatening to be pulled back. And because of this, our observational networks are at risk. Forecasts are already starting to suffer from the lack of weather balloon launches. And the future of climate research is uncertain. So it doesn't have to be this way. If you found this hour or these 38 hours of the stream to be so if you found this to be useful, please consider using the link that will come across the screen again at some point to reach out to your representatives and to spread the word about how the Weather and Climate Enterprise is helping everyday Americans and how we deserve good weather forecasts. And we also invite you to join others to this live stream, because after all, we're here to answer your questions. So please keep them coming in the chat, and stay tuned for some more great science ahead. You got me for another hour, and there'll be a few more great talks as that. But just sort of to give you a reminder of how long we've been at this and sort of what's to come. So you've been watching the Weather and Climate live stream, and we've been running now for 38 hours, and we will continue to share our science for 62 more of them. So there's lots of things to talk about. For those of you who might have just been tuning in, I am Ryan North, a PhD student at Texas A&M University, and as I mentioned, I'll be your host for just a few more talks. Thank you all for being here tonight, and once again for starting your Fridays with us. I know some of you may be on the West Coast, and where Kay was just in Alaska, it's not quite Friday yet, but it's almost Friday. We're almost there. And of course, thank you to all of the organizers who are keeping this train rolling and keeping everything on the track here. They've put a lot of effort in behind the scenes to keep this running. So we've seen a lot of great talks, and we have another one coming up right this. But just as a brief reminder before our next talk, all of our speakers are appearing in their personal capacities, and they're expressing their own views, which may not be those of the other participants that are here in this stream. So with that being said, I'd like to introduce our next speaker, which is Roger Marchand. Welcome to the stream.
Hello.
I will pass it off to you.
Well, thank you very much. Well, good evening. I'm delighted to be here to tell you a little bit about the research that I and my graduate students do. I'm a professor of atmospheric and climate science at the University of Washington, and much of the research I do is really focused on observing the properties of clouds and improving the representation of clouds in climate and cloud resolving models. And this includes developing remote sensing techniques to determine the property of clouds from satellites, airborne and ground-based instruments, as well as applying remote sensing and in situ data in model studies. And I'm a frequent participant in field experiments, including the ongoing cloud and precipitation experiment at Kennock in Tasmania. And I hope to say a little bit about that later in the talk. But let me start off by saying, why should one be interested in clouds? And if you've been watching this live stream, I think for any significant length of time, you already know the answer. For among other reasons, clouds play a critical role in the Earth's radiation budget. As many, and I hope as all of you know, the Earth's climate is largely controlled by the balance of radiant energy coming from the sun which is largely in the form of visible light and often referred to as shortwave radiation by scientists, against the emission of infrared or thermal longwave radiation back to space. And clouds do both reflect sunlight into space, but also absorb and re-emit thermal longwave radiation back to the surface. It's been theorized that clouds will change in a variety of different ways, which are important to this radiation budget. And today, I'm only going to talk about a couple of those. The first of which is that high altitude clouds are expected to become higher in altitude at all latitudes, not just in the tropics as suggested by the picture behind here. And also that low clouds, especially at mid to high latitudes, might become brighter because they have more liquid water in them. So let me jump in and say, I'm going to address this first question. Are high altitude clouds getting higher from an observational perspective? And in particular, I'm going to use observations from two NASA satellites. The first is called MISR, or the Multi-Angle Imaging Spectroradiometer, and the second is called CloudSat, which is a cloud radar that was put into space in 2006. Now, what makes MISR interesting, for at least for this question, is it contains not just one, but 9 different cameras that observe the Earth from 9 different view angles as the satellite is flying along its orbital track. So as the middle panel here demonstrates, there's a parallax that occurs. So you can imagine as the satellite's flying along and it looks at one of its forward cameras, it sees a cloud, and that cloud appears to be at one location on the Earth or on the surface here. But then at some later time, looking with a different camera, that same cloud appears to be in a different point. And it takes a little bit of time for these two views to happen. So in practice, what happens is you see motion of the cloud due to both the advection of the cloud moving with the wind, and also this just change in direction with viewing angle. In fact, for high clouds, it's that first component, the parallax, that's the largest. And I'm hoping that this animation is playing for you at home. I don't know quite how well the internet works, but I hope you can see that some of the clouds in this image appear to be moving quite a bit more than other clouds. And that's not because the time these clouds are moving faster, it's because they're higher. And as we look through these different view angles, we're seeing this parallax effect. And so we can calculate the height of the clouds based on this geometry. And here's what the height of the clouds are, where red here represents pretty high clouds, and green and blue shades are clouds that are lower in the atmosphere. And this is really useful for a lot of reasons, one of which is it means that the height calculation is really not sensitive to the calibration of the satellite or the amount of radiation. So unlike, say, a geostationary satellite that typically uses an infrared sensor to measure how much thermal energy is coming up and then has to infer where from that temperature where the cloud might be, and any miscalibration, any mismeasurement of that temperature or misestimate of how much of that radiation is absorbed in the atmosphere will cause an error in the height. This is a very direct and simple approach to get to the height, and it's going to be stable over a very long period of time. And so that makes it really useful for doing things like looking at trends in clouds. So, do MISR measurements show that cloud tops are going up? The short answer is yes, but how much depends a lot on where you look. So in the left panel here, the black line shows a time series of monthly mean cloud top heights observed by MISR over the Southern Ocean between about 40 and 60 south. And as you can see, there's a lot of up and down on this line. There's a lot of internal variability, but the line is clearly sloping upward. And so we can fit a line to that, and we come up with an estimate of a roughly, oh, here's the cursor, of about just over 5 meters per year. So part of what makes this climate trend hard to see is it's actually quite small, and that's why you need this really stable measurement to help see it. And that internal variability still leaves a lot of uncertainty in how well you can fit a line, whether the line's really going like this or the line's really going up like this. And that's what these error bars here represent, the uncertainty in fitting a slope to that black line. Now, the orange and blue lines here are showing results from two climate models, the IPSL CM6A low-res model and the NCAR CSM2 model in blue. And the fact that the blue line is below the black line does in fact mean that the clouds in the CSM2 model are biased a bit low. They're a little too close to the surface. But nonetheless, you can see, I think, that the trend, the increase in height in both models is quite similar and matches the observations fairly well. And again, the panel on the right is trying to tell us much the same information. So what I've plotted in these solid lines here, the orange and the blue for each model, is what you would estimate for the trend in cloud height increase if the model were the real world. I know that might be a little hard to understand, so let me demonstrate with an illustration. So suppose these dots represent that model output, where each dot represents one of the measurements of cloud top height over time. So if the only data I had was the first 10 years of the data, and I go and I fit a line to that, I can expect to get a fairly shallow change, and that slope will be highly uncertain because there aren't a lot of data points. But as I take a longer and longer time window, I'm going to get somewhat different slopes, and I'm going to get increasingly good fits of that line to the data. And that's ultimately what these shadings represent. So if this IPSL model were what I actually observed from MISR, then I would start off with very little slope, and it would be noisy at first, and then I would get more confidence over time. And the same is true with the blue model. And at least for this region, the two models agree that the rate of increase of clouds, or they project the rate of increase in clouds, should be about 4 meters per year. But based on the variability in the system, it suggests that I might, with observations, just start now, after about 20 years, to be able to actually pick this out and tell that there's an increase in cloud height that's distinctly different from zero, that there is an increase going on. And indeed, the observations agree well for this region. That's less true in other regions, and in particular, when I look at the tropics, I see that there is a slight increase in this region, but it's not very strong, and the uncertainty bars do include zero. So it could be, at least there's a roughly 5% chance in this case, that the observed slope could be an accident, and there's not just a result of internal variability, I should say, not an accident. And there could be, but there also could be a change that's about 5 meters per second, which is on the sort of agrees reasonably well with the blue line, but would be on the low side for the orange. So the bottom line here is there is a change, right? We are observing a change, but it's not very clear, in part just because the variability is larger. You'll note here that the scale on this change is, say, 0 to 20, where it was only 0 to 8. So there's more variability in the height of clouds in the tropics, and that makes it a bit harder to be certain whether the changes we're seeing over the last 20 years represent a true climate trend versus just variability, internal variability in the system. But that doesn't mean that the data are somehow inconsistent with the observations. Again, if I just take that panel to the left and I remove the mean and put them on top of each other, you'd be hard pressed to know if I hadn't already told you which was the observation and which is the model. So it's really, as we move forward, this next sort of 5 to 10 years is really going to be more telling in terms of being able to see actual changes in the tropics and to begin to see changes between these two models, or at least these two versions of reality. I should perhaps comment, however, that a lot of the difference between the orange and the blue model here is that the IPSL model really is predicting more surface warming in response. And that's part of what drives this larger change in cloud top height. In fact, if we think about monitoring the changes as a function of temperature, which is, we see that there's a consistent pattern between the models. So on this plot, what I'm showing is the feedback strength. This is the watts per meter squared. That's the amount of radiant energy caused by the change in high clouds per degree K of surface warming. And interestingly, when you put a bunch of models, which are these various symbols here, and you plot the strength of their feedback versus the amount of opaque high cloud in those models, you see that there's a strong relationship. So part of what happens is part of the uncertainty we see in models is not because they're predicting strong differences in the rate at which clouds are going up per degree of surface warming. It's that some models have a lot more high cloud or have significantly more high cloud in them than other models. And all of the models in some sense here are at least slightly over predicting the amount of high cloud. And so one could say, look at this relationship and say, based on this curve, if we say this is a true relationship for the strength of this feedback for a certain amount of high cloud, and this is where the amount of high cloud is for the real world, this would make a good estimate for the actual energetic impact of this change in high cloud. Oops. And in fact, there was a fairly recent publication by Sherwood et al., where the community really came together and tried to make estimates for a lot of the important feedbacks, including this high cloud altitude feedback. And the best estimate they came to, which was blending multiple lines of evidence, suggested a result of about 0.2 watts per meter squared per degree Kelvin, which is exactly where this new satellite estimate I'm showing you also suggests the real value should be. And this argues ultimately that the uncertainty bounds suggested by Sherwood are perhaps too big, and that if we use this observational data, we have a better idea of how much the strength of this high cloud feedback should be, and we can use this in our future assessments for how much warming there will be. So we're extrapolating from models, from a combination of models and observations, to get a clearer picture of how fast clouds are going up and what the radiative impact is. All right. Well, the other sensor, going back to the other sensor I mentioned, is CloudSat. And CloudSat's a radar, but unlike some of the radars you're used to seeing probably from the Weather Channel or other places, CloudSat isn't scanning, isn't sitting at a point on the ground and scanning. It's a satellite in orbit that only looks directly down. And as the satellite flies along its ground track, it basically makes a two-dimensional cross-section or curtain of the measured reflectivity. So here's an example I took from this nice paper by Lou and colleagues, where this red line shows the path that CloudSat took as it flew over a hurricane. I think this was Hurricane Bill. And below is the reflectivity that it sees, right? So this is the eye of the hurricane, and as it's flying along, the amount of microwave energy being reflected back to the radar is a measure of how big and how much how big the particles are and how many particles there are in this cloud. So I can take that data, this range resolved data, and make some simple data reduction to learn about the height of clouds and precipitating systems. So on the left here, for example, I have a small snippet of CloudSat data as it was flying along, and the colors represent different reflectivities, different amounts of strength of radar power, of power being scattered back to the radar. And I can simply count how often a certain value of reflectivity or a range of reflectivities, say reflectivities between -10 and 0 dBz as a reference, occurs over at some altitude range. And here that's been divided into 1 kilometer intervals. And I can do this same thing over many, many snippets of data, and in fact, over the entire world if I want, and over different time periods. And if I do something like that, what I tend to find is I see shapes. This is for 60 north to 60 south in August of 2020 and August of 2007. So in August of 2007, the average for that month over much of the world, you get this pattern, and you see this sort of characteristic, what I call D shape, where high clouds, the highest, thinnest clouds tend to have relatively low reflectivities. This tends to increase a bit. Then you have some precipitation, and then you have a lot of values for different low clouds having different levels of reflectivity. What's interesting in some sense is I can take the difference between this data from 2007 and 2020. And when I do, I see this pattern here in the right panel, where you have these red-orange colors, which mean an increase, and some below that, some blue colors here. So this is basically, but you also see this dark blue stripe or feature that I've highlighted in red. So unlike the MISR data, the radar data does have some issues related to sensitivity and potentially to calibration that we need to deal with. And in particular, as this radar aged over the years, it put out slightly less power, and that made it less and less able to see the smallest, less reflective objects. So you can see, if you look here, you can see some amount of detections, and you don't see those in 2020. And that's not because these thin clouds disappeared, it's because the radar couldn't really detect them anymore. But I can make a correction for that, and that's what I've done here in the bottom panel, is I can't improve the sensitivity of the data from 2020, but I can go back and I can add noise to the system, artificial noise, that makes the data comparable in 2007 from 2020 and effectively removes the effect of this sensitivity. But there's still the potential for there to be some calibration changes, I should say. So it's possible, for example, that this shape on the right could be shifted slightly to the right or slightly to the left, because the inherent calibration of the radar, how much power I get back, equals such and such amount of, or a certain signal level I get back represents a certain amount of power. And the final calibration isn't finished, and that's an ongoing project, and hopefully one that I will finish in the near future. But of course, that sort of gets us a bit to the issue of whether there will be funding to continue to work on these data. But in any event, while these data are preliminary, I'm reasonably confident at this point that there, in fact, are not major calibration problems with these data. And so what you're seeing here is that these orange and red colors mean that clouds have actually shifted up higher in altitude, consistent with the MISR data. But also we see some shift outward here, suggesting that that the sort of heaviest, the largest reflectivities that are seen by the radar are becoming more common. And that too is in some sense an expected result of warming, where there's going to be heavier rains with larger drops. And also there's some indication here that there's a reduction in low clouds across the spectrum, especially for the thin ones. All right, well, that brings me to this question of what's going on with low clouds. And really, climate models participating in the most recent coupled model intercomparison project, CMIP6, simulate strong latitudinal gradients in the response of low clouds to increases in greenhouse gases over the southern hemisphere in particular. That's this region over here, where the orange curve here is the CMIP6 models, and the blue is the somewhat older CMIP5 models. So you can see there's really big changes here. These are quite important energetically. We're talking regionally sort of 1 watt per degree Kelvin per degree of warming, surface warming. And it's changed a lot between the two models, right? And you see this diapole where you sort of have a negative response and then a positive response. the response is this dipole is due in part because there's a sort of decrease in cloud amount up in this region here around 40 south, while there's a significant negative change, a negative feedback, meaning clouds becoming brighter, so more energy going back, being reflected back to space at higher altitudes. Now, there's a variety of mechanisms that might cause this, and at least a primary idea is that there's going to be a shift that's due to changes in the phase of mixed phase clouds, or related to the change of phase of mixed phase clouds. So a lot of clouds at these higher latitudes are actually composed of supercooled liquid droplets with some amount of ice in them. And as the climate warms, is sort of in this picture here. So this is the sort of 0 degree line today. So clouds with lots of very cold water. So water that's actually below freezing, but it hasn't quite turned to ice yet, and a mixture of ice. And as it gets warmer, the ice goes away. And this actually reduces the precipitation efficiency. And so you end up with clouds with more small droplets and more water, and they actually can last longer. So you can get an increase in both the brightness of clouds and the amount of clouds, with both of which result in a negative feedback. At least that's the idea. But of course, there are some other mechanisms. This phase change mechanism I was just mentioning is partly here, but there's some other mechanisms that scientists have proposed that could also affect these clouds. So what do we see when we look at satellite data? So here's a result that a student of mine just put together recently, Kindra Buglione, where she was looking at the change in cloud optical depth, which is in some sense a measure of how much light will be reflected back into space, with temperature based on geostationary satellite data, in this case from the Himawari satellite that observes the area, the latitude range that includes the area south of Australia. And I'm looking there in part because I've been there have been a number of field experiments going on, and so I have some ground-based, ship-based, and aircraft-based data that I can use to evaluate whether I think the satellite is doing a good job, but also to investigate why that happens, because these kind of field experiments give me much more detailed knowledge of what's going on, especially in terms of what's going on below the cloud, which is hard to tell from satellite visible imagers. And in general, higher resolution and just from the fact that you're closer to the clouds, as well as in some cases flying in the clouds and directly measuring what's going on, is a real plus. So there's a number of different experiments I'm pulling data from, including this Cape K experiment, which is ongoing, and Coast K, which just finished, which are taking place up here near this northern tip of the island of Tasmania.
I'm actually going to stop you there. And we're going to take some time for questions.
Oh, I've gone too slow. Okay, well, go ahead.
So we have a lot of questions here from the audience, and sort of one of them that has sort of come up in multiple forms is, how do you deal with the uncertainty? What does that mean for your results or your main takeaway?
Well, I guess I'm looking at uncertainty in different ways. I mean, I would you like me to go back to the, I guess, is that question in the context of the first result that I was showing here?
I think it's more of a general, so how do we deal with uncertainty in scientific research?
Well, I mean, I think you have to, I mean, that's in some sense where I spend an awful lot of my time working on. So in this case, or this example, right, I have this black line, which is an observation that I'm taking, but that observation has a lot of variability in it, right? And that a lot of that variability is just because the weather from one month to the next can be quite a bit different. So you could have clouds in one month, in this case, which are on average, a couple hundred meters higher than they are the next month, because there may have been more tropical convection in one region or another that influences this, right? And And so when you fit the line, you can do, in this case, what's called a bootstrap reanalysis, where you say, I'm going to take the variability around the mean and resample it to represent a different version of what that internal variability could have looked like. And that's ultimately what drives these uncertainty bars, right? Another way you can think about this uncertainty is the reason I'm looking at two data sets here. The reason I was looking at this MISR data and the CloudSat data is I'm looking for independent pieces of information, independent observations, which confirm some facet of the system, right? And so by having this kind of satellite data where I'm using this imaging, multi-angle imaging technique and a radar, which are entirely different ways of looking at the data, I can gain confidence in terms of what I'm observing.
I think it's a great answer. That you see that come up a lot in talks we've seen and a lot of research you read, that we really try to deal with uncertainty by having lots of independent data sources that sort of confirm what we're seeing. So in the interest of time, I am gonna move on to our next bit of spiel and our next talk. Well, my spiel and then our next talk, but you feel free to engage some of the questions in the chat if you'd like. So let's give Raj a round of applause for his great talk, and thank you for joining us here tonight.
Thank you.
So before we continue on to our next round of talks, I have a few remarks as to why we're here on your screens. So if you're just joining us, welcome. And I'm just going to sort of read through my talking points here that I've written. So the Weather and Climate community has set out to host this 100-hour continuous live stream to help save our forecast here in the United States. We are currently halfway through our 38th continuous hour, and we're going to continue for the next 61 and a half hours. So for anyone just joining us, hello and welcome. My name is Ryan North. I'm a PhD student at Texas A&M University, and I will be your host for the next half hour. Earlier, if you were here, I made a really cringy SpongeBob reference. So in that spirit, let's pretend that I'm ringing the cowbell and hour 38, hour 38. So we're moving along here. And anyway, once again, since I strayed off of topic once again, I seem to be good at that. Let's get back to what the case at hand here. So we've had a lot of great talks today, a lot of great talks in this session, and we have another great talk coming up right after this. So just a brief reminder that our speakers are presenting here in their personal capacities. They're expressing their own views, and that those views may be different from other participants, and that their views do not necessarily represent their affiliations or their funding agencies. However, we all have one unified purpose, and that is that Americans deserve accurate weather forecasts, and that the U.S. has led the world in weather and climate prediction, and we're here tonight advocating for this to continue. So the U.S. was the first to develop computerized weather forecasts, as well as we were the first to develop computer models that mapped the climate impacts of carbon pollution. We have unparalleled observation networks, and these have many different instruments. We have surface observing stations, we have buoys, we have floats, we have airplanes, and we have satellites. So we cover lots of different things with our observation networks. And this excellence has been due to investments from you, the people. And federal funding is critical to science, and especially all the talks you're seeing here. So we're asking you today to reach out to representatives and advocate for science. So the link to do that is scrolling across the bottom of your screen. We greatly appreciate it. And with that, that is the end of my time hosting the live stream. It's been an honor to be here with all of you this evening. And I'd like to thank you all for being here and helping us get our message out there. And then, of course, thank everybody who's in charge of operating the stream and everybody in the background, making sure this runs smoothly for the next many hours that this has to go, since we're now into hour 39. So with that, I'm going to pass the baton to your next host, which is Paul Stanton, who is an associate professor at Indiana University, Bloomington. And take it away.
Thanks, Ryan, and thanks for doing this early in the morning. Yeah, we got about 61 hours left. We've had some great talks. I tuned in just in time to catch Dr. Walczak's talk. And yeah, I'm an atmospheric scientist myself. I study large-scale wind patterns and climate change. and I enjoyed hearing about the ocean side today. We've had a lot of great speakers so far, and our next speaker is no exception. We've got Dr. Dave Gutzler lined up, and there you are, Dave. How are you this morning?
Hanging in there.
Good. Yeah, it's early, isn't it? My eyes are feeling it. Dr. Dave Gutzler is a professor emeritus from University of New Mexico, and he'll be talking today on seasonal forecasts of climate and stream flow in snow-fed rivers in just a moment. And I just want to remind our late night or early morning visitors, or wherever you are. We had one who was going to dinner, and those who are hopping on, thanks for joining us. But I want to remind you about our purpose tonight. Just that, Americans deserve good weather and climate forecasts. And U.S. scientists have historically been world leaders in weather and climate prediction. We developed the first computerized weather forecast, the first computer models of climate impacts of carbon pollution, and have created an unparalleled network of observations like NexRad radar and the balloon networks that have been a prototype for the world. And this excellence has been funded publicly, and now public funding cuts have been affecting it. Weather stations have been getting short-staffed. Some of the balloons haven't been able to be launched. We had a shrinking and shuttering of climate labs. So I hope that you'll help us to save our forecasts. Remember, there's a 5 calls app link available in the video description, which is really a pretty great app. I've started using it myself. It's been a really good way to help me get my voice out. I hope you'll do the same. So with that reminder, we'll go ahead and get ready for Dave Gutzler's talk. They are great. Dave, and I will turn the time over to you now.
Okay. I hope my audio is all right.
Loud and clear.
Very good. I am very pleased to be here in the middle of the night. I'm on Mountain Time, and I am a meteorologist and climate scientist by training, but I want to spend a few minutes here talking about a different sort of interdisciplinary forecast of huge interest to folks in the arid West. And that is the seasonal forecast problem for Streamflow, which involves both people and lots of measurements that include the weather and climate community, but extend beyond that to consider hydrology. And in particular, we'll be talking about forecasting flow in big Western rivers that are fed primarily by snowmelt runoff. I'll be focusing on the Rio Grande, which flows through central New Mexico a couple of miles from where I'm sitting. But a lot of the major points I have to make, I'm sure are quite applicable to many other major Western snow-fed rivers. So we'll be talking about the interaction between the seasonal forecast problem and climate change, because climate change is diminishing the snowpack that feeds these rivers. And I will try to emphasize the concept of of reliability of our water supply from these rivers, which is diminishing due to climate change and the need to keep up funding for people and for monitoring the rivers and the data we need to make these forecasts. So what's here on the right is a photo I took on Monday of the Rio Grande, just north of Albuquerque. And if that looks like a river that's running at low flows, you are correct. And that's a big problem for us, because this is, as we'll see in just a moment, is supposed to be the high flow time of year. And so our task in this talk is to think about the forecast problem every winter and early spring of trying to project how much water is going to be flowing down this river for the rest of the year during the growing season. Okay. For a river like this, not all precipitation is created equal. It's obviously fed by precipitation, but the gold standard for supplying our rivers is snow. So if we wanted to forecast the flow past that red square on the cartoon, and we think about the supply of snowpack way up in the upper left to this river, snow has a couple of features that are just glorious for water supply and making predictions. The snow accumulates all winter. We don't need to build infrastructure or reservoir to store it. It just sits up on a mountainside and then melts and flows into the river at a predictable time of year in the spring. And that process is what's diminishing in the warming climate.
You know, Dave, you mentioned a red square in the cartoon. I don't see a cartoon. I'm still seeing slide 1 of 9. I'm wondering if...
All right. How do I get the slides to advance? Thank you for that. Is that working better?
I still see slide 1 of 9, the intro slide with the less reliable water supply across the west highlighted.
Okay. Where did my I am worried that the PowerPoint that I just converted to a PDF didn't process that properly.
Oh, hey, I see the red square in the cartoon now.
Oh, okay. And now I wish I know what I did to make that work.
I see.
TV. Got it.
Yep.
Got it. I will need to give the prompts to the folks backstage. Okay, so there's the cartoon. Sorry about that. We'll see if we can make this better. In addition to water supplying the river from snowpack, we have large-scale rain, which is the kind of rain that falls as part of a big weather system, often associated with fronts. That falls over a wide area, and from a seasonal forecast perspective, that's the kind of precipitation we often have some seasonal predictability associated with interannual shifts in stationary waves that help guide storm tracks. And then especially here in the interior west, we often get rain in the summer from convective thunderstorms, which are short-lived, local, intense, and those are hard to make much sense of on a seasonal prediction basis. We won't go into groundwater much in this talk, but convective precipitation is not so efficient for having flow percolate into the ground either because it's so flashy and intense. Okay, so it's that snowpack that really helps us out in terms of supplying these rivers with water. Next slide. Great. Okay, so we're going to be talking mostly in this presentation about the upper Rio Grande. Upper meaning in Colorado and New Mexico. So there in the upper left is a map of the Rio Grande watershed. The headwaters are up in the north, north of me anyway, in southern Colorado. The western edge of that watershed, the jaggedy line there, that's the Continental Divide. The Rio Grande forms up in southern Colorado, then flows south, bisecting the state of New Mexico. There are a couple of locations that I'm going to mention here in a few minutes. There's a big gauge at a place that we mispronounce Del Norte. There's a big gauge farther south, which is important for water management in New Mexico at a place called Ottawa, which is right down the hill from Los Alamos National Lab. The river flows through Albuquerque. There's a couple of big storage reservoirs farther south called Elephant Butte and Caballo, and then the Rio Grande ends up in El Paso, Texas, beyond which it forms the international boundary between the American state of Texas and the Mexican state of Chihuahua. And so there's a couple of old plots down at the bottom there, and I want to make 2 points. For the annual time series, The point here is just that on an interannual basis, the flow in the Rio Grande is incredibly variable. We have really wet years and really dry years. And historically, that's always been the case. There's a lot of decadal variability in this river, and variability from year to year that historically has been associated with changes in snow. And so on the lower right, you see the average flow month by month, long-term average in this river. And there's a big obvious peak in month 5, that's the month of May. That's when the snow melts. So in this river, a huge fraction of the stream flow naturally flows in association with snowmelt runoff in late spring into the early summer. That gets mitigated downstream by human management in reservoirs, and a lot of the water gets taken out of the river for beneficial use. That's how we grow crops along the Rio Grande. But first, I want to show you how we have made seasonal predictions for this river. Seasonal meaning in the winter, how much water is going to flow down the river for the rest of the year. Looking at the upper San Juan Snowtell site, which is actually just across the Continental Divide out of the Rio Grande watershed at the headwaters of the San Juan River, which is a tributary of the Colorado. Next slide, please. So this sort of scatter plot is a forecaster's dream, because it shows each diamond, each triangle there represents 1 year, and the x-axis is the amount of snow that is measured at one site above the headwaters of the San Juan River. And then the y-axis for that year, for each point, is the amount of water flowing past a gauge not too far downriver out of the headwaters in the San Juan River. And so all you have to do in this plot to make an awfully skillful forecast of snowmelt runoff is to measure the snow at one place on one day, which happens to be April 1st. And so this is how we have predicted stream flow over many years. There are operational stream flow forecasts made both by NOAA and NRCS, the Natural Resources Conservation Service. However, snow is diminishing, as I'll show you in a moment. And that has two effects. We think it's going to diminish the flow in the river altogether. But for this talk, I want to emphasize the fact that as the snowpack diminishes, this beautiful linear relationship on this plot between April 1st snowpack and total flow down the river starts to diminish, because those other sources of precipitation become relatively more important relative to snowpack when the amount of snow diminishes. All right, next slide. So here's what, now we're going to go back over the Continental Divide. We're into the headwaters of the upper Rio Grande, into Climate Division 5 in the state of Colorado, which is the Rio Grande headwaters. And here's what's been happening to the climate over the past half century or so. On the top, we see temperature. You may need, do we see the text on the right? Yes. No, back, sorry. Can we go back? There we go. You ought to be able to see that it's getting warmer. Fast and very significantly. So the temperature in this basin, in the headwaters basin of the Rio Grande, has increased in these glorious non-metric units by about 3 degrees Fahrenheit since the early 70s. There hasn't been much change in precip, but not surprisingly, when the temperature goes up like that, the snowpack goes down, and down by a lot. So snowpack varies tremendously from year to year. That's a very jaggedy SWE line. SWE stands for snow water equivalent. But that trend line fit to the data represents a decrease of 25% in average snowpack since the mid-20th century. And this has profound consequences for our rivers and the entire hydrology of the Mountain West. Next slide. I won't emphasize it too much in this talk, but one of the consequences of those kinds of trends for long-term projections of stream flow are that the snowmelt runoff peak goes down dramatically, as shown by those projections on the left, and newer projections shown on the right suggest that we'll have very significant diminution of total flow in the Rio Grande over the course of the next 50 years. So even if precip in total doesn't change all that much, just the diminution of snowpack is responsible for projected flows that diminish quite a bit. Now, we haven't seen in a super significant way these projected decreases yet, simply because the natural variability of the flows are so big that it's very difficult to pick out a linear trend in real time based on just a decade or two of diminished flow, which we've had over the past couple of decades this century. All right. Next slide. So now let's talk about what happens when the snowpack decreases in terms of trying to predict how much flow is going to come down the river this year. That plot on the top shows that this is not a new challenge. So just to the east of the Rio Grande, the next river drainage over is the Pecos River, which also has its headwaters in northern New Mexico and also flows south down to Texas. And those plots show the time evolution of NRCS forecasts of stream flow. We like to think we're getting smarter with time and that our prediction skill goes up as we learn more about the system and have more practice making forecasts. But over the course of the late 20th century, streamflow forecast skill in the Pecos River went down very considerably. And we think we know why. It's because the primary predictor for these forecasts, namely snowpack, has been decreasing so much. So those green bars on the bottom plot represent the fraction of the variance, interannual variance of streamflow now back in the upper Rio Grande. And the green bars represent the fraction of runoff variance that we can explain with, once again, just 1st April snowpack. And we start with 80% at the left, and steadily every bar is a 30-year period, but increasing in time by 5 years. The skill that we get just from snowpack goes down, down, down. And what's replacing that in terms of just a linear representation of streamflow variance is the temperature and the precipitation in the runoff season itself in the springtime. Those are the blue and the yellow bars. So this presents us with a forecast problem. What we would like to do is use what skill we have in predicting temperature and precipitation in the spring to try to replace the forecast skill we're losing as the snowpack diminishes. So next slide. I've just set up the problem. There are smart people working on it, but we need continued support to make this work. I'll just show you what's happening this year, which is bad snow. So on the left, there's a time series of the snow as measured in the upper Rio Grande in the headwaters basin, and it was way below average all winter long. So that sets us up for a bad snowpack year, which is now essentially over. In the upper right, having just said that what we would like to do is incorporate a streamflow, a prediction of temperature and precip from the spring season to add to our prediction of streamflow. That's the NOAA CPC Climate Prediction Center outlook that was issued in late March for temperature and precipitation across the US. And it's just adding more bad news to the Streamflow prediction because we're looking at above average temperature and below average precipitation. It's a triple whammy presenting a very grim outlook for Rio Grande Streamflow in 2025, which leads us back to the photo of the Rio Grande I started this presentation with. It's looking bad. Now, let me add that what we have not done as a community is integrate the climate seasonal forecast shown in the upper right, integrated those integrally into the Streamflow forecasts. Those Streamflow forecasts are still using generally historical data. And so a big research challenge from my perspective is to put all these products together and come up with what the kind of 21st century Streamflow forecasts that we'll need moving forward. Okay, one more slide. Where do we go from here? To make better seasonal predictions of short-term Streamflow, as I've repeated now a couple of times, we're going to have to do a better job integrating climate conditions from the snow melt period into our Streamflow forecasts. And so to do that, we obviously need support from the feds, in addition to a continuation of all the monitoring and measurement that went into these forecasts. And that includes not just climate data, but all the hydrologic and land surface data that currently goes into a Streamflow forecast, including snowmelt, snowpack, vegetation conditions, soil moisture. So we've got a big integration, interdisciplinary problem here that's of crucial importance to people in the West. We kind of have the tools sitting around to do it, and we need continued support to make progress on this on this really important forecast problem. I won't go into how we're, the long-term projections that we mentioned briefly and leave it there. And with my profound thanks for people staying up very late to listen to our little story about Streamflow in snow-fed rivers in the West. Thanks very much.
Thank you, Dave. That was excellent. We have several questions from the chat. Greg Linder is asking about something, mentioning support from the feds. He's mentioning what the overlap is between NOAA National Weather Service monitoring and the USDA and SNOTEL. And he asked if you could give a little overview of SNOTEL also, because this is something that your research relies on, a lot of people are using.
Yeah, the NOAA and the SNOTEL, NOAA and NRCS and USGS, which monitors Streamflow, are all in separate federal agencies. So NRCS is part of the U.S. Department of Agriculture. USGS, which maintains the stream gauge network, is part of Interior. And then NOAA is in Commerce. So people talk to each other, but they really maintain separate networks. And so in terms of overlap, people are talk to each other. There's lots of information exchange, but they're really maintained by not just separate agencies, but separate departments at the executive level. And so there's a real integration challenge there as well. And just as a shout out, I should say that my own research and that of my students has been supported by all those agencies. So they're all interested in this problem. But there is a challenge going forward to keep this support going.
Yeah. And what about the upper, another question from Greg, what about the upper basin, Colorado River Basin, in addition to the Rio Grande River Basin? Things are looking, on that map, things are looking pretty rough for the Rio Grande Basin.
Right. So this year we had, not surprisingly, there's often a north-south gradient in snowpack just due to north-south shifts in the winter storm track. And so this year, the southern part of Colorado and southward into New Mexico had horrible snowpack by historical standards. The headwaters of the Colorado River are in northern Colorado near Rocky Mountain National Park. That was considerably better than we got farther south, and better still were parts of California where the Sierra Nevada got actually pretty good snowpack by the end of the season. So there are some, it's not a matter of the whole West drying out all at once. There are north-south shifts in particular that are real common, often associated with the ENSO cycle, which shifts the winter storm track north and south.
Got you. Thank you so much. Thanks again for your presentation and for your time. Appreciate it.
My pleasure entirely. Thanks a lot.
Take care. Our next speaker will be on is ready to go. Will be on just a minute. But I noticed that we had people signing on from Oceania. We had some from Australia. We had a couple from Europe, including one from Germany. So we have people from all over the world tuning in. And if you are tuning in, just as a reminder, so I'm Paul Staten. I'm your host for this segment of the night, or in the evening if you're out west, and just reminding you about the mission. We have all kinds of different topics that our speakers are doing research on, but our mission tonight, our purpose is to help save our forecasts. Americans deserve good weather forecasts, and historically, the United States has been ahead on developing like computerized weather models and the networks that we use to observe and forecast weather and climate. And these things are publicly funded, and they've benefited everybody, both in the country and throughout the world. Right? As I've gone to international conferences, the United States system has been modeled by others and useful for everybody. But these things are federally funded, and they're under threat. Cutting to federal funding has caused weather stations to go short-staffed. Some of the climate labs, including my own, have been shrinking or shuttered. And so we're encouraging people to speak out. Again, there's a 5 calls link available in our video description that people can check out and call. And so that's the mission that we're going for with this 100-hour stream. We have 60 and a half hours left. This mission's important. So thanks again to Dave Gutzler for his talk, for joining us. And up next, we've got Sara Murphy, a postdoc scholar from UCLA. And Sara will be exploring the formation of accretion products in the atmosphere. And Sara, I see your slides up there. Good to see you this morning. How are you?
Good to see you too. I'm pretty good. It's only 12:30 here on the West Coast, so I'm ready to go.
All right. It's a little bit of a late night for you. It was an early wake up for me. So look forward to it. I'll let you let you get started here in a minute, and I'll be watching, interacting with chat, and ready to ask you some questions as we wrap up in just over 20 minutes.
Okay, sounds great. Yeah, thanks for introducing me. Like Paul said, I am a postdoc at UCLA. A lot of the work I'm going to be showing today is in part funded by an NSF Atmospheric and Geospace Sciences postdoc fellowship, which is still around for now. But of course, the cuts are making all of us nervous. So if you like anything you hear today, be sure to call your reps and tell them not to cut the NSF as much as possible. I'm going to be talking about the formation of accretion products in the atmosphere. I promise I'll explain what that means. But the first thing you see on this slide is a picture that I took from the top of Caltech in Pasadena, which is where I did my PhD, right after a fire in the San Bernardino, or in the nearby mountains, had started. And you could see that fire is leading to pretty drastic changes in atmospheric composition. And so in the study of atmospheric chemistry, we seek to understand how fires and other drastic changes will lead to changes in atmospheric composition. But why do we study atmospheric composition at all? So there are two major reasons that I'm going to talk about right now. One of them is air pollution. When we think about air pollution, we usually think about two major metrics: particulate matter. So think smog. These are like small suspended liquid or solid particles in the air, and ozone, which is beneficial to us when it's in the stratosphere. Protects us from harmful UV radiation, but in the troposphere is actually a pollutant and can be harmful to human health. In fact, both of these air pollutants are harmful to human health and lead to respiratory and cardiovascular diseases. I'm showing here a plot of deaths attributable to PM 2.5, which is a type of particulate matter, in millions. And we can see that these deaths have been remaining steady or increasing over the years, which really motivates us to learn more about how these pollutants are formed and where they're coming from. Atmospheric composition also has a large effect on climate. We all know about how greenhouse gases are leading to a general warming of the planet. And I'm showing here a sort of outdated, it's WHO estimated mortality attributable to climate change by the year 2000. So it's a little outdated, but we can see that these numbers are significant, and also that they tend to be concentrated in the global south, which means there's also a social justice component to understanding how atmospheric composition affects climate as well. But what are actually the things that drive these atmospheric processes? When we think about atmospheric composition, most people usually think about nitrogen and oxygen. These are the two major constituents of the atmosphere, right? But the things that are actually driving the processes that lead to these changes in air pollution and climate are actually the trace constituents of the atmosphere, things that make up less than 1% of atmospheric composition. And one class of these trace constituents that play a really big role are non-methane hydrocarbons. For the non-chemists in the audience, a hydrocarbon is what it sounds like. It's a carbon, it's a chemical with carbons and hydrogens. These non-methane hydrocarbons are emitted via both biogenic processes, so emissions from trees. Think that nice piney smell you get from pine trees. That's an example of a non-methane hydrocarbon. And anthropogenic emissions, so emissions from cars, personal care products, etc. Once these are emitted into the atmosphere, they will react with a variety of oxidants. These are usually radicals. Radicals have an unpaired electron, which makes them incredibly reactive. And there are a lot of radicals in the atmosphere, mostly because the sun tends to blast apart bonds, which leads to radicals. So these non-methane hydrocarbons will react with OH radicals, ozone, or the nitrate radical primarily, and will form these compounds called peroxy radicals that I'm going to be talking about during this entire talk, or RO2. And just so everyone knows, when I'm going to refer to RO2 a lot. When I refer to R, I'm referring to some sort of generic hydrocarbon backbone. So I'm showing an example here where we can see an example peroxy radical that you might encounter in the atmosphere. And the peroxy radical part is this O2 with an unpaired electron, and the rest of it is this hydrocarbon backbone. So when I refer to R, I'm referring to sort of that generic hydrocarbon backbone. So the chemistry of these peroxy radicals is very complicated. I'm showing here a diagram that shows just some of the chemistry that these peroxy radicals can undergo. And like I said, unfortunately, it's really important to understand all of this chemistry, but it's also very difficult because of its complexity. But we can simplify this diagram a little bit by breaking it down into two major regimes. So on the right side here, that's now in black, we have a high NO regime. NO is the nitric oxide radical, and regions with high NO are typically associated with high levels of pollution and a lot of anthropogenic influence. So think like busy cities like Los Angeles, which is where I am now. So when in high NO regions, these RO2 sort of have two major fates. One of these is radical propagation. So if the RO2 reacts with the NO to form what we call an alkoxy radical, RO and NO2, you're propagating the radical chain. You're making more radicals, right? And that the key here is that that NO2 radical can go on and go in this little radical cycle that leads to the formation of ozone. So in general, when we have RO2 reacting with NO to do radical propagation, we end up forming ozone, right? Which is one of those pollutants that we talked about earlier. On the flip side, you can also form these stable products, right? These are no longer radicals. These are less reactive than radicals. And they're usually much heavier than the original compound that you started with, right? So you've added a lot of oxygens and nitrogens onto that R, that original hydrocarbon backbone. And as we increase the mass of a compound, we also tend to decrease its vapor pressure, which means that that compound is much more likely to partition into the particle phase and lead to the formation of particulate matter, the other pollutant we were talking about earlier, right? And so in these polluted high NO regions, your RO2 radical will either do radical propagation, which leads to the formation of ozone, or radical termination, which can lead to the formation of particulate matter, right? So knowing how much of each of these pathways the peroxy radical will go down is important if we want to understand the ultimate fate of the peroxy radical in the atmosphere. On the other half of this pie, we have chemistry that tends to happen in low NO regions. This chemistry is much less well studied than chemistry that happens in high NO regions for kind of obvious reasons, right? If you're an atmospheric chemist and you're trying to decide what to study and you're thinking about air pollution, you're probably going to look at high NO regions because those are most representative of urban areas and areas with anthropogenic influence. However, studying this low NO chemistry is becoming more important, especially as NOx or NO, NO2 concentrations are decreasing as a function of time, largely due to emissions regulations that have been put in place in various urban areas. Additionally, these low NO reactions can be important in more remote forested areas and more rural areas as well. And so we can see that similar to the high NO regime, we can have radical propagation. So again, the formation of an alkoxy radical, which leads to more radical cycling. Or we can form a variety of stable closed shell non-radical products, right? Which again, I've highlighted here. And you can see that similar to the nitrate compounds, these tend to form really big, really heavy compounds. In some cases, you're even doubling the mass of your original R compound, right? You have 2 R's in there, you're doubling the mass. And once again, that can lead to the formation of secondary organic aerosol. And so understanding this chemistry, like I said earlier, is incredibly important. And since this low NO chemistry is less well understood, that's what a lot of my research has focused on in the past 10 years or so. And so in that low NO region, one of the reactions our peroxy radical can undergo is a reaction with itself, right? So it can react with another peroxy radical or with the same peroxy radical. And there are sort of 3 outcomes that you can get from that RO2 plus RO2 reaction, right? One RO2 meets another RO2, and there are 3 different things that can happen when that happens. One of these is more radical propagation. So that's 1A here, where you form these alkoxy radicals and you do radical propagation. And then there are 2 of these that are radical terminating channels. So they're going to form those stable products. And in particular, my research has focused on the formation of this product here, this ROOR, which is an accretion product, also known as a dimer. It's called a dimer because you're taking 2 of those original R's and essentially smashing them together with 2 oxygens in the middle, right? And until recently, it was believed that this pathway was largely unimportant to the overall self-reaction. This product wasn't really observed in experiments that looked at RO2 plus RO2 chemistry, and this wasn't really observed in field measurements either. And so people thought it was relatively unimportant. But a lot of recent studies have found that this product may actually form much more quickly than we thought. And in fact, it could form at rates approaching the collision rate, which essentially means that every time an RO2 saw another RO2, they would form one of these accretion products, which is obviously much different than assuming that this never happens at all, right? And so I've thrown a bunch of numbers up here, but trust me, these are just saying it goes really fast, right? And so a lot of my work has focused on looking at, do these form? And if they do they form as fast as these experiments seem to be suggesting, right? We're really interested in this because this is one of those really heavy compounds, right? We've doubled the mass of the original R. So this has the potential to lead to secondary organic aerosol. And in fact, that thought has actually borne out in a lot of field measurements and experiments, right? So the question is, of course, does the formation of these dimers actually impact air quality and climate? dimers have been observed in both the gas and particle phases in remote regions. And so I'm showing here field measurements from forests in Finland, where we can see these dimers in both the gas phase and the particle phase, suggesting that these dimers are forming in the gas phase and then partitioning into the particle phase, leading to the formation and growth of secondary organic aerosol or particulate matter. Recent models, this is a very recent study, actually suggest that dimers could comprise between 30 to 50% of particulate matter in some regions, specifically in sort of these forested regions of South America, which makes a lot of sense, right? I said this tends to happen in low and no regions, so it tends to happen in remote forested regions. But 30 to 50% of particulate matter is pretty bold. That's a pretty significant claim, and is very significant if true. And we can also see that this leads to a significant change in the radiative forcing from organic aerosol as well. So this has pretty significant climate implications. But because we know so little about this reaction, we know so little about how fast it goes, and we know so little about how it changes as a function of structure of the chemical you're looking at, it's actually really hard to do model runs like this, right? These models are very uncertain because we don't actually know that much about this reaction. So this is suggesting to us that it is possibly very important and that more measurements need to be done. And so I have done some of these measurements in my work, and that's what I'm going to show you now. In order to do these measurements, it can actually be very difficult. So we tend to isolate these reactions by looking at them in chamber experiments. So essentially, it's a glorified plastic bag in which we make a fake atmosphere. And we can inject our hydrocarbons, which here I'm showing as an alkene. It's just a type of hydrocarbon. And we oxidize those using that OH radical I talked about earlier, which we form by photolysis of hydrogen peroxide. So we blow it apart with light, UV light in this case. And then that forms our RO2, which goes on to make products. We then detect those products using this fancy instrument that I put a diagram of here. One component of this instrument is a high-resolution time-of-flight chemical ionization mass spectrometer, which is a lot of words, but basically that just takes your compound, turns it into a charged compound, and then subjects it to an electric field. It accelerates, and compounds will accelerate at different rates depending on their mass. And so you can then separate compounds in the time-of-flight mass spectrometer based on their mass, and use that to back out estimates of what that compound could be. In this case, I was using a CF3O- chemical ionization mass spectrometer. That just means the thing that ionizes the compound you're interested in is a clustering with CF3O-. And this is very advantageous for a few reasons. One is it's what we call a soft ionization method, which means that when you ionize the analyte, it doesn't fall apart. If it did, you'd have to go back and try to figure out what you have from fragments. But because it doesn't fragment a lot, it's much easier to actually determine what you have in your system. It's also sensitive to those multifunctional organic compounds, essentially the exact kind of compounds we're trying to detect. We also had a gas chromatograph attached to this. A gas chromatograph will trap compounds at the head of a column at -30 to -60 degrees, and then slowly heat up that column while compounds move out of it. And then compounds will move out of it at different speeds depending on their chemical structure. And this is very helpful for chemical identification. While you separate compounds by mass in a mass spectrometer, you can have two compounds with the same mass but a different chemical structure. And so a gas chromatograph will also separate things by chemical structure. Okay, so one of the difficulty, so we're interested in the formation of these accretion products as a function of structure, right? One of the things that's really hard is that there are a lot of hydrocarbons in the atmosphere, and if we want to accurately model how these accretion reactions will affect things like air quality and climate, we want to be able to predict how a certain peroxy radical will behave in an RO2 plus RO2 reaction rather than measuring the rate of formation for every single peroxy radical you might see in the atmosphere. That's virtually impossible, right? And so our main question in this research was, how does the formation of that accretion product change as a function of structure, right? And so we ran that sort of chamber oxidation experiment I talked about for 4 different hydrocarbons. And these 4 different hydrocarbons, when oxidized by an OH radical, will lead to the formation of 6 different peroxy radicals. And these peroxy radicals vary by their carbon number. So we have some with 2 carbons, 3 carbons, and 4 carbons. And they also vary by what we call their substitution. So if you look at where the peroxy radical actually is, it's attached to a carbon, which is what the node is in these like line and stick figures. And the number of carbon groups that that carbon is also attached to tells us the substitution. So this is a primary substitution. This would be a secondary substitution because this carbon is attached to 2 other carbons. And then we also have tertiary peroxy radical as well. And we know that rates of reactions tend to vary based on carbon number and substitution, which is why we're sort of looking at the variation in this space. And it's actually pretty cool that we can get a lot of information about the peroxy radical structure by only looking at the oxidation of 4 different alkenes. It's actually pretty efficient. And so in order to actually get the rate of formation of these accretion products, we do run into one problem with these chamber experiments, which is part of the reason why there's been so little study of RO2 plus RO2 chemistry, which is that your RO2 can also react with an HO2 radical. And unfortunately, when we form the OH radical, which we need to get the RO2 radicals, that will react with our H2O2 to form HO2. So basically, the way we generate our radicals is leading to the formation of HO2. And so you're also going to get RO2 plus HO2 chemistry. Basically, it's just very difficult to isolate just that RO2 plus RO2 chemistry because you're going to form other radicals when you're forming RO2 radicals. And so the way we get around this is we actually just utilize the fact that there is RO2 plus HO2 chemistry and that we know the rate of a lot of RO2 plus HO2 reactions. And so since we know that rate, we can compete unknown chemistry, so the RO2 plus RO2 chemistry, against known chemistry, the RO2 plus HO2 chemistry. And so we can then have a high RO2 regime where we try to maximize the amount of RO2 plus RO2 chemistry. We'll still have some RO2 plus HO2 chemistry, like I said, but if we can try to maximize the RO2 plus RO2 chemistry, then we expect to form way more of this accretion product. And then in the high HO2 regime, if we try to maximize the amount of RO2 plus HO2 chemistry, we expect to see a lot more of the product that forms from RO2 plus HO2 chemistry. And we can vary between these different regimes by using an external source of HO2, which is the oxidation of methanol by OH. And so essentially what we're doing here, right, is we know we're going to have HO2. So we use that to our advantage by taking the known RO2 plus HO2 rate and then slowly changing the amount of HO2 relative to RO2 we have in a variety of experiments and seeing how the ratios of all of those products changes. And we can use that to get quantitative information about how fast this ROOR forms. And so finally, we're going to show some numbers. That's exactly what we did. So again, we're looking for the relationship between accretion product formation and structure here. And on the left, I'm showing a plot with the formation rate of the ROOR on the y-axis and the number of heavy atoms, essentially the number of carbons and oxygens in the peroxy radical on the x-axis. And then they're colored by the substitution. So primary peroxy radicals are gray, secondary are pink, and tertiary are blue. And then on the right, I'm showing the actual peroxy radical that was used to get the rates that I'm showing in each case. And so we can immediately see that there's a very clear relationship between substitution of the peroxy radical and formation rate of the accretion product, right? Our primary peroxy radicals are forming significantly more ROR than our tertiary peroxy radicals. There may also be a small contribution from carbon number. We see a sort of small decrease as we increase the carbon number or the heavy atom number, but that's within the error of our measurements. And so we have to kind of take that with a grain of salt. But there's a very clear dependence on substitution, suggesting that in the actual atmosphere, primary peroxy radicals will play a far more important role in the formation of these accretion products than the self-reactions of tertiary peroxy radicals. And this is just one piece of information that we now have that we can use to develop what we call a structure-activity relationship, which will tell us the relationship between the structure of a peroxy radical and the amount of accretion product formed so that we can put that relationship into models. And I am running out of time, so I'm going to skip the next part, but I promise it's fun. And I'm just going to tell you what the basic conclusions of everything are. So what we can see is that accretion product formation has the potential to significantly impact air quality and climate, right? We saw that up to 30 to 50% of particulate matter in some regions, for example, the forested regions of South America, is predicted to potentially comprise of these dimers or accretion products, but their formation is very poorly quantified and very poorly understood, making it difficult to actually model their effects in global climate models or air pollution models. And so a lot of my research has sought to look at how this accretion product formation happens for a variety of peroxy radicals and to see whether we can develop a relationship between accretion product, between RO2 structure and accretion product formation. And what I had time to show you is that there's a very clear dependence on peroxy radical substitution, where primary peroxy radicals will form accretion products at orders of magnitude faster than secondary or tertiary peroxy radicals, suggesting that the substitution of the peroxy radical plays a large role and that we should use it in part to predict how much accretion product a peroxy radical will form. And then on the right, time is a funny thing, but on the right, what I would show you is that additionally, the different other compounds on the hydrocarbon backbone also play a significant role. And that's what that right plot is showing there. And so in general, peroxy radical structure clearly plays an important role in determining the atmospheric impact of accretion product formation. And I am now happy to take any questions. Thank you.
Thank you, Sarah. And you do have some questions. One asked several minutes ago by chat member Garbo Dog is so we know that there are a lot of the ROOR particles out there, and that's a broad category, right? So that R, that's your generic backbone. But are there other molecules or structures that you think also need to be further researched in order to understand the accretion problem?
Oh yeah, absolutely. So it's also been shown, and I didn't get into it here, but there are actually other pathways of that RO2 plus RO2 reaction that are being shown to form a variety of different accretion products with structures aside from that ROOR. And which pathways which pathways are important actually depends pretty significantly on that R, that hydrocarbon backbone. So for example, I didn't talk about it here, but that RO2 plus RO2 can actually lead to the formation of an ether or an ROR, which again is another different accretion product and a different dimer that can lead to this kind of secondary organic aerosol formation. So yeah, I think in general, the accretion product question, there are a lot of different structures that need to be considered. And part of the important thing about studying the structure of the accretion of the peroxy radical and how it affects accretion product formation is that we're finding new structures for these accretion products as we continue to investigate.
Gotcha. We have a couple other questions relating to some of the things that influence the emissions or the formation of these products. The first is by Dietrich. How much has the accretion product formation changed due to human emissions as compared to the natural sources? And how has that changed over time, for example, due to environmental regulations, where you see a lot of this is happening in the global south?
Yeah, so I think because the formation of the accretion product is so recently discovered, we don't have a very good sense of how the actual formation of the accretion product has changed over time, specifically because we just don't have a lot of measurements of it. We definitely know that there's a lot of it potentially in like remote and forested regions, which suggests that there are a lot of natural sources of these ROR compounds, but we also know that human emissions can lead to the formation of different peroxy radicals than you would get from just biogenic sources, that human emissions can be transported to these remote regions and therefore change the chemistry and lead to more RO2 production and more ROR formation potentially, and things like that. So it's not entirely clear because there have been not a lot of measurements of this, but as the measurements increase, I think we'll get a better sense for how that might change in the future and how it's changed over time.
Gotcha. And we have a couple of questions by Evan and Fish related to well, really, there's different things that are impacting the distribution in the tropics in particular. And I think one thing about this this map that you're showing, it's showing the relative proportion of these accretion products, not their total aerosol load. Is that fair to say?
Yeah, no, it's showing the relative proportion of the PM 2.5 that contains accretion products.
Right. And so with that in mind, Fish asks, what's with that patch over the Amazon? And Evan similarly is asking, what other factors are influencing that distribution in the tropics?
So, I mean, a lot of it is just the fact that you have such, that it is a remote forested region, right? So in places like the southeastern United States, for example, where you have a lot of biogenic emissions and sort of more remote vegetative regions where you would expect a lot of, for example, biogenic emissions to maybe play a role in this, you do see a little bit of a hotspot. But because it's less remote than the Amazon, you also have more NO concentrations. You have higher NO concentrations, which means that your RO2 can get lost to NO. There's also a temperature component to this, I think. So if you're in a warmer region, that can lead to more emission of, say, biogenic compounds, which can lead to increased RO2 formation. And there's also a component here of the amount of HO2 you're forming. RO2 can also react with HO2. There tends to be more HO2 formation in some other regions as opposed to in the Amazon. So it's a pretty complicated question, and I think people are still trying to understand it, but definitely temperature plays a role, type of vegetation plays a role, amount of vegetation plays a role, and proximity to human emissions also plays a role.
Very cool. Sarah, thank you so much.
Yes, thank you.
I love the way you took the chemical pathways and you broke it down for us.
Oh, thank you.
Yeah, we got it's really cool. The last couple of talks, those just tuning in, we had one going from the oceans, and then we went to the Rio Grande River Basin, and now we got atmospheric chemistry, especially dealing with the tropics. So there's such a diversity of topics that are all impacted, that all rely on this federal funding. And as a reminder, that's the mission. That's what we're going for right now. Is we're trying to drum up support for American science. Americans and others deserve good weather and climate forecasts, and federal funding is such a vital part of that. Part of the history of science research and forecasting here in the United States has been a history of openness, and federal funding has traditionally been associated with not only creating excellent data and data sets and research, but making that data, those data and those data, the research available to everyone who can need it, investors, decision makers, and the general public. And a lot of these things are under threat, not just the generation of the data, but the researchers that use it, the funding for the researchers, and also the free availability of this data isn't something that we can just take for granted. So all these areas are important, and if there's something that's on your mind, we encourage you to check out some of the links on our video description. The 5 Calls app is pretty great. There are lots of ways you can act and contact representatives to let them know that this funding is important to you. My name is Paul Staten. I'm your host during this part of the wee morning hours here in the eastern states where I'm at. And we just heard from Sara Murphy from the UCLA. Our next speaker is Noam Vogt-Vincent, a climate scientist. And let's see. Oh, there he is. Good morning, Dr. Noam.
Hello, can you hear me?
Can hear you loud and clear. Good to see you. Dr. Noam is from the Hawaii Institute of Marine Biology, and will be speaking to us this morning about climate change and the future of coral reefs. I'm looking forward to hearing your point of view on it. I have a colleague here at Indiana who regularly takes students scuba diving and doing research on coral reefs. So that's Dr. Claudia Johnson. So I look forward to hearing your point of view today.
Brilliant. Yeah, hi everyone. Really excited to be here today to talk to all of you about coral reefs and climate change. So just to start off by quickly introducing myself. So I'm based at the Hawaii Institute of Marine Biology, which is this photograph that you can see at the bottom of the screen. So we're actually based on a tiny island just off the coast of Oahu. So I have a rather interesting commute that involves taking the boat every day to work. When I started working, one of the first questions I asked is, "Can I swim to work?" And they told me, "Yes, you can if you want, but there are lots of sharks around the island, so we don't recommend it." So I haven't actually swum to work before. I've stayed safely on the boat, but that's been okay. So I actually started off as a geologist, so I studied earth sciences as an undergrad. But then through my PhD and postdoctoral research, I then ended up going into kind of ocean and climate science. So in earlier talks, I saw how excited certain people in the chat got when paleoclimate was mentioned. So I do also do paleoclimate. We're not going to be talking about paleoclimate in this talk, unfortunately, but it is a really cool area of study as well, and kind of relevant to coral reef research as well. So as you can probably tell from my voice, I'm not from the US, but I moved from the UK to the US a couple of years ago. And I'm funded by the NOAA Climate and Global Change Postdoctoral Fellowship, which is a really fantastic scheme, and that's been funding kind of early career researchers in climate science for several decades now. So all of the research that I'm going to talk about over the next 20-ish minutes or so was made possible by US funding, and specifically NOAA funding into climate research and climate impacts research. So given the number of people that are here today, I'm sure there are some people here who have been lucky enough to visit a coral reef before, whether that is, looking at a reef from the coast or from a ship, or if you've actually been scuba diving or snorkeling in a coral reef. So I've got the chat open on the left. So if any of you have been to a coral reef before and want to mention where you've been, I'll keep an eye out on that. Some basic facts on coral reefs. They cover a really tiny fraction of the ocean floor. So only 0.1% of the ocean floor is coral reef. But despite that, they're only home to over a quarter of all marine biodiversity. So they've got this incredible density of marine biodiversity, which is really incredible, given what a tiny fraction of the ocean floor they cover. Over 100 million people live within 5 kilometers or 3 miles of a coral reef. So lots of people live directly by them. And those of you who have been to a reef before, I see one person mention that they've been to the Florida Keys. You will probably, your involvement with coral reefs was through the tourism sector, which is one reason why coral reefs are really important to the economy. But they're also really important for fisheries because they support a massive amount of fish biomass, and they're really vital for coastal protection. And that's really relevant to places like Florida, where coral reefs play a really important role in kind of dampening the energy from waves and kind of minimizing the impact they have on coastal erosion. So they're incredibly important environments, despite their relatively limited spatial extent. So here we have another photograph of a coral reef. I think this is the Great Barrier Reef in Australia. And we can see all of these coral colonies, which are actually made up of a large number of individual coral animals. So if we zoom in to one of these coral colonies, ignore the fish that's kind of hanging out here in the front. You see all of these kind of circular things here. And each one of these little circles is an individual coral animal, or as somebody just pointed out in the chat correctly, coral polyps. And if we zoom in further into one of these coral polyps, we see that a coral animal kind of looks like an upside-down jellyfish. And that's not a coincidence because they're actually related to jellyfish, but they have these tentacles with stinging cells that poke out into the water. And using those tentacles, they can catch food that's floating about in the water. So corals can catch their own food, but actually you'll also notice that there are all of these like greeny brown dots inside or kind of on the coral here. And these greeny brown dots are not actually part of the coral animal itself. They are algae, symbiotic algae living inside the coral. And these algae photosynthesize, so they get energy from the sun, and they pass some of that energy to the coral that is hosting it. So actually, for most tropical corals, although they can catch their own food, they get the majority of their energy from the symbiotic algae that live inside them. And although, you know, these algae do a really great service for the corals, they also turn out to be a really big vulnerability because when the ocean temperature gets too hot, the corals get thermally stressed. And for reasons that are still not 100% understood, the corals respond to that by expelling the symbiotic algae that live inside of them. And that's called coral bleaching. So here we can see on the left a healthy coral reef where we have these kind of browny green colors that come from these algae living inside the coral. But then in this case, this reef has been subjected to a severe marine heat wave, and due to those hot temperatures, the corals have expelled their symbiotic algae, resulting in this bleached reef in the middle. And in this bleached state, the corals are still alive. That they're not dead, but they are starving because they're not getting, you know, they're now lacking their primary energy source. And if the heat stress goes on for long enough and it's severe enough, then eventually the corals are going to die, and we end up with a dead reef like we have on the right. And for people in the chat who are saying, "Here comes the sadness," yes, that is true, but there is a positive memory. So there's a positive message to this talk, so don't get too upset. But yeah, after a severe marine heat wave, you do end up with a dead coral reef like we have on the right here. And as the ocean gets warmer, these bleaching events and kind of the resulting mass mortality of corals is becoming more and more common. And that's resulted in some of these really dire predictions like we see here. So this quote here is from a recent international climate report, where the authors of this report concluded that limiting warming to 1.5 degrees Celsius will result in the further loss of 70 to 90% of reef-building corals, with 99% of corals being lost under warming of 2 degrees or more. And given that we are currently arguably on track for more than 2.5 degrees of warming, this is a pretty catastrophic prediction for the future of coral reefs. But there is a but. Actually, there are multiple buts, and I want to talk about those buts in the rest of this talk. So but number one is that corals can evolve. So we know that the thermal tolerance of corals has some genetic component to them. So it's not entirely genetic, but the thermal tolerance of a coral is to some extent determined by its genes. So within a coral population, there will be some natural variation in terms of bleaching vulnerability. And after a severe bleaching event, the most vulnerable corals are going to end up dying, and the corals that remain are going to be more tolerant to bleaching. And then over the course of multiple bleaching events, those more resilient corals are going to have a greater chance of reproducing, and the resilience of the population as a whole is going to some extent become more and more thermally tolerant over time. And there's some evidence that this process of corals adapting evolutionarily to climate change is happening already. And another important thing is that coral reefs are connected. So although adult corals are attached to the ocean floor, baby corals or coral larvae float about in the water column, and they can drift over really massive distances with ocean currents. So here we have an animation from a computer simulation here, where we can see these kind of strands, these vortices of coral larvae that are drifting away from their parent coral reef in the southwestern Indian Ocean, and they're traveling over hundreds of miles to new different coral reefs. And that's interesting because if we imagine two different reefs, one reef has been really severely damaged by a marine heat wave, but the other reef might have avoided the most severe heat stress, the surviving reef might be able to then send out larvae to the damaged reef. And if those larvae can then settle in the damaged reef, they might be able to give that reef some chance of recovering from the damage. And then on a similar note, coral reefs can shift their distributions over time. So today, the tropics are generally thermally suitable for coral reef formation, whereas temperate seas are too cold. But in the future, parts of the tropics might become too hot for coral reefs, whereas parts of the temperate ocean might become suitable in terms of temperature for reef formation. And if we're sending if coral reefs are broadcasting larvae from the tropics to temperate environments, those larvae might be able to colonize new habitats in the temperate oceans and potentially create new coral reefs in the future. So we might potentially be seeing in the future a redistribution of where coral reefs are found towards higher latitudes. And to be really clear here, this hypothetical redistribution of coral reefs doesn't do anything about the really serious consequences of losing modern day tropical coral reefs. But if tropical corals can find refuge in temperate, in new temperate coral reefs, they might be able to avoid going entirely extinct. So coral reefs being able to shift distributions, it's definitely not a solution to the crisis that coral reefs are facing, but it might help them to avoid extinction entirely. But the key question here is that I've listed a number of ways in which corals can potentially mitigate some effects of climate change, but the question is that enough? So to investigate whether that is enough, whether these things might, to what extent they will help corals mitigate the worst effects of climate change, we put together a global climate, ecological, and evolutionary model for corals. So we take data from lab experiments telling us how the coral growth rate depends on things like temperature, acidity, and also light intensity. And we also simulate the process of evolution, and we incorporate this process of connectivity whereby ocean currents allow larvae to go between different coral reefs. And here you can see just an animation of how the model simulates the response of coral reefs to future climate change. So in this graph here, on the y-axis, we have the predicted total global coral cover in thousands of kilometers squared. And on the x-axis, we have time going from now to the end of the current century. And this green line shows the prediction for what's going to happen to global coral cover based on current greenhouse gas emission policies, so based on policies that have already been put in place. And what you can see is that under current policies, we expect to see a reduction of roughly 70% in terms of coral cover relative to today by the end of the current century. Although there is a fair amount of uncertainty around that, as you can see in this green shaded region here. But if you look at the blue line here, this shows what we predict would happen to coral cover if all of current policies were reversed and we kind of reverted back to what looked like might have been a possibility a few decades ago if greenhouse gas emissions continued to accelerate unabated. Now, to be clear, we're not on this blue trajectory here. CO2 emissions have started to plateau. So the policies that have been put in place already have potentially already kind of avoided the worst kind of, the most catastrophic possible effects of climate change on coral reefs. So what we're doing may already be having a really positive effect on the future of corals. On the other hand, if you look at this orange line here, this shows what might happen to the future of corals under greenhouse gas emission targets. So basically under the, effectively under the Paris Climate Agreement. So we limit warming to around 2 degrees Celsius. And in that situation, coral cover might start recovering by the second half of the current century. And the main thing to take away from this graph here is that, first of all, coral reefs are not doomed. And secondly, any reductions that we are able to achieve in terms of future CO2 or greenhouse gas emissions is probably going to have a really kind of positive effect on the future of our coral reefs. So any reduction is going to be a really, really positive thing for corals. And then looking beyond the end of the current century, here I'm extending these predictions from 2100 to the year 3500. So in the long term, we are probably going to see a recovery in terms of coral cover, but I have to emphasize here that we're looking here at over 1,000 years. So this recovery here looks very quick, but we're actually looking over hundreds of years' time. So we are going to see a recovery of coral reefs in the future, but particularly under current policies or worse, that recovery is probably going to take several hundred years to return to modern levels. And for the person in chat asking if I said that coral reefs are not doomed or if they're doomed, I'm saying that coral reefs are not doomed. They're not doomed, they're in trouble, but they're not doomed. So now going back to range expansion, which I was talking about a little bit earlier, here we have a map showing the predicted change in coral cover from now to the end of the current century under current greenhouse gas emission policies, where reds are reductions in coral cover and blues are range expansions. And if we're struggling to see very much blue, that's because there isn't very much blue. So we're predicting there's going to be a little bit of new coral cover in southern Australia and a little bit possibly in kind of central or northern Florida. But really, we're talking about a few tens of kilometers squared, which is over 1,000 times less than the predicted decline in coral cover. So for all practical purposes, we're going to get negligible range expansion in coral cover this century. Now, hundreds of years in the future, we are going to get coral range expansions. So here we're seeing a prediction for changes in coral cover from now to the year 3,500. And now we do get significant new reef formation in southern Australia in particular, and to a lesser extent in southern Japan and in the Gulf of Mexico. So in the really long term, we are going to see new coral reefs forming in the subtropics and to a lesser extent in temperate environments. But importantly, coral reefs are facing a crisis in the coming few decades. So a hypothetical range expansion hundreds of years in the future is kind of cool from an academic perspective and from a geological perspective, but it's not really going to help coral reefs with the crisis that they're facing right now. Another thing kind of to bear in mind when we think about potential range expansions of corals is that ecosystems already exist in the environment that corals could expand into. So, in the subtropics and temperate environments, there are already ecosystems that are very happy with their situation. They're probably not going to be over the moon if we suddenly get a massive invasion of tropical coral species into their ecosystem. So, the prediction that we're not going to see, range expansions of corals in the very near future is an important prediction, but it's not necessarily a negative one. So to finish off, kind of the main message from my talk is that corals are not doomed, but they are in serious trouble and they do need our help. So by starting to help, by starting to make CO2 emissions plateau, we've already probably had a really positive impact on the future of coral reefs. But nevertheless, based on current policies, we are going to see a significant continued decline of coral cover this century, with associated very negative effects on things like fisheries, tourism, and coastal erosion, as well as the more kind of emotional impact of the fact that we are seeing the degradation of these really stunning, beautiful ecosystems. And then we are going to see new coral reefs forming eventually, or rather, there will be new coral reefs forming eventually in higher latitudes, but it's not going to be within our lifetimes, at least not for most tropical coral species. And then in terms of what we can actually do about it, up until a few years ago, that people were genuinely predicting that we would see, basically the complete loss of all coral reefs this century, and partially due to kind of improvements in our understanding of coral reefs, and particularly how they can evolve in response to environmental stress, and also partially due to some of the genuine positive policies and kind of changes we've been seeing in terms of greenhouse gas emission reductions. The reductions are not quick enough, but there is, coral reefs are not doomed. They probably are going to survive in some form this century, and importantly, any amount of reductions that we can achieve in terms of emissions reductions will have a really positive effect on them. So in terms of what you can do, so much of the science that I've been talking about today, and coral reef science in general, has been led by the USA. So the US is a leader in terms of coral reef science, and continuing to promote coral reef science in the USA is going to allow researchers to continue to improve our understanding of how reefs respond to environmental change and to design more effective conservation interventions. So I know that I'm repeating what many other speakers have been saying so far, But if you haven't done so already, and if you're in a position to do so, please do contact your representatives to kind of impress on them the importance of maintaining strong US investment in environmental and climate research. So thank you very much for listening to this talk. And if I have some time, I'm very happy to answer some of the questions in chat. And I've seen a lot of great questions in the chat, more than I can probably answer in this session. But yeah, thank you.
Yeah, and thank you, Noah. No, so we actually, it started out, chat members were sad because of the corals, and you gave us some good reasons for hope. And then by the end of your talk, people were sad that you were signing off because you did such a good job presenting, entertaining people in the middle of the night. People said you deserved a better time slot than this. But I'm guessing you got this time slot because you volunteered to do this during a tough time of night for many people. So thank you
did,
for being
yeah.
available.
Yeah,
thank you for doing that. Yeah, we did get several questions. One question or variations of it that came up quite a bit was whether planting corals can help, really does help to restore corals, or if it can help in the process of helping coral reefs to shift if they need to.
That's a really excellent question. So this topic of coral reef restoration, or like kind of direct interventions to kind of help restore coral reefs, is a huge area of research, and there's a lot that I could say on it. What I will say on it for now is that, at least insofar as coral range expansions are concerned, that's probably kind of, like artificially moving corals is not going to help corals expand more quickly. So one of the nice things about running simulation experiments to predict these things is that we can do things that are, or we can run experiments that are not possible in real life. So one of the things we did is we tried to work out what are the limiting factors that are kind of limiting the rate at which corals are expanding their ranges. So we know that environmental conditions that are, the environmental conditions that corals like to live in are expanding much more rapidly than our predictions for actual coral habitation away from the equator. So conditions that are good for corals are expanding relatively quickly. So why are corals not, why do we predict that corals are not able to keep up with that? And the answer is that corals are dispersing to these new environments. So these baby coral, these coral larvae are getting to these new environments. The problem is that the corals that establish themselves there are not growing quick enough to kind of basically keep up or kind of keep propagating corals along. So one of the issues is that although average temperatures are becoming better for corals, although average temperatures will become better for corals in temperate regions, temperate environments have a much bigger seasonality in terms of temperature than the tropics. So there's a coral living in the tropics, even if the average temperature is the same in the future as a present-day tropical environment, it's going to experience much bigger annual variability in temperature, and that in itself is a source of stress, and that kind of limits the maximum rate at which a small coral population can turn into a big coral population. So even if it were feasible to kind of artificially move corals from the tropics into temperate regions in an effort to kind of increase the rate at which corals can expand their ranges, it probably wouldn't really make much of a difference, because the limiting factor isn't dispersal. It's kind of the growth rate of corals in these relatively difficult kind of marginal populations. Another limiting factor is what's called the coral genetic variance, or basically how much genetic variability that there is within the coral population. And again, that's a pretty difficult thing to artificially keep up. So there's a lot of discussion that could be had about artificial interventions in terms of coral reefs, but at least in terms of range expansion, that's probably not going to help, unfortunately.
Thank you. That hits that well. Another question that came up is you mentioned that coral reefs are important for like fish nurseries. How badly, Fish asks, are pelagic fish populations being affected by coral reef collapse?
That is a brilliant question, and the answer to that question is I don't know. That would be a very good question for somebody who thinks about fish and the connectivity between open ocean fish stocks and coral reef populations. Actually, my housemate works on that, so she'd probably be able to answer that. But unfortunately, I don't know. But really good question.
Are we expecting to see a change in the types of coral that are most frequent, like a change from the more vertically structured coral to more fan-like coral, or anything like that worldwide?
Gosh, you all are doing a really good job of answering questions that I can address with my supplementary slides. So the answer to that question, very briefly, is yes. Very simplistically, we can kind of imagine splitting corals into these branching corals, which tend to grow more quickly, but they also tend to be more vulnerable to heat stress, and these kind of massive not branching corals that tend to grow more slowly, but they're more resilient to thermal stress. And this is actually quite an interesting question that I'd love to talk about in more detail, but very briefly, in the short term, we're already seeing a kind of shift away from these more thermally vulnerable branching corals towards these kind of slower growing but more thermally tolerant massive corals. That's being seen already, and we're probably going to see a continuation of that, which is shown by this kind of movement from kind of pale blue to dark blue here. But what's interesting is that after the end of the peak rates of warming, we think there might be a very strong rebound away from these massive slow-growing corals and towards these branching fast-growing corals. And that's because the fast-growing corals are really good at recolonizing kind of dead, abandoned old coral reef. And one last really cool thing is that there is some evidence from a geological record that this kind of short-term movement to massive corals and a long-term movement to branching corals may have happened before. So short-term movement to massive corals, long-term movement to these structurally complicated branching corals.
Yeah, thank you for that. Thank you for addressing those questions. Thanks again for presenting during the wee hours of the morning. Appreciate it, Noam.
Of course. Thank you, everyone.
Great presentation. Yeah, for those of you tuning in or signing on, I'm Paul State, and I'm your host during this segment of the Weather and Climate live stream. What we're doing for 100 hours, we've got about 60 hours left, is we're sharing our science and why our science matters, and we're drumming up support for federally funded science. A lot of what we're doing is funded by federal funds, whether from the National Science Foundation. Quite a few of us in the recent talks have been funded by NOAA, National Oceanographic and Atmospheric Administration, or the U.S. Department of Agriculture. And this funding is important to keep the United States on the forefront of global climate and related research, and contributing to the global community, and also making things safer for Americans and helping to keep us prosperous. So federal funding for science is essential, and I hope you will, if you haven't yet, check out our video description and the links that are there, including the 5 Calls app. Been using that lately to contact representatives. So we just heard from Noam Vogt-Vincent from Hawaii, incredibly beautiful workplace. I have a nice bicycle commute here in Bloomington, but I think he's got me topped. Our next speaker is Jonah Bloch-Johnson, professor from Tufts. Good morning. Good morning.
Yeah, somewhere in between. Thank you so much, Paul. And I just want to say on behalf of all the organizers, thank you so much to everyone who's tuning in. I know it's a strange hour here in the continental United States, but we've just been so overjoyed to see the support for this live stream, to see the people who are out there. So we just want to thank you. Thank you for being there. How's everyone doing in the chat tonight? How are people feeling? Thank you so much, Smart 451 Crab. Yeah, we're amazed that we've been able to keep this going. Hi everyone. Hi Fish. That's great. I'm so glad you guys are excited. You're doing good. Paul, how are you doing? I know it must be late there too.
Yeah, it's early for me. I'm an early riser, but 2:15 a.m. is a little earlier than usual for me.
That's right. That's right. Well, I can say that I'm feeling really good over here about the stream, but I have to admit that I'm upset about these cuts. I've been losing some sleep over here thinking about this. To be honest, I thought I would be able to get some sleep before we came on, but for those of you who are out there who are in the United States right now, our forecasts are getting worse. We're losing our research funding. We're losing our science. I just don't think it's fair. This is resources that you've paid for, that you voted for people who would vote to fund the science, and you deserve to understand the world around you, especially as it's changing. And we want to help you understand those changes. We want to help you understand this new world that we're coming into. And so, as I think about that, I'm losing some sleep, but, we were talking about what time it is. I can see some people in the chat talking, yeah, it's 4:34. That's what it is right now here in Boston. I think you said is around 3:34 there right now, or are you also in, what's your time zone, Paul?
Yeah, I'm also in the Eastern time zone, even though I'm here in Indiana.
Okay.
We decided to buddy up with New York instead of Chicago for some reason.
Sure, that makes sense. What time is it out there in the chat for people? 1:30? Maybe someone on the West Coast?
Yeah, we've got people from Europe, Germany, Australia, so.
Amazing, amazing. Well, as I was lying there thinking about this, I had a thought about, so this is a live stream, right? That's what we're doing here. And I know we had to talk about Streamflow earlier, but if you think about a stream, what happens to a stream? Where does a stream tend to flow? Maybe thoughts in the chat. If you have a stream, what does a stream tend to flow into? I see some 8:30 p.m., 4 a.m. That's right. It flows out to the ocean. So we need to, we're starting here with this little stream, and maybe that stream's going to build up into a river, and then that river can build up into an ocean, and that ocean, you can't stop an ocean. And I'm saying this, I know it's kind of a corny metaphor, but we have had a good core of people here on the stream, for the last 40 hours. I think we've always had hundreds of people, sometimes thousands. But the truth is, if we're really going to push this, if we're really going to make this impact over the coming days, we really want to try to push beyond this. And so we're just asking you, tell your friends, tell your networks. We're not going to be able to do this alone. And we appreciate you so much. Is Tumblr crowd still out there? I know the Tumblr was we had a lot of good representation from Tumblr before, but yeah, but that's great. Absolutely, talk about it on social media. This is a really positive event. We have a lot of wonderful science and a lot of wonderful scientists, and I'm pretty lucky in this, but I know that some of my colleagues, there are people who are kind of going out a little bit on maybe who are a little bit more exposed. So we really got to come together and push this out. Anyway, that's the editorializing, but just wanted to throw that out there. Anyway, thanks for that. So I'm here mostly to talk about. I have some. So this was a time slot that originally going up to this night we needed to have a talk come in here. So this is a little bit last minute, but this is adapted from a public talk I gave a couple months ago. And does anyone want to hear about some climate science? This is sort of like a kind of like a climate science 101. I study climate sensitivity. How much how much warming we're going to get in response to carbon dioxide. And we love you too. We're so thankful you folks are here. Can I get some 100s out there if people want to see some climate science? So, first of all, when I think about climate science, something that I liked, when I first started doing science, I really looked up to other fields, physicists and chemists, because that's sort of what I thought of when I thought of a scientist, someone who gets to think really deeply about some specific physical process, some area. And so to me, I always thought of those sorts of scientists. I think of them; they're kind of like virtuosos of their instruments, so to speak. So these are some of my favorite virtuosos. This is a bassist, thundercat, pianist, Ija Wang. These are some amazing musicians who are experts at what they do. And I think some scientists, physicists, and chemists, they get really in there about gravitational waves or, some specific chemical process. And to me, climate scientists are a bit more like one-person bands. And I say this because we have to understand this big, complicated system. We have to know about lots of different physical processes, so many that there's no way that we're going to be an expert in every single one of these little things. So, we need to cover thermodynamics and fluid mechanics. It's a system with all these different spatial scales and temporal scales. So, it's one of these things where we have to know just enough about all these different processes that we can figure out how to fit them together to explain this big complex system. And another thing about climate scientists that maybe just to make it clear how we're different from meteorologists is meteorologists are, they're interested in what's going on in a given moment. So I have this video here of, this is the Americas as seen from a NOAA satellite. You can see here how beautiful our planet is. You can see those swirling clouds. During the daytime, that's visible light. At night, they're using infrared sensors to get, in white, those are high clouds, and blue, those are low clouds. But, you can see this wonderful dance as the clouds move around. So it's beautiful. And that's, meteorologists are thinking, how are those processes all playing out? And for climate, we're kind of looking at that a little bit at a remove. We're interested in average behavior, statistical properties of the system. So we're interested in things like this. This is a map of the average cloudiness. You can see that maybe some of those cloud patterns you were seeing before are showing up here too. You can, but maybe a little bit more, a little bit more abstract. So you have this band of clouds along the equator, the ITCZ. You have some of these cloud decks that are maybe off some of the coasts. So we're interested in averages or in other properties like this. So one thing we're interested in is understanding the average temperature of the Earth. So now this is something that maybe some of you folks are familiar with out there, but this is a problem that other people have thought about this for a long time, but it really sort of started to pick up steam in the 19th century. One of the ways that people try to understand this is they think like accountants. So think about energy coming into the planet and energy going out. So maybe people in the chat can think, we've got our planet here. What's the main thing what's the main source of energy coming in? Maybe it's a little bit obvious, but how are we getting energy here on Earth? I know there's a little bit of a lag. Yeah, the sun, that's right, fish. So we've got sunlight coming in. Yeah, that's right, Sydney. So we've got sunlight coming in, and it comes in many colors. Here's that visible light. And some of it is higher frequency light, some of it's lower frequency light. But the interesting thing about the sun is that there's actually more light than just that visible light coming in. There's light that's higher frequency or lower frequency that our eyes can't see, but it's still there. And so, that's that lower frequency light, that's infrared light, that higher frequency light, that's ultraviolet light. And this is sort of a smoothed spectrum. Real spectrum's a little bumpier, but and of course we've got a lot of energy coming in. If you average it over the Earth's surface, we think in metric a lot of the time in the sciences. So 340 watts per square meter on average. That's how much sunlight is sort of hitting the Earth. That's, quite a bit of energy in each square meter. But of course, we've got shiny things on the surface of the Earth like ice and clouds, and that reflects some of that sunlight away. And so we actually only are absorbing 240 watts per square meter. 30% of that is reflected back. And if that was the whole story, then the planet would just be constantly gaining energy. And so, some of that might go into melting ice or evaporating water, but most of it would go into just going into the surface and warming it up. And so the planet would just get warmer and warmer until, it boiled away. So there's got to be some other process, right? Something else is going on out there that is helping us to balance this out so that we're not just gaining energy. And the secret is that at the same time that the sun is shining its light on us, it turns out that the planet Earth is actually shining its own light. It's giving off Earth light. And the reason that maybe we don't think about this so much is that all that light is out in the infrared. It's infrared light. And so, excuse me. And the interesting thing about this light is that, in general, the hotter something is, the more of this light it gives off, and the higher frequency of that light it gives off. So here I'm just starting with imagining that the Earth's surface is very, very cold. So let's imagine that it's as cold as the coldest parts of the stratosphere. So it's like minus 80 degrees Fahrenheit. Sorry for folks tuning in internationally for our units here, but this is what we work with. Minus 80 degrees Fahrenheit, very cold. If that was the surface of this planet, is giving off that sort of radiation, then it would only be giving off 110 watts per square meter. And so we have 110 going out, and then 240 coming in. And so that would mean that on balance, using that accounting brain from before, we're getting 130 watts per square meter. That's how much energy is coming in, would be coming in all the time. And so what that's going to do to our planet is that would mean that the planet would start to warm up. So let's say that it warms up all the way to still very cold, but toastier, a temperature of 0 degrees Fahrenheit. Then the amount of radiation leaving the planet would go all the way up to 240 watts per square meter. And so at that point, there'd be as much energy coming in than going out. And so the planet would be in balance. And so it would stop warming. Now, that's still a pretty cold temperature. And this is something that, might be a little vexing, but but what you could see here is that we had the situation where before we were gaining energy, and then the planet warmed until the point where it was back in balance. And we call this sort of negative feedback, the fact that if you have an imbalance, you will warm until you come back into balance, the Planck feedback. So this negative feedback keeps the planet stable at a given temperature. Now, this is a relatively cold temperature, and back in the early 19th century, Joseph Fourier was a scientist, and some other French scientists were thinking about this too. They were trying to think about, this seems a little cold. Why is the planet not actually that cold? What is it about it that allows us to maintain a warmer temperature? And probably a lot of you already are guessing what's going to come next, which is that they came up with this idea of the greenhouse effect. So this is the idea that the atmosphere, they posited, maybe it has this property that it lets the sunlight through, but it blocks all the infrared radiation, all this Earth light that would be coming off of the planet. That's right. Yeah, folks in the chat, you got it. And so let's imagine first that all of that radiation that's leaving the surface is getting absorbed by the atmosphere. Then you'd have nothing making it out to space. But of course, the atmosphere itself is going to have a temperature. Let's say that temperature happens to be this 0 degrees Fahrenheit that we've been using. Then we'd be back in balance, right? We'd have once more the same amount of radiation leaving from given off by the atmosphere as we have coming in from sunlight. But the atmosphere has two sides. It has the side facing out to space and the side facing down to the surface. And so radiation is also going to be coming in down to the planet's surface. And now the surface is out of balance because it's got twice as much light coming in as before. You've got sunlight that's coming in and being absorbed. You've got atmosphere is giving off light that's coming in and being absorbed. So it's going to warm up quite a bit until you have twice as much being given off. So look at that. Now we're up to 86 degrees Fahrenheit, much warmer. So that's this. That was this missing piece, the greenhouse effect. So Fourier had the sense that the atmosphere had this sort of. Oh, thanks, Sydney. Had this big gray. The sort of property of letting through sunlight and blocking infrared light. But it took some more scientists down the road to think about specifically what was going on in the atmosphere, which gases in particular were causing this. And so John Tyndall did a lot of work on this. There's actually also scientists here in the United States, Eunice Foote, who did some experiments with trapping gas in different bottles with thermometers and seeing how that would affect things. But they really, through their experiments, figured out that it was, they really figured out which gases were most responsible. And the way to think about this is we're going to do a slightly more complicated picture than what I showed before. So instead of thinking of the atmosphere as blocking out all of the light from the surface, let's think instead that, let's start with it letting all the light through. So let's say that all that light from the surface is now making it out to space. Then, if you put carbon dioxide in the atmosphere, it turns out that it blocks a specific color of light quite strongly. It just happens that this color is not a color that we can see. And I think that this is kind of a funny thing. If we were in a world where we could see this color, I think that I think that a lot of controversy around climate change and things like that would be a lot easier to deal with because we could just say, oh, you can see that color is the color that CO2 is blocking, but unfortunately it's out there in this place that we can't see. But still, it's there. Yeah, hey, women in STEM. So there's this part of the spectrum that's being blocked by the CO2, but it's blocked by the carbon dioxide in the atmosphere, but that carbon dioxide, it still has a temperature, and the temperature for which that light ultimately emerges is the top of this, is sort of in the stratosphere. That's sort of the outer edge where a lot of this carbon dioxide ends up eventually emitting to space. So it still is itself emitting some light, but it's emitting it at this much colder temperature. So this is the sort of spectrum you would get if you just had carbon dioxide in the atmosphere. It would just take this bite out of the full spectrum, where most of it would be coming from the surface's temperature, but some of it would be coming from the stratospheric temperature. And then they also realized that water is much more complicated. It's related to it being this polar molecule, very strange, but it has this more, takes a bite out of a lot of it. But there's a critical difference between carbon dioxide and water. Oh, so before we get to that, based on this temperature setup that I have right now, where it's 86 degrees Fahrenheit, you can see that now we have a lot more radiation going out to space, as Earth light than sunlight coming in. So that means that we have an energy imbalance. There's more light leaving than coming in. So what's that going to do to the surface temperature, folks? I'll give a moment in the chat. Anyone have any ideas? Any takers? Maybe it's just slow. I'm sure someone's getting it. So it's just going to make it so that if the planet's losing energy, then it's going to start to cool down. So all of this is going to adjust. All of this is going to adjust down, and you're going to end up with a new equilibrium. So it turns out that this is going to give you 56, something around 56 degrees Fahrenheit. That's pretty close to what the surface of the Earth's surface temperature actually is. So this is the sort of that's sort of like the average temperature of the Earth. So this is there's a critical. So these two scientists, they found that carbon dioxide and water are the two most important greenhouse gases, but there's a very important distinction between those two things, which is that the amount of water that's in the air adjusts pretty quickly to match the temperature of the air. So if you have too much water in the air, a lot of it will start to condense out, will rain out. So if you try to add water to the air, and water vapor to the air to try to cause some global warming or something like this, you're not going to have a lot of luck. It'll just rain out. But if you add CO2 to the air, it can stay there for thousands of years. And so this led a scientist in the late 19th century, Svante Arrhenius, to hypothesize that carbon dioxide could actually control the climate across geologic timescales. And he thought that it might have an explanation for the ice ages. And he wrote the first paper that really tried to quantify the effect of changing carbon dioxide on the Earth's surface. I know I'm coming up to the end of my time, so maybe I'll stop here. There's a lot more of this because this is based on a public talk from before, but maybe I'll stop here, and if people have any questions, I'm happy to do anything. Response. But thank you for listening.
Yeah, Jonah, this is an excellent overview of climate sensitivity as a whole, and I love your graphics. I think something that these graphics illustrate, they're not just explaining something complicated for a general audience. The basics of climate sensitivity really do boil down to something that you can calculate on the back of an envelope and get a rough idea of how climate change works. It really does come down to that. And a comment on Eunice Foote. We got people commenting in the chat about women scientists for the win. Her paper, and Jonah, you probably are well familiar with this. Her paper, Circumstances Affecting the Heat of the Sun's Rays, was submitted for a AAAS meeting, but she did we don't know why, but she didn't present herself. A male scientist, Henry, presented for her. And a strange irony about this is that although he did present her work, he kind of discounted her findings in an article later, saying, quote, although the experiments were interesting and valuable, there were many difficulties encompassing any attempt to interpret their significance. And now 100 years later, we can see just how significant these results are.
Absolutely.
So you got some great comments and questions from the audience. One more comment real quick is just that we have audience members who are just learning about climate, and before you learn about climate, it really is this frightening unknown. And one user says it's been extraordinarily empowering and positive to hear about it from the minds and voices of dedicated, committed scientists. So thank you, Jonah, for doing that. Trinet has a question. Did the hole in the ozone layer back in the day have much of an impact on global temperatures? Great question.
That's a great question. To be honest, I don't know a lot about the history of the ozone hole, the ozone layer, going back into the pre-industrial period. I know mostly about it. I know about the issues around the potential loss of ozone and exposure to ultraviolet radiation in more recent years, but I actually, ozone, in addition to, if I were to plot the effect that ozone has on all these different types of light, it would be pretty complicated because it both affects ultraviolet light and it affects infrared light. It's a greenhouse gas. But my understanding is I think that the levels of ozone were relatively stable, at least in the pre-industrial period. I don't know if this is something that, Paul, if you have more experience or background with.
Yeah, well, the ozone layer, the ozone hole is still there. We don't talk about it too much because as a human, this is good news when you're talking about climate change. As a society, we have basically figured out how to stop the ozone hole from getting any worse, and it's slowly healing. And as far as temperature change goes, fortunately, the ozone hole is at the pole where it doesn't have, there's less sunlight at the poles anyway. So its effects on surface temperature aren't all that big. But the ozone hole does mean that the polar stratosphere is colder during parts of the year. And this does affect large-scale wind patterns more than global temperature patterns. So this does affect like the latitude of the southern hemisphere jet stream, for example.
That's right.
So it does have impacts, but it's actually the story of how the ozone hole problem, first off was caused, but also how this problem was solved is very encouraging. These things can be solved. Climate change is a different problem because it has many more contributors to it, and there's not a single silver bullet to fix it. On the other hand, the good news is there are a lot of things we can do.
That's right. That's right.
Jonah, thank you again. Thanks for giving us this overview on sensitivity and really bringing together a bunch of different topics and presentations in this great unifying talk. Thank you so much.
Thank you for having me, Paul, and thank you, everyone.
If you are just tuning in, we are, let's see, an hour 40. I think we're just finishing up hour 40. So I think we're getting on to hour 41. We have about 59 hours of the 100 hours left. I'm Paul Staten. I've been the host for the past couple of hours. And we have a new host about ready, Virginia Shute, I believe. Oh, hour 41. Good. Did I say your last name? How did I do on your last name there, Virginia?
You did pretty well, but honestly, nobody does the last name right. I didn't until I married my husband. So it's Shooty, like a basketball, but the letter E is how I don't know. It's Shooty.
Thank you. I'm sorry about that. There were a few different pronunciations
Oh my gosh.
of it. So Shooty.
Some people add an L in and there is just no L. So you did a good job.
Thank you for being here. Welcome back. Good to see you again.
Thank you. Nice to see you as well. I know we interacted in this kind of time space yesterday as well.
Mm-hmm.
All right. So good morning, good afternoon, good evening, and good night. Fish, you are remembering me. I was wondering who I would see that I recognized from yesterday. Yes. And I'm seeing some of the same names that were here yesterday. You said we're starting hour 41, Paul. Is that right?
Yeah.
Okay. So 41 math. For everyone who doesn't know, it's 5 a.m. my time. So I just got up. Math. We are 60 hours to go.
50.
Yeah. Thank you so much for being with us. I am excited to be with you for the next 2 hours. Yesterday morning, one thing that we loved doing together was leaning into the cozy science aspect. So, one thing that you get from being on this live stream with us is learning about science and climate and weather, of course. But another thing you get is to see us all when we are not necessarily in our offices, because this kind of time block for the US, since we're featuring US scientists, is the middle of the night. So this is my house. My kids and my husband are sleeping up there. We are fostering 2 kittens and they are making noise in the living room. And it's like all my willpower not to just bring them and show them to you on camera. So I think this is one of the things we are doing, is showing the kind of people who care about this stuff in this country. It's all just us. We're all just people. Let's see. So I'm wondering, I know I asked you where you were from yesterday, but I'm wondering how many of you have ever chatted with a scientist before, or if this is your first time. I know some of you are scientists yourself in the comments, but if you could tell me, like, how do you know science? How do you know scientists? Or is this your first time? How is this going for you? Okay, and while you are putting in your comments in the chat, I am going to remind you, while we are all here together, why I'm doing math at 5:03 in the morning Eastern time. We know how important weather and climate forecasts are to you and to everyone in this country and the world. The United States has long been a world leader in weather and climate prediction. And I said it yesterday, I'm going to say it again. Prediction is so different from documenting what's happening, even in real time. Scientists in the US developed the first computerized weather forecast to help everyone know what to expect in the coming days, in the coming weeks, in the coming years. And we made the first computer models of the climate impacts of carbon pollution so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites to planes to balloons to floats. In my segment yesterday, if you were here with me yesterday, we learned about magnetic tapes, which are still the most efficient way to store giant volumes of climate data. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that miracle here with you in the next 2 hours. I will be here with you for the next 2 hours. This miracle was made possible by decades of investment by the American public, which means at least some of you on this live stream right now. I know some of you are elsewhere, but it was the American public and investments in both dollars and support and time and like thinking that this was a good career path and then sending people to do it if they liked it. Oh, we were talking about women scientists last segment. I'm a woman scientist. I know what that's like. So having not only the dollars flowing into science, but the support for the infrastructure and the system of science getting done, letting people explore things they like, teaching parents to teach kids, like to let them do what they like. I'm a parent. It's not hard to let kids do what they like, but sometimes it can feel daunting to support them. Getting off track because I love all of this stuff so much. So back on track, the miracle was made possible by decades of investment by the American public, but in recent weeks, funding cuts have put this miracle at risk. Weather stations are so short-staffed that we are losing our observational coverage, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and the climate is disappearing. It doesn't have to be this way. If you like what you see in the live stream, if you are relating to us scientists as people in our cozy science homes, please use the link in the description for this live stream. And I know people have been putting it in the chat periodically to contact your representatives if you're in the US. If you are not in the US, or in addition to contacting your representatives, if you are in the US, talking to people about climate science is one of the biggest things we can do. If cozy science makes you happy, telling people that you know and love and that trust you that cozy science is a thing, that we're all just people doing our best and we happen to love to do it in a science way, that changes how people think of science. That changes how people think of scientists. It changes the way that people feel when they are challenged to think about the good that we could do if we took care of ourselves and the planet. So contact your representatives, talk to people, and please tell other people to join this live stream if you're enjoying it. We hope that you learn something about weather and climate in the next, again, 2 hours with me and beyond. And I'm going to check the chat now to see what y'all have been saying. I know there's so many comments, but I've been yapping. Let's see. Oh, I know. I know. I'm not going to bring the kittens out, but they're like making tiny squeaks in the background, but they're supposed to be potty training in their crate. So for science show cats. Okay. At the end of this 30-minute segment, if we have a little extra time, I can pull one out maybe, but For now, we're going to stay on mission, people. Stay with the science. I'm a scientist. Mom is a scientist. I talk to myself and I am a scientist. Does that count? Yes, but are you okay? Been interested in science most of my life, hoping to go back to school for biology, a lab tech, watching from the lab currently in Germany. This is fantastic. Oh, and y'all are meeting each other in the chat. Paleontology nerd, I remember the paleontology nerdery from yesterday. Let's see, study wildlife ecology and habitat management. Oh, man, y'all are amazing. Okay, not a scientist, but interested in proofed facts, work in communication, and know how easy words can change the meaning if not proved by facts. I totally get you. It is so, yes, I am a communicator. I am a science communicator. So, let's see, what? Please don't. Okay. Oh, we in the US deserve better. Thank you. It's so nice to hear support from elsewhere. I know I talked about this yesterday, but it can look from the outside as if we in the US are not trying to push back against the cuts on science. And I promise you that we are. I mean, we're here on this live stream, right? But there are people in the US acting in small and big ways every day to get people to understand that as scientists, we care about humanity and the planet. And the goal is to have a better life for humans as they live on this planet. So we are working in small and big ways all the time. It's just that you can't always see all the groups that are doing all the work and all the work we are doing. So this is one of the things that I loved yesterday, was making this so visible to everyone the world over that you can just tune into this live stream and see all these people waking up at 4:30, ignoring kitten squeaks, to come and talk to you about science. So speaking of talking to you about science, I want to bring on Andrew Williams to chat with me about weather, climate science, how things are going. Andrew is an early career climate scientist and an organizer of this live stream. Good morning. Where are you? What time is it?
Good morning. It is also 10:05 a.m. for me on the East Coast. It's kind of insane. I'm glad that we're leaning into the cozy home vibes, though. I just had my cat coming and like scratching my chair in the background. I was like, no, stop doing that.
You should have said yes. Everyone in the comments wants to see our cats.
No, she's okay. She may make she may force her way into this room at some point.
I like that. You're like, I'm telling her to go away, but maybe I'll force her to come back.
I know. She's attention starved, like these cats, they have a hard life. They work really hard. My favorite fact is that if you go, so in science papers that we write, we get to have, we have like the body and the introduction, the results and conclusions. We also get an acknowledgement statement at the end. And typically people just use that and they say, well, I thank my funders. Like, we're thanking NSF and NOAA and DOE for giving us the money to do this science. But you also maybe thank like someone who supported your work along the way. I always thank my cat. And I don't think anyone has realized yet, because they just see Cleo and think it's like my wife or something. I don't know. But anyway, it's Fish. There is a famous story of one person having their cat as a co-author, because so when you write papers, so the story goes, someone wrote a paper and they were the only author, and they kept saying we in the paper. So they're like, we are going to show this, we will now look at this, we will now look at that. And the editors of the journal said, you can't say we, it's just one person on the paper. And so this guy was too lazy to change all the we's to I's, and so just added his cat to the co-author.
I love that as a response. Like, no, I will not be giving in to your demands. I will be adding my cat as a co-author on the
Exactly. Apparently that cat was invited to give talks at universities. So that's, science and cats, it's just, we're right in.
I mean, I would rather show up to see a scientific talk if the person was, those cat cafes, if they were in a cat cafe situation where there were a bunch of cats just like roaming on stage. I think I would be more likely to go, but I don't know if I would
I wouldn't
learned as
focus.
much.
No, I would learn absolutely nothing, but I would be so happy.
I have a very positive impression of the person in the event. Oh my goodness.
So wait, so all of you guys on the chat now, are any of you also up at 5 a.m. your time? What time are you currently experiencing right now? Or are you all like in Hawaii or something at like 10 p.m.? Or
Yesterday they were from Europe and Australia.
7 p.m. Larkin. Oh, hey Larkin.
Oh, we're just getting emojis now. People are so excited about cats.
Oh, it's cats. Oh dear. Oh dear. 11 a.m. Oh, these are okay. We got some Oslo.
Oh, someone's up at 5 a.m. Someone's in our time zone.
Nice.
Oh, someone's up mountain time. Dragon Kiwi, are you up for the night? Are you?
Finland.
Oh, y'all are up at people. I mean, listen.
Wow.
I've reached the age where I go to bed early and complain about how late I'm going to bed. So
yeah.
I'm impressed that y'all are up at 2 and 3.
This is insane. We have someone from Australia who is basically 12 hours difference from us. That's insane. Other side of the world.
Shannon put in the chat that they're in Calif, which I assume is California, and I have never had the guts to abbreviate anywhere that I've lived so confidently. That's so cute. Oh my gosh. Andrew, I wanted to ask you, you said you're an organizer of the live stream, and I know I know we could stick to the science, but this cat crowd I think is a little bit out of the box. Can you tell us what it's been like to make this happen?
Yeah, I think that so you guys just had Jonah on. So Jonah was also one of the main organizers of this event. It was really he was one of the people who had the vision for us putting on a huge live stream. And we were just talking, like so Jonah and I are good friends, and a month or two ago we were on a phone call and just being like, these cuts, we have to do something, right? It felt like this wasn't getting the media coverage perhaps that we thought it should. And we were just brainstorming behind the scenes, thinking like, what can we do? And there were some other ideas that came up before the live stream that were not as good, I think. We were like, maybe we could busk, maybe.
Wait, I want to, please do not move on from that sentence. No. Tell me more about this idea, please.
Okay, basically the first idea was we could basically just say, well, climate science needs $500 million. Let's go out and just try and busk and be like, oh, we made $3, guys. Only like 500 million more to go. I'm glad we didn't do that. I think this makes a lot more sense.
Do you have street corner talent?
So we're all musicians. So Jonah went to like music school. He's like really, he's like a musical like prodigy. I play guitar. And there's also so someone else who's going to come up on the stream later, Nather. He's like a really, really good drummer. So I think the vision was maybe we could like get some like little band together, or something like that. But
amazing.
But I think this is better. We get more. I would not want to be like busking for 100 hours. I think that would actually hurt so much. But yeah, this is so much better, and we get all the chat on the side. Eurovision for climate science. I
think this leans slightly into the shareable talents of maybe a wider group of people. I still believe that there is a place for busking for science, and I love the hard lean into the sarcasm there, raising $3 when you need 500 million to like billions.
Exactly.
I just want to it was a great idea, and people are saying that we should make it happen sometime.
We can, maybe we can do this live stream again and just have it be a concert. Kittens for climate change.
Everyone in the chat right now would show up to the busking and be like, "We love you, but also would you stop now?" Okay, I'm sorry. So I distracted us. So the original.
No. It's, I mean, I think we're matching the energy right now. I got yesterday I went to go and take like a short nap because Jonah and I have been basically up since the beginning of this event. So we've just been like napping sporadically, and I was like, I'll take like a 10-minute nap. I woke up like 2 hours later, so I'm very much plugged into the whole like crazy vibe. It's okay.
So feeding off the chat.
Yeah, but I mean, thinking about just the event in general, so we then reached out to some of the bigger names in our field because we wanted to make sure that there was some buy-in, basically. And you've heard a lot of these people already. So a lot of these people are the ones who gave the keynote. So for example, we had Carrie Emanuel, we had Amy McGovern yesterday talking about AI. Maria Molina, who also talked about like AI and the fact that she was like a weather forecaster, TV broadcaster before going into science. A lot of these people we were like reaching out to and touching base with beforehand and just seeing if there was like enough energy in the field to do something like this. And what we found was it was just as the word that we used was like, it's a bit sciencey, but we used criticality. So it's when like a system is like really close to going into a completely different state. Yeah. And, as a field, we kind of we weren't collectively coming together and saying that much about it, but I think everyone wanted to. I think there was a lot of energy to try and talk about this, talk about the cuts, come together, make some noise about it, and just share our science with people and tell people what we really do. And so when we started reaching out to people, the amount of signups we got was just crazy. And we got really excited when we got our first like 10, 20 signups, and then we ended up having hundreds of signups.
Yeah.
And
y'all advertised this not very long ago, right? This came together very quickly.
Yeah, I mean, really, we started basically everything you see here came together in like a few weeks, and the advertisement was probably like a week before the event or something. We have some amazing people behind the scenes who have been Miriam, who's one person who you may have seen in the chat as well. She's just been helping us so much with the StreamYard and the live streaming setup and all this type of stuff. I think you've said this before, or someone has said this before, but we're scientists, we're not YouTubers, so this is kind of, for at least for most of us, this is new to us, Yeah. And so it's been, we've been accepting all the help that we can get, and just really appreciate the energy in the chat as well. I think also we were surprised it's having so many people. Like, I think psychologically we prepared ourselves for maybe just like 10, 20 people showing up, also scientists or something. Yeah. And then we turned on the live stream, and instantly there were like 300. And by the end of that first segment, we were at like 600, and it just kept going up, Yeah. And even through the night, you guys have been like really strong. We have the international contingents who are like helping to pick up the night shift. I don't think we've ever really dropped below like 400 or 500 people watching at a time,
that's amazing.
I
want to bring up a question from Mbilby. Will there be clips and recording released from this live stream over time? Lots of unpaid editing work there, I do understand.
So when I woke up at 4:30, I woke up to a string of messages from our unpaid editor. His name is Sil. He's actually, he was the first, he was my co-host for the first segment, but he is an amazing editor. So him and a couple of others behind the scenes are putting together some clips now. We have one, which I can share with you, which is just, sharing the full, when you try to share a full like link to a BlueSky post or something, it's super long. So we made this like tiny URL. So if you guys go to tinyurl.com/save, how can I type this? Save.
And it's on your screen right now for those of you watching the playback or looking with us now. It's that link right there.
Exactly. And this is in the chat as well. And this is, so we've got a lot of highlight clips that we're going to be bringing up over the course of the day now. It took us a little bit of time to like work out exactly how to do it. I think we've got it down now. We've got some editing. And this first clip, we thought, maybe we could even watch it together because I think it's really good. Let me see if I can get it up. tinyurl.com.
The behind the scenes people are, I don't know if that's you right now, but the behind the scenes people are like scrambling. While you're pulling that up, I want everyone in the live stream to know, it went by very fast, but Andrew, the joke is that the unpaid editor is like trying to figure out how to do this. None of us are getting paid. I mean, scientists are paid, and scientists have, in general, some kind of service component to their job if they are in what we think of as a typical academic position. But usually it doesn't include things like this. Things like this are seen as a different kind of service. And so everyone that you see on the live stream is going out of their way to spread climate joy, to unify people behind, knowing what's happening, being involved in what's happening, taking action. And remember, you can act with the link that's in the description for this video. The Weather and Climate live stream has made it very easy to get the information you need to take action. You do not have to be an expert yourself to contact your representatives, to talk to people around you about science and how you feel about it. So I just want to emphasize that science is a passion career. You go into science because you love science primarily. I don't know of a single scientist who is in it for the money. Maybe some people who are consultants for certain giant corporations, but I don't know. I hang around with the people who are on the ground, in the mud, on their knees. Yep. And we're all doing it for passion, which means we're showing up to this live stream as well I feel like I'm on QVC or something, by our climate passion, because we've made it just for you with our sweat and tears. But that's the kind of people we are. Cozy science, doing it because we love it, showing up to make this happen because it's what we think is the good thing to do.
100%. And that's, yeah, exactly. I think I didn't even think to mention that we're not getting paid for this, because we barely get paid for anything. So it's
it didn't occur to me either, but you said it out loud and I was like, I wonder if people know that we're just here at 5:24 a.m. being we love science.
Yeah. I can, so let me just show you this clip, because I think so this is from Joe Friday, who is a former National Weather Service director. And we had a panel with him and another former National Weather Service director earlier in the stream. You can actually go to wclivestream.com/catch-up, and you can look at the earlier stream. I think this was stream number 1. But he just had this amazing quote. I'll see if I can bring that up on stage now. So this testing my text skills.
The National Weather Service really is a national treasure for this country. It benefits every man, woman, and child. It costs every man, woman, and child a Big Mac and a Coke a year to provide that service. The National Weather Service really is a national treasure.
I just thought Big Mac and a Coke really put that into perspective for me. That whole segment. Joe and Louise, who's the other National Weather Service director on the bottom. They just talked really passionately about how much value for money, honestly, people get out of this, and no matter where you are in the country, no matter who you voted for, no matter what your opinions are, you need to know if it's going to rain. You need to know if there's going to be a tornado in your area. Yeah. And I also just loved Joe Friday's vibe. I really think if he has an opening for a grandson, I think I'm very keen.
I love that as a way to get to know you. Walk up to that person at a conference and say, "Hello, I'd like to be your grandson."
Yeah, would you like a Big Mac and a Coke? The other thing I thought was amazing was Sara Perkey, who was one of our keynote speakers on the first night. So she helps to organize, or she talked about this series of floats in the ocean called the Argo Array, which are these these robots in the ocean that just float along, and then they sink, and they go along a little bit more, then they sink, and then they go back up, and all along that way they're taking data about the temperature in the ocean, where the ocean currents are going, how salty it is. And they cover the whole ocean. There are thousands of these things there. And the US pays for most of them. Yep. And it only costs every taxpayer in the US $0.05 per year to get these little robots measuring the whole ocean. It's crazy.
So my background is in marine ecology, and though I am a science communicator now, I do a wide variety of things now. And one of the things I do is I'm the co-founder of an ocean data startup, and we are very early on in our product development, but understanding the ocean data ecosystem really explains why we are doing the live stream to highlight the federal funding. And I don't know that we've talked about that specifically. You can do things with giant investments from federal dollars that coordinate across area, across institution, across states even. You can achieve those things in like coverage of the earth, but also in terms of the efficiency, so the Big Mac and a Coke, that you just can't do if you're a single scientist in a lab by yourself. And so the investment, I've been talking about how it's an investment in dollars, but also an investment in the system. Mm-hmm. Federal dollars and federal investment is what makes the giant coverage possible at scale at a cost that is ridiculously low. So everybody watching, learn something from this segment. That's it. We'll learn several things from this segment. Make that one of them. The federal investment is really important.
100%. Yeah. And what Adam said, so Adam Sobel gave a keynote last night, and he was talking about the private sector and how the private sector does insurance, and they calculate risk of climate change and stuff. But the only reason the private sector can do that work is because of decades of federal funding, which has supported basic science. So we know that the reinsurance industry, for example, that's trying to work out where a tropical cyclone will go, is using decades of research from people at institutions and labs across the US who just, without thinking necessarily about an application per se, have just studied these phenomena because they're clearly important. It's clearly important to know where a tropical cyclone is, even if you don't know how to monetize it yet or something.
Absolutely.
And yeah.
I want to extend that to a lot of people don't realize, as I said, I'm in ocean data, and a lot of people don't realize that the data that the government collects, especially through some of their large ocean arrays, is available for free. And it takes expertise to take the data streams and turn them into something, but that's what powers our weather apps. So I think when people were first talking about the federal cuts to institutions like NOAA, which is National Oceanic and Atmospheric Administration, people were saying, well, I'll just go to my weather apps for weather. And it's like, those are powered by NOAA data. They're just, the weather apps take the free data and then they put a nice interactive face on it. And then I heard people saying, well, I'll just look at my local meteorologist. I'll go to their forecast. Those meteorologists are using NOAA data. So the federal government is not just making this data available for purchase to giant companies. They're making it for everyone. And the ways that we get our information are powered by all of that free data. So I'm getting a little bit yelly.
No, 100%. Get on your soapbox. I don't want to take up too much extra time here, but because we have so many great speakers, and you've heard enough from me at this point. But
well, Andrew, would you like to leave us with a parting message as a kind of originator idea for this live stream, and somebody who we just chatted for a little bit about how it's going? Is there a sign off you'd like to give? One last word.
I think I'm not very eloquent, but I think that the thing is, it's so something that really hits me, and so I do myself and some of my friends, we do a lot of climate outreach based off just making sure that people have spoken to a climate scientist and have engaged with a climate scientist, or indeed a weather scientist at some point in their lives. I think most people haven't, and it's such an important issue that it's crazy that that there isn't more communication like that. And so I love the fact that this live stream is reaching so many people. And if you're able to share this with your friends and family, either through Facebook or any other thing like that, I think that'd be amazing, because we climate scientists, scientists in general, it's a little bit easy sometimes to just keep your head down and keep working. But we really need to keep this conversation going between you guys, the public, and us who are doing the science, doing the coding, and trying to learn about our planet. And I think this just shows that it's working. And I would love, we got to keep this going. It's really important.
Well, thank you so much for pivoting from busking to a live stream. I think everybody in the chat, everybody watching is really grateful that that happened, even though we love the busking idea. Andrew, I'm going to let you go so you can get some rest. Thank you so much for chatting with me.
All right. Thank you all. Thank you guys in the chat.
So we are halfway through hour 41. It's now 5:33 my time. Andrew was talking about how we need people to be able to connect with scientists. And I know I've not talked about myself very much. It says science communicator as my title, and that is true. I'm going to give a talk about my work tomorrow morning. So exactly 24 hours from now, plus an hour and a half. So 7 a.m. Eastern. But my job is to make sure that y'all out there who are specialists or not can connect with the good science that good scientists are doing that helps you make life better, because it is a whole job to know how to communicate. So the scientists are busy doing the science, and it would be a whole skill set to learn how to reach people. Andrew said that the people on this live stream aren't YouTubers. I'm not a professional YouTuber, but I do a lot of stuff on YouTube. So blending the scientists with the science communicator, and then just making life better, talking to people, having a good time, making science available, making scientists feel accessible. So yeah. Oh, somebody asked, what date is my talk? May 31st. Again, math at 5:30 in the morning. Yes, May has 31 days. May 31st, 7 a.m. Eastern. I want to bring on our next speaker after I remind you why we are all here, because we have switched speaking slots. So just as a reminder, we're halfway through hour 41. We've seen so many great talks, and I am here for the next hour and a half with y'all, bringing energy East Coast time early in the morning. Weather and climate forecasts are important. That is why we are here. U.S. scientists have been world leaders in weather and climate predictions. We have developed the first computerized weather forecasts. We have an unparalleled network of observations that uses so many different tools to make data available for free to everyone. And the excellence has been brought about by investment in terms of dollars and infrastructure and support from the U.S. public. And so if you are a member of the United States public, please do get in touch with your representatives, because without restoring funding, this will not be able to continue. If you are not part of the US public, well, and even if you are, one of the biggest powers we all possess all the time is drawing attention to the things that we think are important, and just letting other people know that we love and trust that this is important, and they need to know about it, care about it, and act about it for themselves. So talk to people you know and love. Call your representatives, write your representatives. The link on the screen right now has made it easy for you to find the way to contact your representatives that works for you, and you don't have to be an expert. They can help you with what to say and how to say it. All right, it is time for our next speaker. This is Mariya, and I'm going to let Mariya say Mariya's last name, because I'm so sorry. What is your last name?
My last name. So hi, my name is Mariya Galochkina. Thank you so much for running this event. The organizers have put in so much effort into this, and I'm really glad to be here. And it's been amazing listening to other people's science and hear how much people care about their work.
Well, thank you so much for showing up at, I know it says you are with MIT, Massachusetts Institute of Technology, and HUI, which is Woods Hole Oceanographic Institute. So you are also East Coast. So thank you for being here at 5:36 a.m. in the morning. I am going to let you have the stage.
Awesome. So hi, like I said before, my name is Mariya. I am a climate scientist, and I'm a PhD candidate at the MIT HUI Joint Program in Oceanography over in Massachusetts. So good morning, my morning people. And I'll be telling you a little bit about some of the work that I do in using climate patterns to forecast coral bleaching months in advance. But more importantly, I want to just talk about coral reefs and why we should care about them. So coral reefs are perhaps some of the world's most ecologically valuable ecosystems. A statistic that I learned over the course of my PhD is nearly 500 million people worldwide rely on coral reefs for some ecosystem service or another. Coral reefs are hotspots of biodiversity. They cover less than 1% of the ocean floor, but they host up to 25% of all marine species. They also confer a ton of coastal protection to nearshore communities. So coral reefs themselves, particularly healthy coral reefs, can attenuate up to 97% of incoming wave energy, and they also reduce the wave height. Hundreds of millions of people live in low-lying nations in the Pacific, Caribbean, and Indian Oceans, so healthy coral reefs confer a natural protection from storm surges and high tides. Healthy coral reefs are also critical to global food security. So nearly 500 million people worldwide rely on coral reefs for their food or income through fisheries. And in the US alone, and the US doesn't have that many coral reefs. However, despite that, more than half of all US fishery species depend on coral reefs for a portion of their life cycles. Coral reefs are also beautiful, and people love to visit them. Tourism to reefs is estimated to generate over $36 billion annually across the globe, and it makes up a large part of many coastal countries' GDPs and employment. However, it's no secret that coral reefs are facing a litany of threats in the 21st century, from pollution to overfishing to ocean acidification and disease, as well as invasive species eating corals. However, the single worst threat to corals worldwide is warming ocean temperatures. And you don't have to be a coral scientist or a climate scientist to have read some depressing article or another in the last few years about how coral reefs are in decline and they're not doing too hot. So essentially, ocean temperatures are rising to a point that corals cannot tolerate. Over here is a plot of sea surface temperatures trends over the last 120 years, overlaid with points that show where coral reefs are located across the globe. And as you can see, all coral reefs are located in regions that have warmed over the last century and are projected to warm in the future under greenhouse gas emissions. So if we take a step back, you hear the word coral bleaching often. So under normal conditions, a single coral colony is covered in thousands of genetically identical coral polyps. So only the outside of a coral is alive. And all of these polyps contain these single-celled organisms known as zooxanthellae. And these zooxanthellae live within the polyps and provide up to 90% of the coral's energy through photosynthesis. They're also what give corals their vibrant color. However, when corals are exposed to stressors, for example, high heat, they become stressed over time, they lose these zooxanthellae, essentially losing not only their color, which gives them this bleached appearance, but they also lose their main source of energy. So essentially, when corals are bleaching, they're slowly starving to death. So let's think about this practically. You're a coral and you're used to living at a certain range of temperatures that fluctuates from year to year. Much like all organisms, corals have an upper level comfort zone. I also have an upper level comfort zone. I like 80-degree days in the summer. Don't really like it to be too much warmer than that. But all of a sudden, there's a heat wave and temperatures get warmer. For example, a good analogy to this is I'm going to go to the sauna. I'm in the sauna, it's quite uncomfortable, but if I'm in the sauna for a short period of time, I'll be totally okay. However, if you sit in the sauna for too long past your threshold of discomfort, you start to feel really unwell. You might start to get dehydrated and nauseous and pass out. But if you're removed from the hot sauna soon enough, you'll be okay. And this is kind of a good analogy for what a coral is going through when it bleaches. It's not doing well, it's above this discomfort zone, but if it's taken out of this, it'll be okay. But if corals continue to face high temperatures, they'll die. Much like me, if I'm left in the sauna for way too long, I might die there. And here's a pretty depressing image of the same coral colony in 2023 on the left, where you can see it's bleaching. It's very pale and white, but it's still alive. But temperatures continue to be too warm that year, and by 2024, that same coral is dead. And when corals die, they get covered in this gross, slimy algae that makes it particularly hard for new coral babies to grow on top of it. And you can also imagine that the fish that live on coral reefs aren't particularly thrilled to live in what is essentially a moldy garage. And over the last 30 years, over 50% of coral reefs have died across the globe, and coral bleaching events and coral mortality events are projected to increase in number and severity in the future. So currently, coral reef managers monitor bleaching risk through a beautiful, publicly available program made possible by federally funded science. It's called NOAA's Coral Reef Watch, and if you'd like to play around with some cool maps, here's a good website. And essentially, Coral Reef Watch is based, the main product that is offered is a 5-kilometer satellite sea surface temperature data product for the entire globe. This is really high resolution if we think about the entire ocean. It's daily data, and it's been made public since 1985. But the thing that coral bleaching managers really care about is a metric called the degree heating week, which is essentially the accumulated heat stress in a given grid box. You don't really need to know the nitty-gritty, but it's basically an integrated thermal anomaly above the local coral discomfort zone over the last 3 months. And a number that you typically see in the coral reef world is when you reach 4-degree heating weeks in a particular region, that's expected to be enough heat stress for widespread coral bleaching. And when you hit 8-degree heating weeks, that's enough heat stress for severe coral bleaching and mortality. It's important to emphasize that this is kind of a theoretical model of coral bleaching, but this is the product that everyone is using across the globe to make their decisions. My colleagues in the Marshall Islands and the Caribbean all are looking at NOAA's Coral Reef Watch because it's free, it's publicly available, and it's reliable. You might remember some headlines from 2023, which was a particularly strong heat wave off of the coast of Florida. Temperatures reached up to 101 degrees off of Miami. And if we remember, 4-degree heating weeks, you expect to see bleaching. 8-degree heating weeks, you expect to see mortality. This is what the NOAA Coral Reef Watch product looked like for the Florida Keys in September of that year. As you can see in the Florida Keys, you're hitting up to 20-degree heating weeks. So this not only wiped out a ton of corals there, but it also wiped out some restoration plots. And as a quick aside, to try to combat reef decline, groups across the globe have turned to coral restoration as a potential way to stave off coral decline. So essentially the way that this works is that people will plant out fast-growing corals onto these coral trees, and when they grow large enough, they plant them out onto the seabed, onto these structures, with hopes that they grow big enough and form new habitats. But these corals are also susceptible to bleaching and mortality, but people are putting tons of money into growing these reef restoration plots. So in order to protect all coral reefs, including these new coral reef restoration strategies, coral reef managers need accurate long-range forecasts of coral bleaching. And this is where some of the work that I do comes in. And I'm here to argue that to predict coral bleaching far enough in advance, you need to know when bleaching occurred and also what the ocean and atmosphere are doing during this bleaching. So let's travel to the southern Caribbean island of Curacao to test this out. So the first thing that I did was determine when corals bleached in the past around Curacao. And the traditional way that people do this is through coral reef surveys. And what that entails is people take divers out on the reef, they take a ton of photos, and from those photos, you can determine what % of the reef is bleaching. You can imagine this is super time and labor intensive. You have to really be in the right place at the right time. So as a result, there's lots of observational gaps in both space and time. In fact, during most bleaching events, most reefs across the globe are not surveyed. So we have a lot of gaps in the past. So instead, my research takes us to another method of determining when coral is bleached, which is effectively asking the corals themselves, what did you experience? The way that I do that is me and my collaborators go out to reefs and we dive and we take biopsies of living coral skeletons. This is an image of me over here sampling a coral skeleton from Curacao. They look like this, Sharpie for scale. And then what we can do is we can CT scan those corals and look at annual density banding variations. So corals form annual bands, kind of like trees do. And sometimes when corals bleach, they grow super duper slowly because, like I mentioned before, they're starving to death. And they form these high density bands that we can then identify. We know that stress bands are a really great proxy of coral bleaching because when we compare the relative percentage of coral cores that have a stress band in a given year, which is over here plotted on the x-axis, and compare this to the actual on-reef visual observation data for that given year on the y-axis, it falls really close to this one-to-one line. And with that, the other cool thing about these corals is that the corals that we sample can grow for decades and even centuries. So using them, you can generate a continuous record of bleaching presence and absence for multiple decades. So using a bunch of corals from Curacao, I identified 9 strong bleaching years over the last century. The interesting thing to note is that you do not see any evidence of bleaching before 1990. And this is pretty consistent with other corals in the Caribbean. You're not really seeing bleaching until the late 1980s or so, suggesting that bleaching is indeed a recent phenomenon. So the next component that I was interested in is what's happening in the atmosphere and the ocean when strong bleaching events occur. So over here is a map containing sea surface temperature data as well as wind data of what we're typically seeing from 1980 to the present during these peak bleaching months of September to October in the Southern Caribbean. So you're seeing these strong easterly winds, and you're also seeing a generally cooler Southern Caribbean. However, when we compare what's happening in the 9 bleaching years to the whole, 1985 to the present satellite era, you're seeing that during these 9 bleaching years, on average, you have an extra hot Southern Caribbean, and you're also seeing a weakening of these predominantly easterly winds. So I decided to dig in this a bit further and to look at why are temperatures rising so much at Curacao and the Southern Caribbean. And the answer is that it's not just this North Atlantic warming. During normal conditions, like I mentioned before, you have these easterly winds coming in, which drives this Caribbean current in the Southern Caribbean. And as a result, this brings up a lot of cool water from the deep ocean to the surface, and that cools those coral reefs. There's also this wind coming from the east to the west also leads to a lot of latent and sensible heat loss. So you can kind of think about it like blowing on a hot bowl of soup. The more you blow on that bowl of soup, the more it's going to cool down. However, during bleaching conditions, you have a baseline warmer North Atlantic to begin with, and you also have weakened easterly winds. And due to these weakened winds, you have this weakened Caribbean current. So you have less of that cold water being brought up, and you also have less of that latent and sensible heat loss. So imagine, once again, that bowl of soup. If you're not blowing on it, it's going to remain hot. So what's ultimately responsible for this? The thing that's responsible for this pattern that we're seeing is what we call climate modes. And climate modes are essentially patterns of climate variability that are very well studied. They oscillate back and forth from positive to negative phase, and they influence weather and climate conditions across different regions. Specifically, I hypothesize that these 3 climate modes are what's driving the conditions in the Southern Caribbean. We have the Atlantic multidecadal variability, the El Nino Southern Oscillation, and the North Atlantic Oscillation. And all the data for these indices is made publicly available online, thanks to NOAA. And I take all this data and I put it into something I call the Coral Bleaching Advanced Predictor. So essentially, I test what combination of 1, 2, or all 3 of these modes could possibly predict bleaching in the Southern Caribbean. And what I find is that for a very particular combination of months, for the NAO index, the AMV index, and the El Nino index, over the last 70 years, so this is data from 1950 to the present, this particular combination of years is able to predict 8 out of 9 bleaching years. It's also important to note that bleaching occurs in Curacao in the late fall, so October, November, but the latest index used is June. So essentially, by the time that June 31st rolls around, you can access these indices online and determine whether or not bleaching will occur at Curacao. Like I mentioned before, this is data for the 1950 to 2022 period. And over this time period, you have 9 total bleaching events. These are what I determined from coral cores and also visual observations. And this particular metric predicts 8 of those events correctly. It only gives you 1 misprediction and 1 false alarm. And it also correctly predicts the 2023 and 2024 events, which we know were strong bleaching years at Curacao. When we compare this to the standard NOAA degree heating week metric, and once again, not to knock the degree heating weeks, it's a great resource, and it is a really good approximation of how much heat stress has built up on the coral reefs. Using that, if we assume that bleaching is happening at 4 degree heating weeks, we have 7 correct predicted events, but we have a ton of false alarms. The other thing to note is that the CBAP metric is able to predict bleaching 5 to 6 months in advance. However, the degree heating weeks are essentially an instantaneous forecast, so it gives you about a week or so of lead time to make any decisions. Both are calculated using publicly available and accessible data, thanks to NOAA. And in summary, so CBAP, this new metric that we pose here, is able to anticipate bleaching risk by capturing these large-scale dynamic processes. And by incorporating these climate modes, these climate patterns, it's able to predict bleaching months in advance. It's also adaptable to other reef regions if you know when bleaching occurred and didn't occur over the last few decades, and also what's broadly happening in the atmosphere and the ocean. And I guess as a takeaway, what this means for reef managers is that with this 5 to 6 months of lead time that this can confer, managers can now have the time to prepare appropriate mitigation strategies, monitor reefs, perhaps reduce tourism and other local stressors. And like I mentioned before, lots of organizations are putting thousands, if not millions of dollars into these coral nurseries and these coral restoration plots. This 5 to 6 month lead time gives managers the time to move these nurseries to a colder location or to tanks on land. So all in all, I kind of sped through the end there, but thank you so much for coming to my talk. I've hoped I've convinced you that coral reefs are so important to the world, and got to do our part in reducing greenhouse gas emissions. We've got to do our part in becoming better stewards of our environment. But also, federally funded science is so crucial for helping not only American scientists, but also scientists around the globe monitor and make decisions about coral reefs. With that, I'm happy to take any questions.
Thank you so much, Mariya. We definitely have questions. And I hope before you go back to sleep or before you take a nap later today, if you're able to scroll back through the comments here, as soon as you started talking, there was a flood of just coral reefs in all caps and people yelling about how wonderful your photos are. So the energy is there if you need a lift anytime today. I want to get right into these questions because we do have time. Can corals ever recolonize coral skeletons after the coral is bleached?
That's a great question. And the answer is yes, to some degree. So we see this often in the Pacific where you see these mortality scars within coral cores. And we've learned over time that what's happening is that often during these bleaching events, oftentimes a lot of the coral will die off. But like I mentioned before, a coral is a colonial organism. So the very top layer of that coral is alive. That's where the polyps are. Beneath that is just the dead skeleton. But even if you have a few polyps alive on the side of the coral, we found that these polyps, given good conditions, are able to resheet over that surface and are able to heal. So I know that my advisor at one point went to an expedition in the Pacific. They found this one coral that was dead. They came back 3 years later. It was alive. It turns out that they missed a few living coral polyps. And over time, I think it was over 3 years, these polyps were able to resheet over the entire coral. So yeah, bleaching isn't the end of the world. Corals can bounce back from bleaching. They can even bounce back from general mortality. But the problem is, as greenhouse gas emissions continue to rise, there's not enough time for corals to recover between bleaching events.
Okay. So I want to ask 2 more questions. I believe we have time. First question is from Furkeep. Is there something that does thrive where coral is not anymore? And I want to add on to that thing that does thrive, does it do the same thing for the reef, or does it change the way the whole reef works?
So we're seeing this a lot in the Caribbean. So a lot of the things that I'm mentioning here and a lot of the photos that I'm showing are hard, stony coral skeletons. And this is what really forms the basis of the reefs. And this is what gives reefs their structure. We're seeing in the Caribbean, as a lot of these stony corals are dying out, we're starting to see a resurgence of soft corals. And while soft corals are also great habitats for fish and other organisms, they don't quite confer the same level of ecosystem services. And also they don't form that stony skeleton over time. They don't add to that complexity in the reef. They often don't live as long. They also don't offer quite as much protection from coastal waves, like I mentioned before. Sponges are also thriving in some areas, but sponges are quite a mystery to me. They're also not quite as... they're a mysterious organism. They also don't quite offer that same level of ecosystem service. So you're seeing in a lot of areas, like your coral and algae is taking over, that sludgy algae, which isn't not really great for fish or other organisms. So yeah, there are organisms that are thriving where coral isn't, but unfortunately, we really need that coral to give ecosystems their structure and their habitat.
So corals are bleaching without enough time to recover, but they could recover if we were able to, act on climate change and do something about that. And when they do die, the things that take over their space are not the reef builders like the corals are. And this brings me to my question, which is not one that anyone specifically asked, but as you were talking, the comments basically said, this is so sad. And then when you were talking about corals being able to recover, a couple people said, ooh, this gives me hope. I want to ask you, Mariya, you just gave us a talk about death of something that is beautiful. And you started out by saying this is so good for all these reasons. What gives you hope working on these corals, on these reefs? Tell me how you wake up and you're still excited to do this.
That's such a great question. I mean, sometimes you really have to dig deep for that optimism, but in the places that I've traveled over the last few years to do my work, what's fascinating is that there are still corals that are surviving. And especially corals that live in really hot areas. And that seems to be a big target of future, the future of coral reefs is finding corals that live in really hot areas that are used to those hot areas and seem to be doing okay under future, under heat wave conditions. It's also interesting to see that even on dead reefs that aren't doing too hot, and like even after bleaching events, you still see a ton of fish there. So fish are still living around these coral reefs. They're still hanging on. They're still trying to take care of those reefs and pluck out that algae so new baby corals can recruit on there. But yeah, I mean, it's definitely tough to be optimistic, but I think there's so much work and so much technology going into trying to save coral reefs. And I think with the right messaging and the right tools, we can still continue to see coral reefs in the next century.
Yeah. So I used to work on reefs, and I'm just going to inject for everyone in the chat that I've heard a lot of people say that the tough thing is less that it's happening and more when people don't act to make things better, because we totally have the power. One of my favorite coral reef scientists ever, who was on my PhD committee, said, if it is a human-caused problem, then there is a human-based solution. And so I just want to re-up the link in the description for this live stream. You can act right now if you're in the US by contacting your representatives. You can act no matter where you are by talking to people about why we love this stuff, why it's important. And Mariya, I really appreciate you being a little vulnerable there, sharing what gives you hope. I do want to ask, we have time for at least one more question. You are getting so many technical science questions. I don't know if you're going to be inundated the next public place you go with all these questions, but you've got some, let's see. Oh, here's a great summary question. So you can kind of give us a last word about your work and the work in the field. What are some of the biggest unknowns in coral reef research?
Oh man, I mean, I think a big unknown is, why do some corals bleach when others don't? That's, fundamentally, that's an answer that is still, it's a question that's still out there. We don't know why certain corals, within the same species, are doing better than other corals, and how to predict what a specific organism's thermal tolerance is. I think, in my mind, as somebody who studies coral bleaching very specifically, that's such a big unknown. Yeah, it's also unknown at the rate at which corals can adapt to warming temperatures. That varies from coral to coral, and it's something that's very hard to quantify, but something that I'm very interested in hopefully learning in the future.
Thank you so much for being with us. It just ticked over to exactly 6 a.m. Eastern, and so I'm going to let you go get some rest. But thank you so much for sharing your research. This was great.
Thank you so much. It was great.
All right, everyone, we are in hour 41. It took me until the last hour, because I've been live hosting 5 to 7 a.m. my time, getting up at 4:30. Took me forever to realize this little count here is the hours into the live stream. I was like, what's that TV doing? Oh, it's the number of hours we are in this live stream. So we are now, it just updated. I must have called attention to it. We are starting hour 43, if that is to be believed. It is hard for me to keep track because of all the math I'm doing. Oh yes, I just got a message from behind the scenes that says, LOL, sorry. We are all so excited about scientists. We are all not paid to be here. It is the middle of the night for it seems like all of us keeping up this 100-hour live stream. It says now hour 42, which matches with my count. This is a live look at what it means to be throwing things together really fast for impact. So this whole thing only works, the hours, number 42 out of 100, because everyone here is showing up, showing support, lending energy and attention to this cause. So now that we are at the top of the hour, I have another hour to go as your host, and I would like to remind you why we are all together in the first place. So 42 means there are 58 hours left. I just want to remind you that you can watch any of the past hours, including the keynote speakers or including the people who are up in the middle of the night like me, on YouTube, on the YouTube channel where you found this live stream. You can watch past recordings. They will be publishing highlights as we are able to sleep and get those edited and together. If you want to hang out with me again, I will be doing the same time block, so 5 to 7 Eastern, tomorrow, which is Saturday, and then also Sunday. So I will be here providing this early morning energy for you at the same time the next 2 days in a row. And I will be giving a talk about my work tomorrow, 7 a.m. Eastern, so at the end of my hosting block. So I really appreciate that we're all together. Oh, and I wanted to mention, some of you in the chat are like saying hello and good morning and good evening to each other, because I assume you've been hanging out on the live stream together. And it is so cool to see that not only are we maybe letting people know about climate science, weather science, and the federal cuts in the US, but also y'all in the chat are meeting each other and uplifting each other because you are here because you care. I'm seeing multiple calls in the chat, so I will say this. Yes, please like the video, and YouTube will be more likely to show it to people, which would help with some reach. And okay, somebody else is saying that I should say subscribe. If you would like to, please subscribe. But thank you for being here, especially no matter what time of the world it is for you. We are here because we all know how important weather and climate forecasts are to the people in the chat and people the world over. The United States has long been a world leader in weather and climate prediction. US scientists developed the first computer models of the climate impacts of carbon pollution, the first computerized weather forecasts. So everyone, again, our data covers not just the US, and it is available to anyone. So people in a lot of places can understand what's coming days from now, weeks from now, and then decades from now. To make those forecasts work, US scientists created an unparalleled network of observations using everything from weather stations to satellites to planes to balloons to boats to floats to magnetic tapes. The resulting forecasting and observation system is a true scientific miracle, and we are excited on this live stream to share some of that miracle here with you and introduce you to the people who are making all of that work happen. All of that work happens not only because of the people, but because of the dollars invested by the federal government and the support for the scientific system within the US. So people in the US have been saying that science is important and worthy of our attention, money, support for decades. But in recent weeks, federal cuts have put this miracle at risk. Weather stations are so short-staffed that we are losing our observational coverage, which is already hurting our forecasts and putting people in danger. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and the climate is disappearing. This is not easily undone, because every time a student loses funding and their education ends there, how do we get them back? How do we get the future of science back? It does not have to be this way. If you like what you see on the stream, then please use the link in the live stream description, the link that's going in the chat, the link on the website for this live stream to contact your representatives if you're in the US, tell them to save our forecasts. The links that you are seeing will help you know how to do this and what to say. You do not have to be a climate or weather expert or a scientist to make this work. And just a reminder that anyone, live stream, globally, whatever, one of the biggest powers that you have all the time is to talk to people that you know and love and trust about what you think is important in the world and what's happening in the world today, so that we all know what's happening and know how we can act on it. This sounds so silly to say it out loud when you are someone who watches the news and who talks about the news to people around you, but think about, like, is there a group chat where you just don't say stuff to certain people because it's causes conflict? This is not a recommendation that you cause conflict, but I just want us to think about the relationships we have with people and that power that we have to bring things up. That's power. Let's see. Please spread the word to join the live stream. Like I said, if you like and subscribe, YouTube might promote this live stream a little bit more, but mostly we are here because we've all heard about this from someone. Right? Word of mouth is the biggest way that you can let people know that a bunch of really passionate, really sleep-deprived people are here to help you understand about these cuts and about weather and climate science. So please let us know if you have any questions or comments in the chat. Y'all have been doing a great job. I've not even needed to remind you before now. And I want to bring on the next speaker. Peter is a professor at Harvard. And Peter, I'll let you, again, you're on the East Coast with me, so it's 6:06 a.m. The floor is yours.
Okay, thanks. Good morning from the East Coast. Thanks to everyone who's been doing this. I've gotten to watch a number of them. It's really been a lot of fun. What a nice community you've assembled here. watching Mariya's talk just now, I grew up on Curacao between the ages of 2 and 5, and so hearing a little bit about how the coral reefs are doing and hearing her her optimism despite the difficulties was really powerful. So that was great to catch. You know, I was kind of wondering what should I share here. What are people going to be interested in? What I want to do is share with you a piece of work that we kind of have going on that's midstream. This is not the thing we've been working on for 10 or 20 years or that we even have figured out, but it's an interesting observation that depends upon a lot of the observations that have been made available through satellites and through weather stations. And it's, and in some ways, challenges a particular aspect of our climate models. And in that tension, you know, kind of there seems like there's something there, and maybe there's something that we have to learn. And so what I was hoping to do is kind of walk through this with you all and explain to you that there's all sorts of discoveries that are kind of inherently waiting for us. And so this is my attempt to frame it. It's going to involve a little bit of linear algebra. It's going to involve some observations. And if there's questions as we go along, I think I've set this up in a way that I can see that there's questions. I'm really happy to pause at any moment and just chat about what we're seeing, cognizant of the time. So I just have 15 slides. So I think it won't take too long. Finally, let me really highlight, this is Annalea Albright, who's a postdoc at Harvard, has been doing a lot of this work, and we've been closely collaborating. And so if you have really hard questions or you really want to follow up on things, talking with her is going to be something that would be really helpful. Okay, so with that, let me just talk about, there's a number of data sets that I'm going to be using. I made a table here. First of all, Earth surface temperatures, there's a number of groups that provide these. There's some from the UK, there's a number from the US. The one I'm using here is the Berkeley Earth surface temperature, and the reason why I'm only listing one is that for annual average temperature over the period that we're looking at here, we have those pretty well understood. We have a good observational record. And the Berkeley Earth surface temperature, its acronym is the best. I'd say it's among the good ones. Then we have 4 different rainfall data sets here that we're going to be calling upon. Reagan is from interpolated land rainfall observations. Persean is using satellite observations that's trained on a weather model that incorporates a lot of different observations, both from satellites and from in situ atmospheric observations. TAMSAT is an infrared cloud top rain gauge, infrared cloud top satellite observation system that's calibrated on rain gauges from the surface. And then we have iMerge, which is another microwave, it's another satellite observation data set. And so we have a variety of different ways of getting at these things. And the reason why that's so important is measuring rainfall is actually really hard. If you're trying to measure it from space, you see the raindrop falling through the air, but you have to figure out what rain actually hits the ground. If you're sitting in the ground, you have this little tube that you're measuring rainfall in one particular location. How much does that tell you about what's happening everywhere else? And have you been able to maintain that tube in a way that it's providing homogeneous observations over decades? These turn out to be really hard. And so having a certain degree of redundancy makes it really important. I wouldn't be showing you this unless we had multiple different data streams that we could look at and get similar answers so that we'd have confidence that we're not just looking at noise. So it's one reason why you actually need a degree of redundancy. You also need a degree of continuity to kind of do this sort of analysis. So yeah, does it mean the same thing as a microwave? Yeah, it's microwaves are really good at heating up water, right? If you put something frozen in there, it doesn't actually work so well. It's not till it thaws and you have water. If you put something that's dry in there, it doesn't work so well. Microwaves absorb water. What that means is that they radiate. Water radiates quite well in the microwave region, and so if you have a satellite that's in orbit, the ability to sense microwaves becomes really important because that's sensing the water that's in the system. Water gives off things at the microwave frequencies. So here is it's kind of the same equation 2 times on the left and the right. I'm going to be doing this for both precipitation and for temperature. it's just a super simple model, okay? So if we look at the precipitation one, what this says is P of t, precipitation at time t, is going to be equal to the precipitation at the previous time step. So this is going to be the previous year, multiplied by alpha, and alpha is going to be some number that's less than 1. And then we're going to add some random component to it, this eta. And so you can see this is in some ways the simplest time evolving model that's possible. It's just saying that the present depends on the past to some degree that is controlled by alpha. And then there's also noise. And so if you have a system like that, if your alpha is equal to 1, this is a so-called random walk. And over an infinite amount of time, we'd expect it to vary infinitely. The reality is that these things are going to be bounded to some extent, and so we expect alpha to be less than 1. The variance of p then in expectation is going to be equal to just how variable that noise term is. And so I'm using the term sigma here to indicate the standard deviation. The standard deviation squared is the variance. And so the variance of this eta variable is clearly going to control the variance of the precipitation. So that makes sense. That goes up in the numerator there. And then in the denominator, there's this interesting term, right? It's 1 minus alpha squared. And so you see if alpha goes to 1, then this thing blows up. It goes to infinity. And if it's a little bit less than 1, then you have values that are not quite as big. And so what we're talking about here is just how variable is our precipitation and how much memory does our precipitation have. That turns out to be really important, right? If there's a lot of variability, it becomes harder to adjust. What should we grow as crops this year if it's going to change from year to year? If there's a lot of memory that's present, what that says is, oh, if we know what's going on this year, that actually tells us about what's happening next year. And so then you have this inherent basis for being able to do prediction. We can write the same equation for temperature, and it's exactly the same thing. I've just now used a beta rather than an alpha, and it's the same dynamic. Okay. So we have this really simple linear algebra way of representing interannual variations in rainfall and temperature. Okay, so here's my main result. Again, credit to Mariya Albright for doing the calculations here. And let me see if I can articulate what we're seeing. Okay, so I got this one thing on that's measured CMIP 6. This is the Climate Model Intercomparison Project, Phase 6. And this is a consortium of climate models that are run from groups that are around the world, including groups in the US who may not be able to run these going forward. Now, each color is a different model, and there's multiple entries for each model because there's multiple runs that are done with each of these models. These are historical simulations where these climate models are forced with the radiative effects that we know have happened historically, and then they are integrated forward, and we look at what they do with regard to temperature and precipitation variability. And I've put them in this very simple context of just what is that innovation variance in that simple autoregressive order 1 model that I was showing you in the previous slide. And then we have the observations, okay? And so if we look at the x-axis, we have temperature innovation variance, and at the y-axis, we have the precipitation innovation variance. And what this is then indicating to us is that there's this kind of center of mass where all the models sit, and then there is a location where the observations sit. Those bars are the 95% confidence intervals, and so that things don't overlap. There is this big difference where the temperature innovation variance in observations is less, and the precipitation innovation variance is not significantly higher, but it's a bit higher. Okay. Just quickly looking at the comments. Okay, so do we got that? Okay. So now there's a discrepancy here, okay? And that's always interesting when you have observations that you can there compare against your simulations, and if they don't match up, you're gonna learn something. Sometimes you learn that your observations aren't actually exactly what you think they are. Sometimes you learn that your simulations are missing important processes that if we took into account would allow us to better understand how the climate system is working. Okay, so that's innovation variance. The other component is this AR1 coefficient, this autocorrelation. This is a measure of how much memory there is from one year to the next in our temperature and precipitation variable. And here's the thing that kind of blew us away. Right? We look at this, and there's just a massive difference, right? So if we're looking at the observations, we have an regressive order 1 coefficient, this alpha term, which is around 0.125, whereas the simulations are around 0.025. Okay, so a factor of 5 difference. The temperature coefficient is also somewhat different, and there's only one model. The one that comes from the United Kingdom that is kind of similar in terms of how much autoregressive memory there is in temperature. Okay. So this sort of discrepancy then raises the questions, of course, of why. Where does this come from? And if it's real, what can we do with it? Okay, so now what I'm going to try to do is use a couple techniques to see if we can start to characterize what it is that we're seeing here. So I've kind of shown you this at a very high level statistical framework. I'm going to now start to try to develop some maps and some time series and see if we can understand the nature of the variability. So this question from Fish, how many people are working on this? So it depends how you count it, right? So there's a string of papers in the literature over the last couple of decades that have looked at this sort of memory in the climate system. In fact, we're running a summer school about memory in the climate system in northern Sweden this summer. From students from all around the world will be looking at this. But there's not a whole lot of attention that's being paid to it. One thing I like to mention is, in some of the sciences, you tend to try to be a little bit secretive about what you're working on because you don't want to get scooped. In this weather and climate science, it's more like, hey, we have so many problems that are really interesting and relevant. The more people that will work on them, the better. And so, we haven't published on this, but it's fine. I'm happy to share it. We're kind of midstream with it. If other people wanted to jump in and look at this as well, great, please do. Okay. So here's a map of this auto correlation coefficient for precipitation. And that's the one I'm really going to focus on here because in many ways it's the one that's the most strikingly different and hasn't been really commented on quite as much in the literature, though I'll point out in a second that there is one paper that kind of nailed this in the same way that we're finding it earlier. So if we look at this, there's a bit of a pattern that comes out. If you look in the tropics, you can see that it's mostly pretty deep red, okay? And so what we're seeing here is a lot of memory in the tropical climate system, and that's not really surprising. We know that there's the El Nino Southern Ocean phenomena, which has this interannual variability associated with it. And so in part, we're maybe picking up on that. There's also these interesting places where we see these blues, this anti-correlation. It means if it rains more one year, statistically, it is expected to rain less the next year. So if we look at the southwest of the United States, there's some places here which have kind of light blue. You can imagine there's a scenario there where you get a lot of rainfall one year, you have a lot of vegetation grow, and then the next year you tend to get a drought. And so that sort of anti-correlation could be really important for understanding why there's high forest fire risk in certain locations. Just to give one example of why understanding these things could be pretty important. Okay. Let's move on now. So there's this paper from Kumar et al. In 2013, and they did this with observations, totally different observational data set, a completely different collection of climate models. And what they found is that there is memory in this rainfall at the interannual timescale as well, with a very similar pattern. They actually use something called Hurst coefficient, which is more looking at power law behavior in the precipitation time series variability. But it turns out to have a very similar pattern to the somewhat simpler autocorrelation that I'm showing you here. You see that the places with memory are largely in the tropics, as well as the western portion of South America. If we flip back for a second, you see that there's this strong tropical band here, particularly in the Sahel, in Indonesia, and then in the western part of South America. And so those things pretty much line up with each other. So this has in some ways been a long-standing mystery. Why do our observations, in fact, show more memory than our simulations? If anything, you'd expect it to be the opposite. If you had noisy observations, you'd expect it to be uncorrelated because that noise would hide the correlation, whereas we don't really have noise like that in the simulations, at least not observational noise. And so the fact that it's coming out stronger in the observations than in the simulations, in some ways, makes it even more intriguing. And so, great question, Cameron, are these correlations stable over different time ranges? And how much do they shift? Let me tell you, it's exactly what I'm going to get at here. Let me get you kind of a way of looking at the spatial temporal variability associated with the structures that are giving rise to these correlations. And so to do that, I'm going to call on one other kind of linear algebra technique. This is something called maximum covariance analysis. It's kind of interesting. Now, if you think of a matrix U, which is all of your temperature variability, annual averages looking back for about 50 years. Okay, so it's a giant matrix because there's one entry for each location on the globe, and then there's one entry for each year. You put that all together, and you have that matrix U. And then you do the same thing with your matrix for precipitation. And then you multiply the two matrices together. And what that tells you about is the covariability of temperature everywhere on the globe with precipitation everywhere on the globe. And so we get this large covariance matrix. Okay, and then what I'm going to do is apply a technique called singular value decomposition. I'm going to pull that matrix apart in a different way than I originally constructed it. Rather than doing this location by location, what I'm going to do is I'm going to pull out the patterns that explain the most covariance between temperature and precipitation. We're going to look at those. So it turns out to be a powerful technique for looking at spatial temporal variability. So this covariance then we're going to look at in terms of what it is that explains how precipitation and temperature kind of covary with one another. Let me show you the first one. Here, there's a time series and a map that's associated with each variable. I'm just going to go through the maps first because those are pretty intuitive, and then we're going to look at the time series of the third one, which I think is pretty interesting, and I'll try to wrap up here in about 5 minutes. So if we look at precipitation and temperature, you see this kind of global warming pattern in temperature. So this is really what's happening as the globe warms up and cools down. And in our analysis, interestingly, what we're finding is the globe warms up, Africa is drying, other places are getting wetter. And this appears because we're controlling for a lot of the other modes of variability. But this is the one that comes out as being the most important. Some ways it's a frightening prospect because if many places are water limited in terms of food production within sub-Saharan Africa and in North Africa. And so if you're seeing an expectation for things drying as they get warmer, that could be really concerning. Now, this is all historical variability. Whether or not that actually holds exactly going forward is something we need to think about very carefully. And so this is not a prediction, but this is a description of the historical covariability that's been present. Okay, second, I told you about the El Nino Southern Ocean phenomena. When you have an El Nino, it warms up in the Eastern Equatorial Pacific, and then, boom, that's exactly what we're finding in the temperature pattern at the right here, this pattern of warming in the Eastern Equatorial Pacific relative to the Western Equatorial Pacific. When that happens, you get this shift in global rainfall patterns, and it gets drier, including in Curacao, like we heard about in the previous talk during an El Nino, but kind of in northeastern South America in general, this southern Africa and Australia and Indonesia, and then a little bit of a weaker correlation, but largely in South Asia as well. And so this is pretty well known. And then this third one, let me just talk about it a little bit more detail, because this one I don't think is quite as well appreciated. Now, the temperature pattern, these things are modeled in a little bit. I'm just giving you simplistic interpretations of them. But if you look at it, there's this distinction between the northern hemisphere here and the southern hemisphere. And to zero order, what this temperature pattern I think is telling us is that when you have cooling in the northern hemisphere and warming in the southern hemisphere, so you get this asymmetric heating between the hemispheres, what you get is in the cooler hemisphere, it dries. In particular, there's this rain band, the intertropical convergence zone, that moves north and south. And when it is cooler in the northern hemisphere, that intertropical convergence zone shifts to the warmer hemisphere in the south. Okay. And again, we're seeing the locus of activity being in Africa. We're only looking at rainfall over land here because that's what I'm particularly concerned about with regard to implications for agriculture. Now, you can see is a shift in the rain band further south, which would then cause drying in West Africa, in the Sahel in general, and kind of across this band, kind of in the northern tropical regions of Africa. We also see drier conditions in India and in Indonesia, and places in Central America and North and South America. And so this is a big systematic shift to the south, which would have just kind of amazing consequences. And we in fact did see this. So let me give you a simple description of this. If we just average over longitude, and so we're looking at zonal averages, in the east, what we're saying is if the temperatures are colder to the north and warmer to the south, we get this southward shift. And in fact, then what you do get is these drier conditions in the north and these wetter conditions in the south. Okay. Now, this happened, okay? Between the 1950s and the 1980s, we did see this global shift of the intertropical convergence zone to the south, particularly in Africa. Then we saw this recovery. In some ways, this recovery really mirrors what we've seen with aerosol concentrations in the Northern Hemisphere, particularly in Western Europe. And there's a theory that this cooling that was created by the aerosols increasing in concentration through the 1980s, leading to a shift of the intertropical convergence zone to the south. And then with cleanup of those aerosols and the cooling effect that they cause, since the 80s, because of environmental regulation, as kind of led by the Environmental Protection Agency in the US, what we had is a situation where we had a recovery. But now what we have is a Northern Hemisphere that is heating up faster than the Southern Hemisphere, and it's pulling that intertropical convergence zone back to the north. So that's kind of a story that can be told here. That's probably appropriate. And that's causing systematic changes in rainfall. It's also accounting for a lot of the memory that we have within the interannual variations in temperature and precipitation. Now, the one thing I want to point out here is that if we go to that region in West Africa, where we see these systematic shifts taking place, this kind of locus of activity, and we look at what our climate models are doing, our climate models are fantastic. They simulate all sorts of aspects of the climate system, but they do not get the intertropical convergence zone, particularly in West Africa, with much skill. So the observations are in black. The simulations, are in green. I have 6 different simulations shown here, but I could show a lot of others. And I'm plotting the northern edge of this intertropical convergence zone, this rain band that shifts to the north and the south. And I'm plotting that against latitude. They're not offset from one another. This is the actual latitude that they exist at in the simulations and the observations. They don't align with each other. And there's just this systematic climatological difference. And so we know that there's this opportunity here to improve our climate simulations, just baseline in terms of the climatology that they produce. In addition, the variability that we're getting in the simulations is not like what we're seeing in the observations. So there's this opportunity to improve these things through observation model comparison. And I have some ideas for why that is, but I'm going to skip through that because the time has gone quicker than might have hoped. So let me just say a few conclusions. Observed temperature and rainfall show greater persistence than simulations. The majority of interannual temperature and rainfall covariance involves global warming, the El Nino Southern Oscillation, and the interhemispheric mode of variability. If we look at the covariant components that I got with this maximum covariance analysis, what I could do is take those out of the observations and the simulations. And what that would do is make temperature uncorrelated. And I would show you that precipitation actually becomes anti-correlated, which is a kind of a strange phenomena to have arise. And it leads to other questions of exactly what's happening. And it could be that the interannual rainfall variations are inherently anti-correlated, except for the persistence that is imposed by temperature influences. And so there's some simple models I can use to express that. And there's a lot more work we need to do with the actual climate simulations and the observations to kind of further pursue and unravel what it is that's giving rise to this interannual variability that we're observing globally. Okay, so I'll stop there. Thanks for listening. Wherever you are in the world, it's been nice to share a few things with you.
Thank you very much, Peter. So I know you were answering questions as you went, and I just want to ask you one that kind of prompts a summary view from you before I let you go.
Yeah.
This is from Cameron. I'm sorry, I wanted to ask one from AR. Sorry about that. What do you mean by memory, that nature will return to previous states or just that the past changes the present?
So I think memory does mean that the past has to somehow influence the present. And the specific way that I was characterizing memory in this case, interestingly enough, you said it was AR who asked the question. So AR is that's the acronym that I'm using for auto-regressive processes. And what an auto-regressive process means is that the state at this time instant depends in some linear way on the state in the previous time instance. And so I was characterizing that memory by saying this is the degree to which the present depends on the past at these 1 year increments.
Perfect. I don't know that I've really thought about that, and I certainly have never thought about it with so much math as you have. Thank you so much for sharing your work at this time of day in particular, and I hope you have a lovely day.
Yeah, you too. Thanks for doing this.
All right, everyone, we are halfway through hour 42 of the live stream. I want to take a quick minute to remind us why we are all here together. We've seen so many great talks. There are so many left to go. We are approaching the halfway point. If you are a super nerd about this live stream and about this content, being here for hour 50 might be something special. But for now, we are in hour 42, and I'm so grateful that y'all are just really answering each other's questions in the chat and doing such a good job being high energy. We're here because weather and climate forecasts are important, because you as scientists have led the world in weather and climate predictions, but not just for ourselves, for the global discovery and potential to make good decisions based on that data. Some of the things that U.S. scientists have done are develop the first computerized weather forecasts, develop first computerized models of climate impacts of carbon pollution, and we have huge observations of, huge networks of observations that are in the ocean and on land and in the air. The excellence has been brought about by a long-term investment in the science infrastructure in this country by the public, by dollars and by support and by encouraging people to love science in this country. But now funding cuts are affecting all areas of weather and climate science. Weather stations are short-staffed, climate labs are shrinking or are shuttering. And I want you to know that it is not hopeless. That's why we're holding the live stream. If you want to act and you are in the US, you can use the link on the screen or in the description to get some help doing that. You don't have to be an expert yourself to make a difference. And whether you are in the US or not, talk to people around you about what you are seeing, what you know to be important to the way that we all live well on this planet. With that, I want to make sure we give enough time for our next speaker, who is Delta Merner. Good morning. I love that you put doctor in the front of your name on the stream. That is something that I don't do very often, but when you've earned it, you've earned it. Congratulations on that. So I'm going to hand the floor to you. It's all yours.
Wonderful. Thank you so much. Good morning. I'm excited to be here, to be part of this, and to share some of my work on climate attribution in science. So I'll start with just a little bit about myself. So I am a lead scientist and associate director in the climate energy program at the Union of Concerned Scientists. This past semester, I was also able to teach geomorphology at UMBC. And it was really nice to be able to reconnect with some of the physical science that I focused on during my PhD work, and to be able to work with students. It was also really terrifying seeing students that are preparing to graduate, students who have been working towards careers in agencies like USGS, the US Geological Survey, which helps to provide reliable and partial information about the natural world to inform decisions on resource management, on public safety and environmental protection around water resources, geology and hazards, ecosystems, mapping and remote sensing. So students who are preparing for this while the agency is being gutted, and the opportunities for kind of public service through science are really being slashed in this country. So right now I am 10 years out of my PhD, a little over, I think, actually. And I've never worked for the federal government myself, but I am here today because government funding for the sciences is what allowed me to be able to get my education. So during my undergrad, I had two different REUs, which are research experience for undergrads that were funded by the National Science Foundation. And it was through this work that I was introduced to research, that I was introduced to modeling, and really had the opportunity to learn those skills. And then for my PhD, I was fully funded by the National Science Foundation as well. I was really lucky to be part of a program that no longer exists called IGERT. And I think that stood for Interdisciplinary Graduate Education and Research Traineeship. And this was a program that was developed for students who knew that they wanted to do research in an applied way. So my PhD research itself was focused on flooding in southern West Virginia, and really I was able to have an interdisciplinary committee where I pulled together meteorologists, flood hydrologists, geomorphologists, but also kind of the human side, working with critical human geographers. Directly after school, I worked at the American Institute of Physics as a senior scientist for 5 years, and now I'm currently at the Union of Concerned Scientists. I've been here for a little over 5 years. And today, during this talk, I'm going to share a little bit about the current research that I do at the Union of Concerned Scientists. All right, so that is, as the main slide says, is climate attribution science. So what is climate attribution science? This is a rapidly advancing field that helps us to understand the influence of climate change across a range of factors. So from long-term shifts in climate patterns to the role of climate change in altering specific events. It can also be used to analyze the source of emissions, allowing us to understand how those emissions contribute to climate impacts. By analyzing data, models, and observations, attribution science shows how climate change has altered everything from temperature trends to extreme weather events. It helps to distinguish between natural variability and human influence. So it helps us answer critical questions like, did climate change play a role in that? And what emission sources are contributing the most to climate change? So in short, attribution science can explain how climate change makes a heat wave hotter or a hurricane-related downpour more intense, as well as quantify how emissions from specific sources contribute to climate impacts. Now I want to break this down just a little bit further. So attribution science right now has 4 subfields, each offering a unique perspective on climate change impacts. So first we have trend attribution, which identifies patterns of changes over time, showing how climate is shifting due to global warming. The second piece here, event attribution, is probably the most well-known area. And this examines specific extreme weather events, such as hurricanes, heat waves, or floods, and asks how climate change has altered them. So for an example, an event attribution study shows that climate change increased Hurricane Harvey's rainfall by at least 15%, and that climate change made the 2019 European heat wave as much as 100 times more likely to occur. The next category is source attribution, and source attribution determines the relative contribution of different emission sources, such as the fossil fuel industry, the agriculture sector, or even a country itself, right, to the overall rise in heat trapping gases in the atmosphere. At UCS, the Union of Concerned Scientists, we've conducted source attribution studies that look at the contribution of the largest carbon producers and global, to global surface temperature, to sea level rise, ocean acidification, and wildfires. And I'll talk about that a little bit more later. Finally, the last area is impact attribution. This is the newest area, like the newest subfield. And this is looking at how climate change is affecting ecosystems, economies, and communities. So altogether, attribution science can help us understand not only what is happening, but also why and who or what contributed to it. All right, so I want to take a moment just to dig into how attribution science actually works. So attribution science is often comparing 2 scenarios: the world as it is today with our current greenhouse gas levels and warming against a counterfactual world. So what the climate would have looked like without human-caused emissions. So using climate models and observational data, scientists stimulate both scenarios thousands of times, right? By comparing the frequency and severity of events across those 2 worlds, we can determine, how much more likely an event is because of climate change, or how much more intense the damage or damaging impacts were as a result. So this method is statistically rigorous, it's peer-reviewed, and it's also something that's constantly improving, which is really exciting about this field. While it's technically complex, the core idea is straightforward, right? So compare what happened to what might have happened in a world without those emissions. I wanted to illustrate this using a figure from a paper. So this figure shows attribution, how attribution science works by comparing the real world to a modeled counterfactual. And, you know, so what would have happened without human caused climate change. This graph here, just to say specifically, the graph on the left shows observed and modeled global mean level surface, the sea level rise from 1900 to 2012. The center graph here is the counterfactual. So this is the climate model run without the added emissions, again, looking at that sea level rise. And then finally, the last graph here is, is the difference between these two worlds. This is how we're able to attribute sea level rise, right? To see how much the sea level has risen specifically because of these specific human activities and climate change. So this side-by-side approach is really core to attribution science. It quantifies how much worse climate outcomes could have been, because of emissions, and asks what if we hadn't warmed the planet. Just for another view of this, attribution science doesn't just tell us whether climate change caused event, it helps us to understand how it changed the nature of that event itself. So in this figure, we see two overlapping climate worlds. So again, picture those counterfactuals. The dotted curve represents a counterfactual climate, what the temperature distribution looked like without human influence, and the solid curve is the present climate shaped by human-caused greenhouse gas emissions. The vertical dash line here marks an extreme heat event. The shaded area that's under each of those curves then shows the probability of that event, or a worse one, happening in each of these modeled worlds. So in the past climate, it was very unlikely, shown kind of by the small purple area. But in today's climate, the likelihood has increased dramatically and is now represented by the larger pink area. So we're not just saying, this event wouldn't have happened at all. We're saying we're saying it became more extreme, more probable because of human influence. And that's the nuance that attribution science really captures. All right, so how do we actually apply this? This is really important. This itself is a graphic from the IPCC. This is from the 6th assessment report, and it summarizes how science now clearly shows that climate change is making many extreme events more frequent and more intense. So we see more extreme heat, longer and deadlier heat waves, heavy rainfall events that are happening more often, increasing flood risks. Drought is becoming more severe for some regions. Fire weather, the kind of hot, dry, windy conditions that fuel wildfire is also on the rise. And our oceans are not only warming, but they're also acidifying and losing oxygen, demanding, this is something that damages marine life and is harmful to coastal communities. So these are not just general trends, right? Attribution science is helping us to connect this specific events, like a deadly flood or record-breaking heat wave, to human-caused emissions, often with high confidence. It's important to note here that the inclusion of attribution science in the IPCC 6th assessment report marks a real turning point in its evolution and acceptance in the scientific community. What was once a developing field is now recognized as a critical part of climate science. It's rigorously peer-reviewed, methodologically sound, and broadly endorsed by the scientific community. So I wanted to pull this up just to show, attribution science isn't theoretical, it's being applied. In this chart, we're looking at 170 peer-reviewed studies, and it shows how scientists have assessed the role of human-caused climate change over 190 extreme weather events across categories that you see here: heat waves, droughts, floods, ocean impacts. The red bars show where human influence has made events more likely or more severe. That's specifically clear for heat. Nearly every heat-related event studied shows a strong human fingerprint. Even in areas where there's a less clear signal, like cold events or some storm systems, scientists are actively investigating and refining methods in these areas, right? So I also want to point out the portion of gray that's here. So this is areas where there's insufficient data or the results are inconclusive. And this is something that's also really important to have this transparency in science. All right, so attribution itself science itself is not equally advanced for all types of events, as you saw a little bit in the last graph, but just to kind of drive that home, the strength of the science varies based on the type of event, the region, the availability of data, the maturity of method that's used to model those events. So here is just 2 panels to kind of show the evolution of attribution science. Panel A shows where we were in 2016 regarding confidence in attribution science. Events like extreme heat were already highly attributable to climate change, while events like severe storms or tropical cyclones, we still had a harder time to link that with confidence. But panel B, this is published in the Frontiers in Climate, shows how much the field has progressed. So today we have robust evidence, not just for terrestrial heat waves, but also for marine heat waves, extreme rainfall, and different types of drought. So in short, the science is not yet possible for every single event, but it is growing stronger, faster, and more precise every year. New methods, better data, a deeper understanding of climate systems are making more types of attribution possible, even for complex or compound events. Now, quickly, I want to talk a little bit about the area that I focus on. This is event attribution. So the science has shifted to be able to not just look at climate change resulting from all human-caused greenhouse gases. We're able to attribute those changes to specific emission sources. What I'm showing you here is a graph in blue of the global carbon emissions from all fossil fuel producers and cement manufacturers since 1850 in million tons. In red, this is from just the top 90 carbon producers. This is work that was published by Rick Heady, and he found that nearly 2/3 of all industrial carbon emissions, starting from the Industrial Revolution onwards, can be traced to 90 carbon producers, investors, and state-owned fossil fuel companies. So just to run through quickly, the colleagues at my work and kind of teams building off of this have done a number of studies to understand the impacts of the emissions from these sources. This first one is looking at global mean surface temperature rise, where 42 to 50% can be attributed to those companies. This next study is looking at ocean acidification. Again, you have around half of it, ocean acidification, that we've seen globally connected to these handful of emitters. The most recent, or another study, is on wildfires, which I think the next speaker is actually going to talk about in more detail. So this is a 2024 study that looks at increased wildfire-prone conditions in the Western US and Canada. And then finally, I want to highlight a study that I co-authored that was published a few months ago. This was led by Dr. Sadai, who will also be presenting, I think, later today. What's new here is that we didn't just look at the contributions of emissions to sea level rise up to today. We also looked at how past emissions from fossil fuel industry will shape sea level rise well into the future. So again, using that modeling and counterfactual scenarios, we asked, what if the world's largest fossil fuel companies had stopped emitting at critical historical moments? And you can see some of the findings here, what those differences would be. And again, I think this research is really critical for us to be able to make informed decisions, to be able to apply policy to where it matters, to really get at the root of what's happening. So attribution science itself is incredibly powerful, but it has limitations. And I want to make sure that I'm really clear what the value of this science is. I often get asked, was an event caused by climate change, or see headlines like Hurricane X was caused by climate change. However, this framing doesn't really accurately reflect what attribution science does. So a better question is, did climate change make this event more intense or more likely? For example, while some events like the 2021 Pacific Northwest heat wave are directly linked to climate change, more often we see results like early season heat in South Africa, in South America, where climate change made the event 60 times more likely. And then just real quickly, one last thing I wanted to mention for this space. Over the past few years, I've had really the honor of engaging with the Intergovernmental Panel on Climate Change, the IPCC, which is the world's foremost scientific body for assessing climate change. So this was created by the United Nations in 1988. And the IPCC produces comprehensive peer-reviewed reports that synthesize the latest global science on climate risk, on impacts and solutions. These assessments guide international negotiations, national policy, and local decisions on how to respond to the climate crisis. I bring this up because US research plays a really vital role in the IPCC report, from foundational climate modeling that Virginia was mentioning, right, to satellite observations. This is what we need to advance extreme weather attribution, to understand our energy systems, to really understand climate impacts on agriculture and on health. Contributions from US agencies, from US universities and research institutions help to ensure that the IPCC report reflects cutting edge science, and it helps shape effective evidence-based responses to climate change around the world. So I honestly believe that we're better off for having the IPCC, and I appreciate the global work that makes it possible. But I'm also really deeply concerned about how efforts to defund science in the US could impact this work in the long term. I'd say, maybe just to conclude, kind of overall at my core, I want decisions that we're making in this world to be informed by the best information. And science plays a really key role in that, right? So we need the up-to-date science to be able to make those informed decisions. And with that, I will end the presentation. Thanks, everyone.
Thank you so much. I think many of us in the chat have been talking about how this is a new term for us, attribution science. And I'm realizing as you went through this talk that I feel like I've heard of this all the time. This event was X% whatever changed by the things that have happened to the world recently in terms of, climate and global changing and that kind of thing. So I really appreciate you making this something that we all know about now. You have multiple questions. I'm going to ask the specific question first that Cosmic put in the chat, and then I'm going to nudge it to be a little bit broader. So Cosmic asked, do you look at the intensity of LA wildfires impact to the community with the loss of homes, insurance being denied, and a study about the link of wildfires linked to increased chance of lung cancer? And I want to broaden it up to be, how do you decide which events specifically to do attribution science for, and which do you let go?
Yeah, that's a great question. One of the things, kind of going back to that first, or one of the charts that we looked at, is understanding, right, that attribution science isn't equal for all types of events. And that has to do with the physics that's behind our modeling and understanding those events. So that does play a role. In essence, anything that is directly connected to heat, so heat events themselves are going to be the easiest to model, the most direct, because the physical relationship between what we see with increased CO2 and heat itself is the simplest relationship. From there, you start to kind of have more variables that go into your modeling, so it gets more complicated. Like I said, the next speaker, Dr. Carly Phillips, is going to be speaking about wildfires. So I'm excited for you to have an opportunity to dig into that a little bit more with her. I think to answer the question in whole though, so I haven't specifically looked at LA wildfires particularly, but the piece that you're talking about is really understanding that impact. And one of the things that's really exciting that's happening in attribution science right now is that the community is starting to do what's called end-to-end attribution. So I talked about the different types of attribution. So the impacts, the event, the source, the trends, all those pieces, right? And end-to-end attribution science is saying, let's look at these pieces all together and have a single chain of understanding what's happening. So understanding the trends that we're analyzing, the sources, where those emissions are coming from, the events that are happening ideally, right? And then what those impacts are. So the pieces that you're talking about with impacts on community, loss of homes, insurance being denied, those are the types of questions that can fall into this impact attribution piece, but can again be connected. And there was a study that was published in Nature just last month, I think it was, that really laid out the argument for end-to-end attribution and some of the methods for addressing that. So that is kind of the next level of this field, is making those firm connections. And impact attribution in general is a really exciting area that allows us to apply this work in really meaningful ways.
I am imagining the pettiest parts of me being very excited about end-to-end attribution, because I know I love when things are not fair and I can point out exactly how they're not fair. I'm imagining that kind of energy being like, it's that thing's fault. And I'm imagining a certain sense of satisfaction that comes with this. We are almost at time. So we do not have time to answer all the questions. I'm sorry for everyone in the chat who's going to be skipped over here, but I want to give you the last word by answering, let's see, Lila Kulat's question, which is, where can people go? What sources can they use to learn more about your field?
Yeah, so at the Union of Concerned Scientists, we do a lot to try to help communicate science out. So we do have a page that synthesizes attribution science. We're constantly, science is coming out in the field, updating. So I'd encourage that. There's also other institutions that are leading around attribution science. So you can see the Sabin Center at Columbia posts a lot around attribution science and ways to apply that. But yeah, you could start with we have kind of an explainer page that we connect to different resources there.
Perfect. Thank you so much. I know it's early. I'm going to let you go. For everyone who has been with us, thank you so much for staying with us. It is time for a reset on the live stream. YouTube has a cap for how many number of hours we can go to before we have to start a new segment. It is not 100 hours. This is the sign off for me as your host today, but I will be here for the same block tomorrow, which is Saturday, and the next day, which is Sunday. I'll be giving a talk about my work tomorrow at the end of this block. It's been so great spending my very early morning with y'all. The link that you need to get back into the live stream will appear on your screen once I officially say goodbye. And just use the links that you've been using to get back here. It may take a couple minutes to change over, but don't worry, we will be back. We are going to reach 100 hours with you all. Thanks so much. See you in a second.